Good morning. It's 6 o'clock here in Austin, Texas. We're going to officially kick off this workshop at 6:05. So stick with us and grab a beverage, do whatever you have to do, and we'll be back with you in a few minutes. Thanks. Okay, we'll be starting in about a minute or so. Hang with us. Hello. Okay, it's 5 minutes past the hour and it's time to get started. Thanks a lot for joining us today. It's 6 a.m. in the morning here in Austin, 1 p.m. in Central Europe, 5:30 p.m. in Mumbai, and 9 p.m. in Tokyo. So please grab a beverage of your choice and listen in. Before we officially start, I'd like to get a few of the comments and common questions that we have answered. First off, given the wide disparity in time zones of the attendees, this entire session is being recorded and will be made available on the FCG YouTube site. Excuse me. Where used, PowerPoint presentations will be made available after the event. Please, please, please ask questions during the segments using the Q&A tool that we've provided. Don't be shy, you're anonymous to us. Our plan is to stop the pre-recorded content in between major sections and stop to answer questions. If there's no questions, we're just going to keep rolling. So it's a good idea to ask your questions when they occur to you. Now, the agenda has shifted around quite a bit since we sent out the initial invitation. So if you have not seen the updated one, look at the web portal for what is current. We've tried to make it as accurate as possible because we realize that given the length of this workshop, some of you might need to drop in and out for other business. Lastly, before we roll the first presentation, I'd like to give a shout out to Heather, Stephen, and Irina, who have worked tirelessly to get the content prepared and the production site ready for you to have a great experience today. We've been working on this program since the summer, and I hope that you find it useful. So with that, let's kick off the workshop and roll the first tape.
Thank you for attending today's workshop. As the title states, we've prepared a highly informative agenda of topics related to HART-IP and Ethernet-APL. If you are a member of FieldComm Group, it's likely that your company makes products for the HART communications protocol. We all know that HART technology is now and will continue to be the leading automation protocol used throughout the process automation industry. Harry Forbes, a well-known analyst from ARC Research, estimates that as of 2018, nearly 50 million HART-enabled instruments are present in the installed base of process automation end-user control systems. Currently, that number surely exceeds 50 million. And furthermore, HART technology continues to be the most often supported protocol in new instrumentation shipments. Oh, and by the way, those instruments shipped this year will still be installed and operational 15 years from now, or longer. Every major control system and asset management system in the market today supports HART communications. Instrument technicians, controls engineers, and plant operators are all familiar with HART technology. The point that I'm making is that HART technology is here today. It will still be here tomorrow, and in fact, it will be supported for decades to come. Now, we can all agree that HART technology is well established and in some senses mature. But HART continues to evolve and change to meet the demands of the process automation industry. As I'm sure you're aware, in 2007, wireless HART was introduced. And then, originally to serve as a high-speed backhaul for HART and wireless HART, HART-IP was specified in 2012. Now in 2022, FieldComm Group is about to release version 7.9 of the HART specifications. A key component of this release is enhanced cybersecurity features, principally focused on HART-IP. Products supporting HART-IP have been in the market for nearly 10 years now. Most of these products are used in automation system infrastructure, products like remote I/O, gateways, multiplexers, etc. And as you'll learn later today, HART-IP is simply HART data packaged in an IP packet. But the use case of HART-IP as only an infrastructure product is about to change. That's because of the other topic that we're going to be discussing today, which is Ethernet-APL, or simply APL. APL is a new standard for 10 megabit communication that uses Ethernet technology or IP technology. What's unique about APL is that it is a two-wire physical layer that also provides power to the instrument and can be installed in hazardous areas. I want to repeat this because it's really a game changer. Ethernet-APL is a two-wire, 10 megabit per second physical layer that includes power and supports intrinsically safe design. At FieldComm Group, we firmly believe that in the coming years, Ethernet-APL-based instruments will be broadly manufactured by suppliers and adopted by end users. And as a result, you as a developer and a member company need to pay attention to this technology and start creating development plans around it. But APL is only a physical layer. An instrument also requires an automation protocol. And again, at FieldComm Group, we believe that for many of the facts already mentioned, HART-IP is the best automation protocol for Ethernet-APL. So the purpose of this workshop is to help our members better understand how to take advantage of the expected adoption of Ethernet-APL through the creation of HART-IP Ethernet-APL enabled instruments. Now let me be clear. The process for creating a HART-IP enabled Ethernet-APL instrument is very different from creating a HART 4 to 20 milliamp device. In the classic 4 to 20 milliamp design, a supplier will select a processor and a modem and likely use an internal embedded developer to create a HART communication stack. Sometime later, an instrument will be created that will be deployed on a HART and only a HART network. In the modern Ethernet-APL HART-IP design process, there are many differences. The processor is more powerful and power consumptive. The communications media is an Ethernet component provided by a supplier like ADI or TI. There is quite a bit of software, much of it is open source, and it's often tied to the selected processor. So familiarity with a component supplier tool chain is highly beneficial to enabling an efficient design. The IP communication stack and HART-IP stack are eventually integrated together as part of the development process. Yes, some of the HART-IP stack comes from HART 4 to 20 milliamp, but not all of it, and new features must be supported. So at the end of the day, a supplier will create an instrument that will be certified for both HART and Ethernet-APL conformance. That instrument will then be deployed on an IP network where devices using many other non-HART protocols will also be installed. Some of you may have the in-house skills required to create this new device. Others will seek out a development partner. Either option works, but please do your homework and understand what's best for your organization. Which leads us to the topic of the day. We've assembled a great program. Wally Pratt, whom we all know as the godfather of HART, will talk about HART-IP. Sean Vincent, who led the Ethernet-APL conformance team, will discuss Ethernet-APL. And numerous development partners, including Analog Devices, emBex, Phoenix Contact, Relcom, Smart Embedded Systems, Softing, and Utthunga, will share their expertise on selected topics and explain their offerings in the Ethernet-APL market space. Today's workshop is split into two parts, a morning session and an afternoon session. Loosely, the morning is somewhat less technical, while the afternoon is more technical. Finally, we've created a microsite full of great content. Heather Wilden will provide more details on the microsite at the end of this workshop. And of course, we are recording this session so that you can view it later. And while much of the content is also pre-recorded, we will break after each segment to handle Q&A.
Hello, I'm Cyrus Kelly, the president of Relcom. I'm going to talk about Ethernet-APL networking basics. Before we get started, I wanted to note one thing. Ethernet-APL is often shortened to just APL. It is much easier to say, and I will do that for the rest of the presentation. The purpose of this presentation is to give you an idea of what you need to know about networking to develop a product compatible with HART-IP and APL. It is assumed that you are already familiar with developing a traditional 4 to 20 milliamp HART device. But to get started on common ground, we will cover traditional HART network architecture. After that, we will look at HART-IP over APL and how its network architecture is different from the traditional HART network architecture. We will talk in detail about the components of an APL network. Along the way, we will cover some networking terms that are good to know when developing HART-IP APL devices. First, let's look at traditional HART network architecture. At the center is a control system with input-output connections. Each I/O connection has its own pair of terminals where a shielded twisted pair of wires is landed. The other end of the wire pair is attached to a HART device in the field that could be 1,500 meters away. A 4 to 20 milliamp analog signal provides power to the instrument and reports the primary variable, such as pressure, temperature, or flow, to the control system. At the same time, the HART digital signal rides on top of the analog signal. A HART multiplexer in the control room area taps into each instrument's cable and is used to communicate with the instruments using HART digital signals. The HART multiplexer is connected to computer workstations, often via RS-485, to support various functions. The HART digital signaling is used by these stations for asset management, maintenance, and diagnostics. So the HART signal is used as a secondary channel for information, not plant operation. The 4 to 20 milliamp signal is used for that. The HART protocol itself is a master device approach. The instruments just respond to commands. However, the instruments can be configured to send data at regular intervals. This is called burst mode. HART communication is simplex, meaning only one device on a cable can talk at a time. HART communications are a very slow 1200 bits per second. Separate from the HART network is an industrial Ethernet network. The control system is attached to the industrial Ethernet network, along with operator stations and support equipment. Connections to the industrial Ethernet network are made using familiar Ethernet cable, for example, Cat5, and Ethernet switches that direct packets of communication to the appropriate destination device or devices. The support equipment provides various services that support Ethernet features. These include DHCP, DNS, and others we will get into later. How does a HART-IP over APL network differ from the traditional HART network? The key thing to understand is that HART-IP just puts HART onto Ethernet. That sounds simple, but it is also hugely powerful. To explain in more detail, let's talk about Ethernet. Ethernet is a standardized set of physical cabling technologies or physical layers. These include coaxial cable, Cat5 cable, and fiber optic cable. But Ethernet also includes a protocol for carrying information between devices on the network. A protocol is just a set of rules and definitions. The rules and definitions include things like what the signals will look like, what the signal is for a digital 1 or 0, and what order information is in. One important fact is that multiple protocols can be used at once. Some protocols are used together to build on each other. Others are independent. Following the protocol rules keeps the communications organized and allows multiple protocols to function at the same time. Using Ethernet means you can connect devices on these different Ethernet physical layers together, and they will be able to pass data between them. APL uses the 10-base T1L physical layer that was added to the IEEE 802.3 Ethernet standard in 2019. So now you can have Ethernet over a single shielded twisted pair of wires that can provide power, go to hazardous areas, and communicate at 10 megabits per second. APL is Ethernet for process control. It allows Ethernet to go all the way to the field devices. So where does the IP in HART-IP come from? It stands for Internet Protocol. IP is a protocol that allows Ethernet networks to be connected together. So you can connect the PC on your home network to Amazon's network to place an order, or connect the PC on your work network to the FieldComm group website to find registered field devices. Now we add HART to IP. HART-IP is another protocol. It uses IP, the Internet Protocol, to allow devices to transmit and receive HART communication packets over Ethernet networks. Keep in mind that HART-IP is totally digital. There is no 4 to 20 milliamp analog signal that represents the process variable. The process variable is sent in a HART packet over Ethernet. Now we can bring it all together. I find the following analogy useful. APL is like a system of roads that lots of vehicles can use. HART-IP is like the trucks that can travel on the road and the traffic rules the trucks obey. The HART-IP trucks carry HART packets anywhere the roads go. How does HART-IP over APL network architecture differ from the traditional HART network architecture? Here's a block diagram of what a HART-IP APL network might look like. The HART-IP architecture is very similar to traditional Ethernet architecture. An infrastructure of switches is used to communicate between the control system and devices, just like in other Ethernet networks. Switches connect all of the devices together and move IP packets to the right place so devices can talk to each other. Notice that this entire architecture is Ethernet. The maintenance, operation, and asset management stations are all connected to the same Ethernet network with no RS-485 involved. In addition, the instruments themselves are connected to the Ethernet with no HART physical layer. The Ethernet architecture makes passing commands and data much easier because the communications use the same foundation, Ethernet. Let's look at the components of an APL network in more detail. We will start at the field level and work our way up to the control room. HART-IP APL instruments are connected to a field switch using shielded twisted pair cable. A field switch is hardware that connects multiple APL field devices to an APL trunk. The trunk is a cable that gets APL back to the control room. Each field switch port that can connect to an APL field device is called a spur. The spur port of the APL field switch provides power for the APL field device and allows it to communicate on the network. Spur cables can be up to 200 meters long. Each APL cable is connected to 2 APL ports. The cable and the 2 devices at each end establish an APL link segment, or link for short. APL is not a bus architecture like Foundation Field Bus that can have multiple devices connected to a single cable. An APL power switch converts industrial Ethernet to APL and feeds power to the field switches it connects to. Power switches are provided with power by external power supplies such as bulk 24-volt DC power supplies. The cable from the power switch to the field switch is called a trunk and can be up to 1,000 meters long. Note the APL power switch is optional. This brings us to a second common architecture for APL. In this architecture, the field switch still provides APL spur ports for connecting APL instruments. However, instead of a trunk port, the field switch has an industrial Ethernet port and connects to a standard Ethernet switch. As a result, the APL field switch must be provided with power. Field switches may support the power switch architecture, the architecture with no power switch, or both. Before going further into APL networking, let's discuss a few definitions that are helpful. A host is an entity that communicates on a network, for example, a field device or control system. An APL switch can be a host too, allowing it to be configured over the Ethernet. A host name is a name that can be used to identify a host. It is the HART process unit tag, followed by a hyphen, followed by the HART long tag. The tags are assigned by the user, just as in HART. HART-IP uses IP addresses. An IP address is a 4-byte number assigned to a host to support data transfer to and from the host over the network. An example IP address would be 192.168.0.101. Next is a subnet. Subnet is short for subnetwork, which is just a portion of a network. The subnet an Ethernet device is on is determined by its IP address and its subnet mask. A subnet mask is another 4-byte number. It is combined with the host's IP address to determine the subnet the host is on. An example subnet mask might be 255.255.255.0. Next is a link. A link is a cable connection between two Ethernet ports. Ethernet devices typically have a link status LED. The link status LED comes on when communication can be established between the two devices on the cable. Now that we have those definitions, we can discuss some common Ethernet features that may also be used on HART-IP APL. These features are called services and are typically provided by one or more hosts on the industrial Ethernet network. HART-IP APL field devices must support these services. The services include the following: a DHCP server. DHCP stands for Dynamic Host Configuration Protocol. It is a host providing a service that automatically assigns IP addresses to other hosts. Hosts need IP addresses to communicate on a network, and this is one way they can get them. IP addresses may also be set to a fixed value. This is called a static IP address. Static IP addresses are typically assigned during initial device configuration, along with the device's tag. Next is a DNS server. DNS stands for Domain Name System. A DNS server is a host providing a service that keeps track of host names of devices on the network. Like an address book, it contains a table of each device name and its IP address to support communication by names instead of IP addresses, which may change. An NTP server. NTP stands for Network Time Protocol. It is a host providing a service to synchronize the date-time clocks of the hosts on the network. This ensures all use the same clock for timestamping and communication. Syslog server. System logging is a protocol allowing HART-IP devices to report events that occur to a host on the network where the events are stored. Events that are reported include things like device startup, firmware upgrade status, session initiated or closed, configuration change, etc. One last set of terms, then we will tie it all together. A router is a hardware device that connects multiple networks together. Routers are used in conjunction with the Internet protocol. Client-server model. This is a relationship between devices in which there is a client, which is a device that wants data or use of a service, for example, the control system or asset management system, and a server, a device that provides data or a service. For example, the DNS server or a field device, which is a HART-IP server. Last is a PHY. A PHY is a chip that acts as a transmitter and receiver on the cable it is attached to. It knows how to turn the data a host wants to send into signals on the cable. It also knows how to convert signals received on the cable to data the host can interpret. If you have designed HART devices before and you want to make HART-IP APL devices, what do you need to know to get started? You can get into more details about how the networking works, but it isn't necessary to get started. Ethernet does get complicated, but the details have been figured out already, and code is typically written to handle those details. This code is called middleware. The microprocessor in your device runs a real-time operating system, or RTOS. When you make the code for the microprocessor, you include the middleware you need to support the HART-IP features like Internet Protocol, DHCP, DNS, and NTP. You need to make sure the microprocessor you choose for your product supports an RTOS and the middleware you need. In other words, you don't need to reinvent the wheel. You do have to know enough about Ethernet and the networking features required for HART-IP APL to be able to integrate the middleware into your code. Also note that you still need a HART stack. You will just be putting the HART packets into Ethernet. You will have to write code to bring the HART stack and Ethernet features together. That's where a basic understanding of Ethernet networking comes in. In conclusion, we covered a lot of networking concepts at a high level, but that gets you a long way toward developing a HART-IP APL device, especially if you have already done a HART device before. Because APL is Ethernet, you can use existing libraries of middleware code to support the required features. Here's my contact information in case you have questions. Thanks for watching.
Hello, I'm Wally Pratt, Chief Technologist for HART at the FieldComm Group, and architect of the HART protocol for over 20 years. Thank you for joining me in this introduction to HART-IP. While HART-IP is relatively simple, there is also quite a rich set of features. HART-IP does everything an HART 420 milliamp device does, plus more, without the analog signal, of course. So we'll start to talk with a review of those features and talk a bit about smart data publishing. From there, we have an overview of HART-IP security that is provided. Ethernet-APL is touched on briefly. Then we will close by discussing what it takes to deploy HART-IP devices and networks. Now for an overview of HART-IP features. First, let's take a moment to talk about HART in more general terms. HART is really about field communications, and we support a number of different technologies. The HART 420 milliamp current loop, of course, wireless HART, and HART-IP, but they all use the same application layer. Each of them use the same tools in the same paradigm. So if you're used to using a HART 420 milliamp device, the kinds of things you do there are pretty much the same. You can go about doing them no matter what the communication technology. It's this commonality of paradigms and application layers that are really central to what makes HART so powerful. HART-IP puts a thin wrapper around the existing HART communication and then layers it on top of the Internet protocol. Since it's the same application layer, it's pretty easy to pick up an existing IP stack and start doing HART-IP. For hosts, HART-IP adoption is very straightforward. Many hosts permeate the HART data throughout their systems, already do. And so, with a simple interface, the HART-IP data gets in the host and the HART data then flows through the entire system. There are lots of advantages of working on top of the Internet protocol, not the least of which is it'll work on any physical layer in the world, whether it's Ethernet or Wi-Fi or 5G cellular and so forth. For controllers and other clients, Ethernet-APL is also simple to accommodate, either via a native controller interface or via APL power switch over existing gigabit Ethernet. HART-IP serves to provide a high bandwidth connection between clients, data consumers, and servers, the data producers. Clients are the typical applications you find in process automation, monitoring optimization, process controllers, asset management, and what have you. The servers are essentially the process interface, and they are designed to push the process data to the clients. Communication is session-oriented. In other words, the client has got to open a session, and then all the communication with the server occurs during that session. Backward compatibility and interoperability are core principles of the HART protocol. And as we improve HART-IP to standardize security, we followed those rules. That means a version 1 and version 2 clients will interoperate with version 1 and version 2 servers. It's what we expect from HART. Security is essential, so version 2 servers will only communicate securely. Backward compatible operation is determined when the session is started. If you notice the first exchange is called Session Initiate. And it's done the same whether it's a version 1 or a version 2 client and server. During this, we negotiate which version of HART-IP protocol both sides are going to support. If both sides say they're version 2, then we launch standard TLS, DTLS security initialization. This is when we establish trust and exchange the keys that are going to be used for secure communication. From then on, all communication is encrypted, and the keys that are exchanged are used for that secure communication. HART-IP specifications identify 4 types of servers: wireless HART gateways, 4 to 20 milliamp remote I/O, native HART-IP instruments, and HART-IP adapters. HART-IP 4 to 20 milliamp remote I/O is the next evolution up from the old RS-485 multiplexers. Unlike the multiplexer, which depends on device-specific commands for operation, HART-IP I/O communications is standardized. 4 to 20 milliamp I/O and wireless HART gateways use the same procedures and commands for accessing their subdevices. Native HART-IP instruments also offer many benefits. For example, HART-IP allows valve signatures, radar level echo curves, vibration spectra to be uploaded in seconds rather than dozens of minutes. HART-IP enables faster and smarter communication. And finally, HART-IP adapters are specified to enable access to stranded instrumentation. Many plants now have Wi-Fi infrastructure, and the HART-IP adapters adopt the persona of the connected 4 to 20 milliamp device, enabling access seamlessly via HART-IP. HART-IP, like all HART networks, supports 2 communication modes: request response and publish by exceptions. Request response supports acyclic communications like those typically used by asset management systems. Publish subscribe pushes process and status data directly to the consuming clients. This is the preferred communication pattern for control systems, data historians, and more. All HART-IP servers must support both request response and publish subscribe. Since HART-IP is fundamentally HART, all the device integration techniques used with a 4 to 20 milliamp HART can be used with HART-IP as well. In FDI-enabled systems, HART-IP servers use the same device packages in use now for several years. HART-IP is transparent. The only noticeable difference is it's fast. The same is true for mobile workers using, for example, tablets. Since HART-IP enables wide area communication over the ubiquitous IP networks, integration with edge gateways is even easier than with HART 4 to 20 milliamp. The needed communication and connectivity is fundamental to HART-IP devices. Integration can be further enhanced using HART device info technology. Using device info, the edge gateway convert binary HART communication directly into JSON or XML structures used in operational technology. HART-IP security was designed to be relatively simple but also scalable. It's designed to support air-gapped networks because that's what you see in most process automation plants. Initial provisioning builds upon the experience with wireless HART in that only a single set of parameters must be entered before you can securely deploy the device. Robust security is essential and layered defense was designed. HART-IP security rests on 3 major elements. The first, communication security, is based upon the industry standard TLS and DTLS. User credentials are used during the initial security negotiation to establish trust. By that, we mean, do you really believe you're talking to who they say they are? HART-IP provides a minimum of 5 sets of user credentials. We also use the concept of a security manager for wireless HART. For HART-IP, the security manager is the first user, if you will. Only the security manager, that first user, can change security credentials. To enhance the preventive security used in communications, 2 detection strategies are employed: audit logs and syslogs. Audit logs are communication and event summaries stored locally and always available. In addition, syslogging publishes individual events to a central syslog server or repository. Events are like changes to security credentials or clients connecting to the device. In addition, field upgrades are mandatory. This allows for upgrades to cipher suites and to address any security vulnerables that might occur over time. Bear in mind, HART-IP is a tool and is designed to complement your overall plant security strategy. We designed HART-IP for simple deployment. For new devices, the initial provisioning follows the same paradigms you see with HART devices or with wireless HART devices. Take it out of the box, connect it to a client application, provision with a minimal set of parameters. To simplify the initial connection, new devices have default IP addresses and host names, so you don't have to go do anything special to get started. There are also default one-time security credentials used to ensure the initial provisioning is confidential. During this initial provisioning, you have to provision at least one set of user credentials, and that's the ones we call the security manager. In addition, you can enter tags for the device just like you do any other HART device, and you can provision whatever else you want on the bench. When you're done, the device is ready to deploy to the plant network. I'm sure nobody in the audience has ever forgotten their passwords. Well, I have. Probably just a personal problem, I guess. But in the discussions about HART-IP, we decided that we needed a way to get a do-over, a way to reset everything so we can get started all over again. So there's a factory reset that's required to be supported by all HART-IP devices. This is essentially a hardware jumper or switch that has to be asserted when you cycle power. So this will cause everything to be set back to the factory original conditions. This allows you to start over the provisioning and get your device back online. This is an important element that allows you to recover in case, something bad happens. Safe HART can be included in HART-IP devices as well. When it is, HART-IP servers can be used as part of the plant's safety function. Safe HART works on all HART communication and will successfully tunnel through unmodified remote I/O and wireless HART gateways. And of course, safe communication can be freely mixed with normal communication with no negative consequences. Safe HART is accomplished through the addition of a CRC and a sequence number to the end of the commands. Safe HART ensures communication has a probability of failure per hour that is much less than 10 to the -9th. Another feature that can be included in HART-IP devices is a digital write protect. Historically, write protect has relied on physical jumper on the device. Pretty awkward because then you have to go to the device. HART now has a secure means to assert that write protect jumper via communications. Digital write protect is conceptually based upon the lockout tagout practices. In this case, a lock is attached to the device that secures it into write protect. That lock has two elements, a combination that is at least 8 characters long and a username. Like with lockout tagout, you can see who locked the device, but only that user should have the combination. Of course, the user should be a person or a role or whatever plant policy is. Also, like lockout tagout, there's a way to cut the locks. Doing so is relatively painful, requires 2 people, and physical access to the device. Digital write protect is a really nice feature of the HART protocol. HART Smart Data Publishing is a smarter version of Publish Subscribe. To be clear, HART has supported publishing of process data since 1990. However, for the last 15 years or so, the HART Technology Working Group has been focused on publish by exception, making Publish Subscribe smarter. As a result, today, the process engineer can configure how often the data must be published, what triggers, and which data, process, or status is published. The windowed Smart Data Publishing is shown here. Basically, the process data is published at a fixed rate except when the process is changing quickly. In that case, the data is published more frequently. In other words, when the process is stable, there's less information, so you can publish more slowly. The figure depicts level-triggered operation. In this trigger mode, the process data is sent more leisurely when the measurement is below a set point, then speeds up when the set point is crossed. To be clear, Publish by accepting provides a lot of benefits. Examples include one packet or measurement can be generated and sent to everybody. Smart data publishing only uses the network when it needs it. And in the case of wireless HART, it optimizes battery life. Publish subscribe also means client don't have to poll the device over and over and over again, often getting the same values for long periods of time. Smart data publishing is an optimal and elegant solution for process and status data communications. Of course, one of the big benefits to smart data publishing is the process engineer can choose how often to publish based upon the process to be measured or controlled. This table lists typical process characteristics. The main point is some processes are very fast that need 20 updates per second, but there are many that need less. In fact, temperature monitoring is often among the slowest, needing maybe 15-second updates or less. The process time constants don't change, so this is a one-time configuration. Configure it one time and you're done. One underlying principle here is coexistence. The HART community thinks this is a really big deal. Coexistence means you work hard, get the job done, but then be a good neighbor when you're doing it. Now we take a deeper look into HART-IP security. The HART-IP security relies on defense in depth, and this three-legged stool is a good way to remember HART-IP security. The three principles of communication, forensics, and diagnostics make HART-IP security robust. Strategies supporting both prevention and detection make HART-IP security resilient. The first leg is prevention, preventing unauthorized access to your data. For this, communication security relies on proven industry standard TLS and DTLS. To this, HART-IP provides infrastructure to make that successful. That infrastructure includes things like user credentials, options like read-only users. We also specify how to bootstrap security when introducing new devices to the network. User credentials are used during session initiate, where the initial security negotiation establishes trust. This confirms the server can be trusted by the client, and in turn, the server can trust the client as well. HART-IP provides a minimum of 5 sets of user credentials. They consist of a user ID, options, and then either or both of a pre-shared key or password. The user ID can be a person, can be a role, whatever. In other words, the user credentials are utilized in the way the plant policies dictate. One of the kind of cool things we added when we did communication security is read-only operation. This allows us to kind of follow that data diode metaphor where a particular user can only read things. I mean, there's still request and response commands that go back and forth, or it can be publish, subscribe. In any case, no writes are allowed. You can't change the configuration, and of course, it works not only with HART-IP field devices, but I/O systems and wireless HART gateways. And since I/O systems know which commands are read commands from the HART protocol specs, they can enforce read-only on the 4 to 20 milliamp devices or the wireless HART devices that are connected to it. Now for the first of 2 detection strategies. Since no one likes being caught, the HART-IP detection features enhanced security through deterrence. The concept of a syslog has been around since the 1980s, and so it's really well established. Syslog provides a system-wide focus. In other words, it's kind of the forest view of what's going on in your plant. The way syslogs work is timestamped events are published from all the network devices. These are received by the syslog server, basically a database that collects the events. And it allows you to untangle things like plant trips or security events or any number of things. The HART-IP events published are diverse, including things like when the server powered up, when somebody changes security credentials, whenever a session is open or closed, or whenever a configuration parameter changes. If the event is triggered by a client, then the IP of that client is also included. This way you know who did it and when. To make it easy to search and sort the events, we follow the Micro Focus common event format. This is really powerful stuff, but of course, there has to be a syslog server actually on the network. Audit logs are the second detection deterrence feature. Audit logs focus on one leaf, a field device or an I/O within the network. Audit logs provide summaries of client interaction with that device. They consist of a header which summarizes the general health of the device, then client records summarizing each session that has been connected to over time by the clients. The audit logs are volatile, which means you lose them on power cycle. But that's okay because you know when somebody powered it back up too. But the other really big benefit is that audit logs are always available. Even when the optional syslogger is not there, you can still have the diagnostics that allow you to figure out what's going on. In the top of the screenshot, you can see the general information about the device, like when it was powered up and when the security was changed. Below that is a series of records for each client that talk to the device. For example, when the client opened and closed the session. Particularly interesting is the session status summary that will tell you things like whether or not that client has changed the configuration of the device. So really powerful stuff. This slide shows a typical plant security lifecycle and HART-IP's role in each one of these. Procurement we're going to skip over because it's kind of out of scope. Provisioning is about getting your user credentials securely and safely into the field device. Installation, you follow your normal practices. However, you might consider changing the user credentials as an extra security step during installation. During operation, you're going to monitor the integrity of the device. That includes configuration change counters, device status. You should periodically look at audit logs. If you see any anomalies, then you should investigate. Periodically, you should change the security credentials as well. Maintenance is usual plant practice. However, you must also consider whether firmware upgrades are going to be needed during the maintenance cycle. For example, because of security vulnerabilities or a new cipher suite. Replacement, it's sort of like going back and starting all over again with provisioning, getting those credentials in there, and then configuring the device. Disposal is a little bit special because you need to evaluate your security exposure, perhaps do a factory reset or maybe even destroy the non-volatile memory of the device. Because people do dumpster diving and there are other best practices, recording device configuration, change management, and protecting your security credentials, access, and so forth that's important. Bottom line, you should think and act security through the entire normal plant life cycle. Let's briefly discuss the emerging Ethernet-APL and how it complements HART-IP products. The main thing to remember is Ethernet-APL is Ethernet. It's the same packets, the same addressing, the same bus arbitration. It's just like any other Ethernet physical layer. You can also mix and match whatever protocols and applications you want on the same network. The big difference from, for example, gigabit Ethernet is that Ethernet-APL PHY is designed for automation, both factory and process automation networks. That means there's a single twisted pair that carries both communications and power. Of course, Ethernet-APL also supports intrinsically safe operations found in all process plants. Like twisted Ethernet topologies, Ethernet-APL consists of switches that connect the devices to the network. In APL's case, there are two main switch types: the power switch, which is kind of a gateway actually, and then the field switches. HART technology is generally designed to work for the hardest problem, worst environment. The result is great reliability, ease of use, and flexibility. Assessing HART-IP over Ethernet-APL, it is clear process control is a great fit for this pairing. HART-IP is tailored to process automation. Publishing at 20 updates per second and timestamping the process value provide controllers with solid information to make control decisions. Looking at Ethernet-APL performance of 10 megabits per second, HART-IP, providing 20 process values per second, uses a tiny fraction of the available bandwidth. I've been doing real-time control for over 40 years. Cutting through all the hype, real-time simply means you're doing it fast enough. On the example network of 10 HART-IP devices, only 2% of the bandwidth is used for HART-IP. This light footprint ensures both reliability and coexistence. There's lots of excess capacity for retries, for asynchronous communications like asset management, and ensuring the network meets your needs. Finally, we look at what operational HART-IP networks really are. What are the typical actors in these networks? Let's look at a simple HART-IP network. It contains everything needed to deploy a serious application solution. First off, this example is an air-gapped network. We have a HART-IP host application, the client, a field device, which is a HART-IP server, and if it's Ethernet-APL device, then there'll be Ethernet-APL power switches. In addition, there's a lightweight set of network services the field device uses when it powers up. The HART-IP device will get its IP address through DHCP and register its host name with the domain name services. The host application knows the device is tagged because tags are on the PNID drawings. They're everywhere. So the host looks the tag up on the domain name services and gets the IP address and then opens a session to the HART-IP device. These are all very simple operations with very little extra network services. In fact, we run these network services on a Raspberry Pi in our test labs. The concept of tag is immersed in the process automation industry. It's everywhere. Tags are used in controllers and data historians, and there are tags in the field devices since 1990. When developing HART-IP, we decided to fully embrace the tag. As a result, we set the host name for the HART-IP device to be the tag, and then we register that tag with the domain name services. Now, any of the process automation just uses a tag to connect to the field device. Very logical. But we do know that sometimes there are multiple process units that have identical, even down to the tags. So we have a separate data item called the process unit tag that, if you enter it, it gets concatenated with a device tag. And that's what gets put in the domain name services. That way, the host names remain unique. So, at the end of the day, it all comes down to is if you know the tag, you can connect to the device and you're in business. A critical part of deploying HART-IP network is deploying the HART-IP devices themselves while maintaining security. So one of the kind of tricky things is how do you get started with that communications and do it in a secure way? What are those first steps? Here's a screenshot from the portable HART-IP client that illustrates those simple steps to deploying HART-IP devices. Specifically, this wizard guides you through the initial provisioning. You can see there are places for entering the initial security configuration, the host name, which is the tag and process unit tag, and the details about the syslog server, if there is one. Bear in mind that this was designed to be performed on an instrument workbench by a technician. With one client, the HART-IP device, nothing else, well, aside from wiring. That means that nobody is there to see what you're doing with the security credentials or what they are. With this little bit of work, you're ready to deploy the new HART-IP device to the field. Wait a minute, it gets even easier to deploy a new HART-IP device. HART-IP allows you to simplify your network deployment even more using zero config technology. This means you can take your clients, edge gateways, controllers, what have you, your HART-IP devices, the network stuff like switches and wiring, and your network can start right up. IT stuff like DHCP and DNS are not even required, totally air-gapped. When HART-IP devices power up, they use MDNS to find their own unique address. The clients do the same thing. Using MDNS, the device can confirm all their tags and host names are unique. Now let's look at the second part, which is DNS service discovery. HART-IP itself is what the internet calls a service. That means, for example, a client can ask the network for all the HART-IP devices to make themselves known to the client. They all answer and the client knows. This results in the client having a list of all the HART-IP devices, their tags, their IP addresses, right there in the controller. Both MDNS and DNS are internet standards, but there's more. HART-IP standardizes the descriptions that devices can return with DNS-SD. For example, HART-IP tells the client the manufacturer, device type, and the revision of the device. It also tells the client what kind of device it is, like pressure or temperature, Coriolis flow or whatever. The bottom line here is HART continues to look for ways to make it easier on the end users. Actually, I think this is another really cool HART-IP thing. So in summary, we've discussed a broad overview of HART-IP. There are a few things I want you to remember. With HART-IP, it's relatively easy to deploy a secure network. HART-IP works well with air-gapped networks, but is also scalable to unit, plant, or even enterprise-wide deployments. Provisioning a new device is simple and can be done by an instrument technician on the workbench with no special network gear. Continuous polling of devices are not required. Smart data publishing allows HART-IP devices to push process and status data to multiple clients either cyclically or upon exception. With Ethernet-APL, HART-IP is control ready and uses a small fraction of the available communication bandwidth. The optional SafeHART enables integration of HART-IP devices into safety functions. It's all HART. Your team follows the same paradigm and practices used with HART 4 to 20 milliamp or wireless HART devices.
Hello, and welcome to this introduction to Ethernet-APL. We will cover the background, the key technical features, conformance, and guidance on design and preparing products that support Ethernet-APL technology. My name is Vincent. You may know me from my work with the FieldComm group, but I also serve as the chair of conformance for the Ethernet-APL project. Ethernet-APL is a physical layer and therefore supports a number of protocols. In the context of FieldComm group, we'll focus on HART-IP. Ethernet-APL is a two-wire, intrinsically safe Ethernet specifically designed for process automation. Ethernet-APL is the first time we've enabled capital E Ethernet to a field device network with complete support for intrinsic safety, power, and data sharing the same two wires. Ethernet-APL also presents an opportunity for re-architecting products. Since the physical layer applies to multiple protocols, there's an opportunity for companies to create a platform to enhance features and to offer new products based on this exciting technology. There are several misconceptions about Ethernet-APL. First, it is not a protocol. Protocols such as HART-IP are supported by Ethernet-APL physical layer, but Ethernet-APL is IEEE 802.3 and therefore supports any Ethernet-based protocol. There is an opportunity for cable reuse as long as the cable meets very specific requirements set forth in the Ethernet-APL specifications. Cables such as those used with Foundation Fieldbus, known as Type A Fieldbus cable, can be reused as long as the specific cables installed are within the specifications of Ethernet-APL. Keep in mind that cables in some locations may not be compatible with APL. The requirements for Ethernet-APL cable are clearly defined. If a cable is measured and tested to meet those requirements, then it will support Ethernet-APL. Ethernet-APL is part of a larger group of specifications known as single-pair Ethernet. This can include POODLE, Power over Data Line, and SPOE, as well as other non-intrinsically safe Ethernet physical layers. All Ethernet physical layers, including traditional 8-wire, 4-wire PoE, POODLE, SPOE, etc., support HART-IP. Ethernet-APL is one of many solutions for HART-IP. HART-IP is the best solution for Ethernet-based products. Products and the desire for Ethernet-APL can be summarized by speed and bandwidth. A HART-IP Ethernet-APL network with 117 devices can update at 25 updates per second. This is with minimal optimization and no scheduling or significant oversight. Speed of these updates provides unparalleled access to the HART data model. This allows existing HART systems, asset management tools, to receive HART data that is consistent with the data received from previous HART products, but at a higher frequency, higher speed, without latency. This enables the usage of known tools, known work practices, and maintains the historical records for products in plants and facilities. Ethernet-APL provides unrestricted access to all HART data, enabling efficient upload, download to multiple devices without delay. HART-IP enables support for all types of Ethernet products. The HART-IP project group conducted a detailed assessment and study of the speed and bandwidth advantages of HART-IP. This is available in the workspace. Ethernet-APL specifies power up to 92 watts for the trunk, and field devices and intrinsically safe applications that are limited to 0.54 watts due to the hazardous atmosphere. APL is a switched Ethernet network, which enables the common model of a single field device on a single port of a switch. This is the common model we see in other Ethernet applications. The defined networks allow copper cables to support 1,000 meter trunk and an additional 200 meters for each spur. If we're using fiber for the trunk, each trunk could be up to 2,000 meters. We typically speak of the 1,000 meter trunk with 200 meter spurs. The field network runs at 10 megabit per second, but remember, once you move above the field, the switches provide a connection to the plant and control networks, which could be 1 gig Ethernet or other options. The core of the two-wire intrinsically safe Ethernet is similar to the field bus intrinsically safe concept, or FISCO. It is a system model. Ethernet-APL specifications include IEEE 802.3cg from 2019, which will become simply IEEE 802.3 very soon based on the IEEE naming policies. The intrinsic safety aspects are included in the larger intrinsic safety specifications. The IEC 60079-47 defines two-wire intrinsically safe Ethernet. The IEC 63444 defines the port profiles, which include the power, signaling, core information, and connectors for APL products. EMC test requirements are specified in the IEC 61326. There are many EMC requirements that products must meet for various industries and applications. For Ethernet-APL, there are additional specific tests and configurations that must be tested for all Ethernet-APL products, regardless of target industry or application. Cables are defined in the IEC 61158-2 specification, and these are known as Fieldbus Type A cables. IEC 61156-13 provides specific single-pair Ethernet cable installation length and transmission rates. In other words, it is possible for different cables to meet APL requirements at different lengths of service. It is useful to understand some terms. Advanced physical layer is derived from single-pair Ethernet. The IEEE defines the encoding and signals as well as the basic structure of the packet. This is where we get single-pair Ethernet. Ethernet-APL is a specific single-pair Ethernet that supports intrinsic safety, topologies familiar to process automation, with power sufficient to handle the common applications and products. We also have distinct EMC requirements based on the real-world conditions of the process installation. An Ethernet-APL field device is a product, whether it's a valve positioner, level, flow, pressure, temperature, or any other type of transmitter that supports Ethernet-APL and HART-IP. The Ethernet-APL specifications define requirements that can be met by a variety of cables. Specifications also define 3 types of connectors, including the pinouts for APL. We often talk about Fieldbus Type A cable because this is the cable we are familiar with in foundation Fieldbus installations and other Fieldbus networks. The APL specifications do not require a specific cable, but instead provide the characteristics that the network must meet. We'll see that different cable types at different lengths can achieve these characteristics. All Ethernet-APL cable is targeted to shielded twisted pair. It is unlikely that a HART 420 mA transmitter cable will meet the requirements to reach 1,000 meters. But as we will see, there are varying distances achievable depending on the specific characteristics of the cable. APL cable is a balanced, shielded, twisted pair cable with characteristic impedance in the range of 100 ohms plus or minus 20% in the frequency range of 100 kilohertz to 20 megahertz. This is measured according to the International Telecommunication Standards in wiring testing, for example, the ASTM D4566-05, or other equivalent standards. These are cables typically used for foundation field bus H1. Wire diameters can be in the range of 26 gauge to 14 gauge, either with solid or stranded wires. We can divide cables into 4 cable categories defined in the APL specifications. The categories limit the maximum cable length due to characteristics. Categories allow the use of higher insertion loss cables, which can only support a lower maximum APL segment length, while still fulfilling all the requirements of the network. Remember, APL segments are powered, so the voltage drop over the cable distance must be taken into account to determine the maximum length that that cable can support. For example, if we have a 16 gauge cable, we run 1,000 meters, then connect to a switch, then run another 1,000 meters and connect to a switch. And each of these switches supports 2 field devices that are on 200 meter spurs each. However, if we change the wiring to 14 gauge wire, then we can increase to 3 devices per switch. The 2Y specification lists the overall inductance and capacitance of the network, which cables must be factored into, in addition to the switches, devices, and other components. All network requirements are specified so installers and users can calculate the specific layout of a network and determine how many devices an existing cable installation can support. Topologies of the network for the APL systems are designed to meet the needs of different installation applications. The structure of the overall plant control network is a higher layer than what we will discuss today. The APL network includes switches that connect to the upper layer, or they connect directly to a control system. We'll focus on the field network side. Remember, the plant, control, or industrial Ethernet networks need to be routed to the locations where the APL power or field switches are located. Remote I/O or controller that supports APL could also be available for the field connection. APL differentiates between trunks and spurs. The features can be described as follows. A trunk is the main line of the APL network. It connects the APL power switch with the APL field switches and APL field switches with one another. The length of the trunk segments can be 1,000 meters each. Maximum overall length of a trunk can be calculated. This is a powered trunk. A spur cable connects to the field device from the switch. So a single port of a field switch connects to a single field device. The length of a spur cable must be 200 meters or less. Recall the cable categories. The combined use of trunks and spurs is shown in star topology. The star topology is compatible with existing field bus installations, the FF topology, the HART remote I/O, and multiplexer architectures. Trunks and spurs have a source, power, and a load. The load could be a port on a switch, in which case it would be a trunk load, or it could be a port on a field device. In that case, it's a spur load. The source and the load includes all port profile power classes. These are all defined in the Ethernet-APL port profile specification. Field bus applications are typically made up of more complex multi-point connections, field bus power supply and multiple devices, than your traditional analog point-to-point signals. The traditional intrinsically safe entity calculations are very cumbersome with multi-point connections. FieldComm was developed many years ago to overcome those challenges of multi-point systems. This is what we inherit today through the 2Ys, 2-wire intrinsically safe Ethernet. The segment class determines signaling type, 1 volt for spurs and 2.4 volts for trunks. Segment class also determines the maximum possible length on the supported cables. Note that inserting inline auxiliary products, such as lightning arresters, etc., will impact the overall network due to the voltage drops. Also, these products must not interfere with the signaling for Ethernet-APL products. The port class defines the direction of the power. The electrical characteristics of all ports are captured in the power classes. A power source port, P, typically found on switches, both power switches and field switches. The power load, L, are typically found on the field devices. A cascade port is also defined. These are found on switches and allow multiple switches to be linked together. Ports are characterized by their power class. Power class A and C are primarily intended to be used for devices in the field. These would be spur ports. These power classes include coverage of power classes that support hazardous areas. These applications could also support non-intrinsically safe ports and applications. The IEC 60079 defines the system parameters. The overall 2-wise system is defined by overall power source, overall power load, cable, and other inline elements. For example, SLAA, so a spur load, power class A, and protection class A, with 15 volts and 0.54 watts is one component of the larger system. The SLAA is a spur load, and this is commonly what we would find in a field device profile. The definition for source and power in the IEC 60079 allows designers to build systems made up of components, including the SLAA field devices. There's provision for 1.1 watt field devices as well. Trunks can be either 57.5 or 92 watts depending on application and equipment. These are the current port definitions for APL. It is possible that future developments and specifications will add to this list. HART started with FSK, then added PSK, and wireless HART. Now we add support for Ethernet-APL, which is a digital modulation known as PAM3. The actual signal in the cable will be a 4-binary 3-ternary or 4B3T encoding using the PAM3 or pulse amplitude modulation. There are numerous requirements for the physical layer signaling. There are 2 amplitudes for the signals, the 2.4 volt peak-to-peak for the trunk and the 1 volt peak-to-peak for the spur. Commercially available PHYs are responsible for the transmission and reception of the Ethernet frames. Compliance testing assesses the signal encoding, power, and other requirements. Keep in mind that high temperatures will challenge device designers with the current draw. Also, low temperatures will challenge for noise and transmit distortion. There are several commercial 10BASE-T1L5 vendors in the market, for example, Texas Instruments and Analog Devices. These vendors handle the PHY and even up to the MAC layer for you. Intrinsic safety protection adds another layer as well. Good to understand the requirements, but rest assured there are companies that offer assistance. Now let's take a functional view of the Ethernet-APL field device. There are numerous models and layers that can describe communications and designs of field devices. In this presentation, we show the Ethernet-APL physical connection to the network, including the intrinsically safe protection. This is then layered with the Ethernet-APL PHY, which handles the 10BASE-T1L for both the PHY and the MAC. We then add the HART-IP communication stack, which handles all the formation of the content of the encoded Ethernet packets. Our existing HART application can be reused because HART-IP is an extension of HART. All existing HART data model, including, for example, Command 0, Command 48, can all be reused with the HART-IP implementation. In addition, the device functionality in support of the sensors continues in a similar implementation to what we use today. We still need to measure the physical process. We're not changing the laws of thermodynamics with this new physical layer. We will continue to sense or measure from the process, create a measurement, then communicate that measurement to the system. We'll also continue to receive a set point from the control system and adjust the valve position to meet the desired outcome. Quite simply, the HART control loops continue, but at the speed of Ethernet, which gives us an immense advantage. All current types of HART measurement and control products will continue to be needed, and these are supported within HART-IP and Ethernet-APL. Ethernet-APL is based on the IEEE 802.3 CG from 2019. In accordance with the rules of the IEEE, this specification will simply be known as IEEE 802.3 moving forward. Ethernet-APL is a profile which includes power, connections, specific signaling, and conformance. Requirements of an Ethernet-APL product are available from the FieldComm group, as well as in the emerging IEC 63444 port profile specification. Ethernet-APL cable is defined in the IEC 61158-2 and the IEC 61156-13, which, keep in mind, not all cable that supports APL or single-pair Ethernet will support the requirements for long-reaching, intrinsically safe networks. Developers, installers, and users all benefit from reviewing the engineering guide, which walks through the practical design of networks and takes into account the requirements when looking at how to build out the different topologies to meet the needs of process applications. Ethernet-APL has very specific requirements for testing. These include EMC, which is captured in the IEC 61326, the two-wire intrinsically safe Ethernet, otherwise known as 2Ys, which is captured in the IEC 60079-47. The EMC and intrinsic safety elements of a product are confirmed and tested by vendors and test houses in accordance with international standards and government requirements. The data test specification confirms the operation of the Ethernet PHY in conjunction with the intrinsic safety protection front end. The goal is to ensure that Ethernet-APL products work in an interoperable manner. The power test specification confirms the power requirements specified in the Ethernet-APL port profile spec. Power tests also ensure devices are robust in handling noise and ripple on the single shared power data lines. We'll discuss more about conformance and testing later in this workshop. Thank you, and as always, if you have additional questions, feel free to reach out to the FieldComm Group staff or via the support portal.
Okay. Hopefully you can all hear me. We're gonna go through some questions that we've had during the past few videos. Hopefully this will answer some. If you have any other questions, please feel free to post them while we move on. The way that I'm going to do this is I'm going to ask a question. I'm going to ask a specific person to answer it, and then if you guys want to chime in with anything else, please go ahead. So. First question is a real softball question. It's going to go to Wally. The question is, where can I find the HART-IP security specifications?
The HART-IP security specifications are in the network management spec.
And where would you find that?
Well, they're part of the protocol specs that all member companies get.
Okay, so it's on Workspace or somewhere?
It's on Workspace, but it's also published by FieldComm Group to our members.
And don't we have a specification out for ballot right now?
Yeah, you have an out for ballot. That is balloting Safe HART.
Mm-hmm.
It has some improvements to add MDNS and DNS SD,
mm-hmm.
But that really doesn't affect the security.
Yeah, but if they're looking at that spec that's being validated, is that part of what they would be? Could they reference it there?
Absolutely, it's there too.
Okay,
it's just not changed with that ballot.
Yeah. Okay. Thanks. I just want to know if I'm trying to come up with the easiest way for them to find what they're asking for. All right, got it. Thought that was a softball. Okay. Here's another one for you, Wally, since I got you going here. So the question is factory reset and break the right lock. Is it allowed to implement this over NFC instead of a physical button? Ingress protection IP68 is harder with a physical button. Hopefully that makes sense.
I know that's why we didn't say physical button. We said a physical means. NFC could substitute for that. You have to remember that the factory reset includes cycling power on the device, and when NFC starts working again during the cycling of the power of the device is not immediately obvious to me.
Mm-hmm.
Okay. The cutting of the locks is a little bit different. It requires a command to be sent remotely to the device while the cut right lock feature is asserted. And so the near field communications is not exactly the same button because it'll be, independent commands. So somehow you have to maybe you enable it with C and then send the command to cut the locks or some combination. So definitely worth looking into.
Got it. Okay, great. Thank you. So question for Cyrus here. The question is, how is configuring my HART test network for APL different from Ethernet? Hopefully you understand that question.
Yeah, okay. I would assume that they're talking about having a HART test system and wanting to use that to test a Ethernet-APL based HART-IP product. So actually Relcom developed a product to help with that, because what you need is something that's going to convert from your standard Ethernet over to APL so that you can hook up your device, and the device will need power. So we made up a product called the A111 Ethernet-APL adapter to support that just for a single device. You could also use a field switch, or if you needed to, also with the field switch, use a power switch, and you can just use the field switch to convert from the standard Ethernet over to APL. So those are two options.
Okay.
As far as getting your test system set up.
I think that you also talk more about the A111 in one of your profile videos later on during this session, I believe. Is that correct?
Yeah, that's correct. Yeah, you can also go to relcominc.com, and there's a webpage for our APL products there. Okay,
excellent. Well, okay, so stay tuned, all of you, and take a look at that. Sean or Wally, do you want to elaborate at all on this answer? So the question again is how is configuring my HART test network for APL different from Ethernet?
Yeah, the quick answer is that you use the HART test system, and the HART test system contains all the services that you need for supporting the HART-IP product. It includes the test cases, of course, but it also includes the Ethernet services that are required for testing. Mm-hmm. And in the conformance section, we'll go through that in more detail.
Okay. Sounds good.
So stand by for that.
All right. While I've got you, while you're talking, Sean, I'm gonna read this question. It's the most complicated one that I think we've gotten so far, and it came in very early. So hopefully you've had some time to think about it. So the question reads as follows: APL test spec for data and power shows several test setup examples. One of them shows a theoretical setup with software controlling the test equipment and device under test to automate the testing as much as possible. I think that's what DUT stands for. Are there currently any solutions for this?
Yes. And again, we'll talk about that in the conformance section, but there are tools from the University of New Hampshire, as well as a company called Telebyte, that offer automation around these tests, but also a company could develop a test platform that could be done with their own equipment and discrete components that are in our equipment list to build up such a test system. Part of that software is that you need to be able to generate specific frames, specific packets to get specific responses or no responses. And so the creation of those packets requires an arbitrary waveform generator. And of course, to drive an arbitrary waveform generator, generally it's a lot easier if you use software than trying to create that in other fashions.
So is it our intention at FieldComm Group to eventually be able to offer this type of setup?
We do not have any plan currently to sell a specific test kit. Instead, we are working with other companies' commercial products that offer it. Also, we are working closely with the vendors of scopes and some of the other test tools that they are adding the 10-base T1L testing to their tooling, as well as extending it specifically for Ethernet-APL.
So this question refers more to a product under development as opposed to a conformance testing type of situation.
Well, for conformance testing, we will have a specific set of equipment to perform the test as described.
Got it.
As a
Okay.
developer, you will need to run the same tests before you send in the product. And to do that, you'll have several options.
Okay, cool. All righty. So let's see. So Sean and Cyrus, you guys can kind of tag team this one. I don't think I've asked this one yet. How will the new architecture of APL be compatible with the current 4 to 20 milliamp architecture that's widely used in industries currently? I think kind of they're getting at how would you incorporate 4 to 20 milliamp devices that are already installed in the field into this Ethernet-APL architecture. Cyrus, I think you addressed that a little bit, and maybe you can handle this one for starters.
Yeah, we expect that there will be remote I/O. As a matter of fact, the FieldComm group is got a HART-IP project group that's working on specifications for remote I/O for HART-IP.
For testing.
Yes, and the idea would be have a device that you could hook up HART instruments to, likely multiple HART instruments, and then the other end of it would be APL or standard Ethernet that could carry HART-IP.
Okay. Anybody else want to add to that?
Yeah, I was just stepping in there is that the specifications for remote I/O using HART-IP are in place. The registration program is not complete yet. So you can build them right now. In fact, Cyrus has some, and so does several others. But the actual registration procedure is what we're still working on.
Yeah. I think I want to chime in as well, and Sean, I'll let you go. I think from a software side, it's important to note that, as Wally said, it's just HART. So if you're using an asset management system that uses HART, or using any kind of a controller that uses HART, when that controller, that controller should be in that's the software at least should be able to support all of the HART-IP data, because it's just HART. You do need the hardware links, as Cyrus and Wally have alluded to, remote I/O and that sort of thing. Sean?
I think that's a key point, is that the infrastructure of the system, the controllers, the asset management, those can handle the HART-IP data the same as HART data. And that's a key point to have the conversion. But specifically if you're looking at physical layer, remote I/O is definitely the way to migrate your 4 to 20 milliamp devices into APL. But also you can bring those in individually if you wish. I mean, the architecture that we show, it's a Ethernet architecture with switches, and we often show the trunk and then the spurs. Each device on a spur, if you created a switch that also offered support for 4 to 20 milliamp products, it essentially becomes a remote I/O. In these cases, you could either have that deployed on the field side, or you could run it back to a controller. And we've seen examples from various companies of I/O and systems of different architectures, and there's a lot of ways to solve that.
Okay. So here's one that I think both Wally and Cyrus can probably address. Is it possible to convert conventional HART data to HART-IP data using a HART to HART-IP converter? It sounds to me a lot like a wireless HART adapter, only instead of wireless HART being at the high end, it's Ethernet-APL or HART-IP at the high end. Do I have this right? What do you guys think?
Yeah, there is a HART-IP adapter. It's even more transparent than a wireless HART adapter, and it'll work with any IP network, Wi-Fi, including Wi-Fi. So you could actually use it to get to stranded data and then put it on the Wi-Fi network that a lot of plants have, or it could be in the field, either one. And so you're not really converting the data because it's the same data. Okay, all you're really doing is kind of it's really kind of a gateway where you're transferring it from the 4 to 20 milliamp to the IP world.
Cyrus, has Relcom thought at all about this kind of a product?
Yes, yeah, we've been working on. I guess basically, to me, it's a remote I/O is basically what you're describing. You're taking a HART 420 milliamp instrument and connecting it up to a device so that it can be hooked up to Ethernet or Ethernet-APL. And yeah, we've been working on a what we call the A504. It's a HART-IP APL remote I/O that does just that.
Mm-hmm. Okay. Here's one that I'm not sure who should answer it. It might be Wally, it might be Cyrus, it might be a combination, maybe Sean, I don't know. So the question is, how do I configure network switches for HART-IP 2.0?
There's no changes to the network switches.
Mm-hmm.
They just work.
Mm-hmm.
Okay. We do recommend the switches support diff serve, which most intelligent switches have supported for 20 years.
Mm-hmm.
Other than that, the switches are completely transparent to HART-IP.
Mm-hmm. Okay. Got it.
I mean, clearly, if it's an APL switch, you got to make sure you're plugged in the right port and get the right power and yada yada.
Yeah.
Yeah. But
When I saw
switches
2.0,
in general.
when I saw 2.0, I was thinking about HART-IP and security, and that's mainly implemented on the device. And you have to configure the device.
Those,
and we're going to cover that in the next section. So,
but those are all IP datagrams, so
yeah.
it doesn't really change anything to the switch.
Okay, cool. All righty, let's see. We did this one. I think we've handled all of the questions that have come in. If we have more that come in, we'll get them during the next break. For now, we're gonna put on the put on the "We're on break" video, whatever that is, and we're gonna come back and start again at 45 minutes past the hour. Thank you guys for answering these questions, and we'll be starting at 45 minutes past the hour, and I believe the next set of topics is all about HART-IP security, and that's pretty interesting. So stay tuned. Thanks.
Hi, I'm Wally Pratt, Chief Technologist for HART, and I'm joined today by Pran Haran, the CTO and VP of Engineering at Smart Embedded Systems. Together, we'll provide a product developer view of HART-IP security. With HART-IP, the process no longer needs to be on an island. Valuable process insights can be easily transported by HART-IP and permeate the enterprise. But that presents its own problems. Improved connectivity exposes HART devices to more threats. This is even as hackers are eyeing the sensors, actuators, and controllers as promising targets. Of course, the HART-IP protocol has industrial duty security. Developers must implement the security. Just as importantly, though, devices themselves must be secure. So let's review what HART-IP security means to a device developer. What are the issues to be addressed and the tasks to complete? Here's our HART-IP security triangle. To realize this triangle, it takes more than just acquiring a TLS, DTLS stack and plugging it into the firmware. I think we all know that. First, the development process itself must be improved to integrate security lifecycle. Addressing security begins before product development and extends beyond its release and shipment. It also continues even after the product is no longer offered. The product itself must be designed to establish a root of trust that ensures, step by step, that the device or its security artifacts are protected and the device itself can be trusted. Of course, all of the security requirements must be implemented. Each of the three legs of the triangle have infrastructure, like the TLS, DTLS stack, that can be acquired and must be matched with in-house development. Looking at these in turn, communication security requires the developer to provide user credentials and support backward compatibility between version 1 and version 2 of HART-IP. Audit logs are unique to HART-IP and thus must be developed. Both audit logs and syslogs detect events that must be captured by the developer and pushed to the respective module. Audit logs summarize events and syslog push the events out to the network. And since the security and threat environment is continuously evolving, the device must support field upgrades. We'll talk about each of these in this presentation. Yes, developing a secure HART-IP device is non-trivial. To help the FieldComm group provides many resources in the network management specification itself. Of course, the actual HART-IP security specifications are indispensable. They are not a cookbook, but all the pieces are clearly stipulated. Since we know that security may be a bit of an unknown, especially for HART 420 milliamp developers, we also provide an annex on security. It includes an introduction to security lifecycle, root of trust, and so on. There are a lot of publications about security out there. To assist, the network management specification provides a curated list of references. All these are freely available, and I recommend you review these references. In addition, the U.S. National Institutes of Standards and Technology, Cisco, IBM, Microsoft, and others have lots of materials for secure IoT and IIoT development. Lots of different so-called security life cycles exist. The HART-IP introduction talks about the one a plant should use. In here, we're going to focus on the security life cycle a product developer should consider. The security development life cycle really is like other life cycles running in parallel with the one you already have. I mean, for example, QA/QC is its own life cycle. And each step, it has its own requirements and tasks to be performed. This is a good list of touch points, but you need the process to fit your organization. Probably the biggest challenge is finding or grooming the expertise and then integrating that security into your existing team. Security expertise is a challenge to find, no matter the organization, no matter the size. A key security procedure that must be developed is a security response plan. What that means is when you get a report of a security anomaly, you should have a repeatable process for recording, assessing, and dispositioning that event. It could be simply doing nothing is the right answer, all the way up to deploying a field upgrade for your product. And this could be even after the product's no longer sold. To be clear, security reports don't happen often, but you should be ready when they do. A key part of security planning is identifying the attack surfaces in your product and your systems. For each attack surface, you must have a security strategy to protect that opening. An example of the attack surface is the HART-IP itself. The good news is that it's well specified for you. Another is adding a web browser to your HART-IP product. Sounds great, but there are lots of ways to exploit web services, so be careful what you ask for. The key is to evaluate the features you want versus the effort to implement and the effort to secure. Roots of trust is a key requirement for secure devices. Simply put, a root of trust means starting your device from a point that is implicitly trusted. In other words, providing a device security traceable to an immutable, secure foundation. Starting from the root of trust, all software and hardware are verified secure before the software is started or the hardware is used. Each step along the way is a potential attack surface, so it's essential that each link in that chain is trustworthy and secure. The root is sometimes called a trusted computing base, essentially a small, immutable bit of hardware and software, sort of like a bootloader that can be proven unalterable and can self-verify. Often the required private keys are written there during manufacturing at the factory. Then the fuses, etc., are blown to ensure it's impossible to corrupt or alter. All software modules should be authenticated before loading and executing. In some designs, the security software and the key elements of the operating system run in a protected space where the device itself, the application, runs in like a sandbox where it cannot access the protected space. Most hardware vendors have architectures and solutions that meet modern needs for roots of trust. Architectures that enable development and deployment of secure devices containing robust chains of trust. The ARM secure device architecture showed here. This architecture allows both hardware and software to be allocated between the normal world and the secure world. Your threat assessments, field upgrade plans, secure artifacts like the private keys will drive this allocation between the normal world and the secure world. IBM, Intel, AMD, Cisco, and others have strategies and architectures that support secure devices. There are also things called secure crypto processors called trusted platform modules that can be used as the coprocessor to provide a root of trust. Next up, Haran will talk about communication security.
In communication security, we will discuss the procedures employed in HART-IP for securing the communication data. We will start with where it all began, its evolution, and a functional view of what it does. We then go into some details from the point of view of the network admin. We will then take a developer's point of view to know what to look for when implementing and testing the HART-IP product. We will further review pre-existing and open source stacks and what design choices we have to make. We will also cover some critical issues that will affect one's make or buy decision when implementing a HART-IP security for a HART-IP device. HART-IP achieves communication channel security using TLS, Transport Layer Security, and DTLS, Datagram Transport Layer Security methods. The first step is to ensure that the credentials are set on the client side and on the server side. The HART device is a server here. The credentials can be a shared key or a username password combination, which is then used to generate a shared key. Once the trust is established, during TLS-DTLS handshake, data is encrypted and the information is protected using an AES 128 encryption scheme. Application level security can be further applied to provide access restrictions, such as read-only or read and write access based on organizational roles. In HART-IP, a device must have a minimum of 5 security profiles. Each one has a client identity, its associated key or password, and access level such as read-only access as described in Table 81. Slot 0 is reserved for HART-IP Security Manager. The requirement also covers extra CRC checks to avoid operator making a typo, entering a wrong key, and you'll end up breaking the device. When storing keys and other credentials in the local flash of the device, the developer should take care and not store them in clear text. You can use factory installed private keys to encrypt them during the storage and retrieval. Operating systems used in embedded devices for implementation, such as Mbed OS, has APIs for storing the keys securely. You can find other firmware implementations for a device which will functionally do the same encrypted storage as is done in Mbed OS, regardless of whether it lacks a complete set of platform security architecture APIs known as PSA APIs. Please remember that hacker can buy your device in the open market and spend as much time as they need in their lab to figure out all its weaknesses. So please take care to ensure that at a minimum the keys get stored securely and not easily accessed. TLS is a cryptographic protocol that provides end-to-end security of data sent between applications over the internet. It's mostly familiar to users through its use in secure web browsing, and in particular the padlock icon that appears in the web browsers when a secure connection is established. This can be used by any client-server application that's communicating data securely. This is exactly what we use in the HART-IP protocol. TLS evolved from Secure Socket Layers, SSL, which was originally developed by Netscape Communication in 1994 to secure web sessions. SSL 1.0 was never publicly released, which was quickly replaced by 2.0, then into 3.0, on which TLS is based. There are plenty of open source TLS implementations available. We'll cover the top few in the next few slides. They are well tested by time and all the weaknesses detected, exploited, and fixes put in place. Please remember that TLS only encrypts the data in the communication channel. Any local storage should deploy other methods to make sure the data is secure. So let's take a look at what happens during TLS. In HART-IP 1.0, everything happens in clear text. A session initiate is sent, the response is received, and the rest of the HART-IP communication goes on. In HART-IP 2.0, we use TLS handshake. TLS is just a sequence of back and forth communication that happens between client and the server, establishing the identity of the client and the credentials. In HART-IP, the client identity is the identity information stored in command 542, as we saw earlier. The credentials is the pre-shared key, PSK. First, the client sends client hello with its information and a list of TLS protocols it desires and it supports, and along with the client identity.
The server identifies the clients from its stored list and agrees to a mutually common and preferred protocol, usually the most secure, and responds with a server hello with the selected protocol. Then the client and server let each other know that they are moving to a secure communication method, and the application data is sent encrypted using the agreed upon pre-shared keys and encryption protocols. We will see more details on this in the next few slides using the Wireshark capture. Let's take a look at client hello. All transactions begin with TCP sync from client and then server followed by ACK. The client then sends client hello with all its cipher suites it can support. When you are testing HART-IP device, you may want to consider testing with just one supported client protocol to force a server to that same specific cipher suite. This handshake shows an example of that. Note that the item named random just above the cipher suite list. This is a random seed that's used during encryption so that playback attacks can be rendered ineffective. The server responds to the client with the server hello. The server hello also contains information of the selected options from the client hello, or when the handshake fails, it could be a handshake failure message. The random here is similar to the client random, and this also is 32 bytes long, and the first 4 bytes is the current date and time. The next 28 bytes are randomly generated. So just as in client, this random seed allows one to avoid playback attacks. Now, just below the random is a selected cipher selected from the client hello. If no supported cipher suite is found in the server among those listed by the client, a failure alert will be sent and the connection will be closed. The next step is server key exchange. This is the message sent by the server to the client about the details needed by the client for generating what is known as a pre-master secret. In PSK cipher modes, this does not play any major role. In SRP cipher, this is used to calculate the pre-master secret. They are group parameters N and G, server's public key B, and the salt. With this, the client can arrive at the pre-master secret, which is essential for decryption of the server data. Normally, a developer does not need to worry in detail about what happens here. In some TLS stacks, SRP has been deprecated and may require some customization and changes to get it to work properly. The server then follows this step with the server hello done. This indicates the server has done its part of the handshake and waiting for the client's response. The next step is client key exchange. The client key exchange indicates the client identity and tells server that the client has calculated the pre-master secret. In PSK mode, this only contains the client identity. In SRP cipher mode, this contains client's public key A. The client identity has already been sent to the server in client hello. In SRP mode, now the server has all the information needed to calculate the pre-master secret. It will now wait for the next step, which is change cipher specs. The next step is client change cipher specs. Client change cipher specs will let the server know that the client is now entering encrypted message phase. An encrypted handshake message is sent. So when the server decrypts using its pre-master secret and the message integrity is good, then encrypted communication can successfully be done from this point onwards by the server. In line 100, the client is sending encrypted handshake message. Once the server receives the encrypted handshake message, it's able to decrypt it using the pre-master secret. The server then lets the client know that it is entering encrypted communication with its own chain cipherspecs, followed by encrypted handshake message. You can see them in step 102 and in step 103. Now both sides are in an encrypted state. In TLS 1.3, all these individual steps can be combined into one single TCP payload, and the number of round trips can be minimized. And again, with the same client, reinitialize a new session using the original session ID, all this entire handshake can be bypassed by retaining the original parameters in the stored data. This provides an efficient way to restart communication without additional handshakes and delays. So this is in a nutshell how the client and server handshake works in TLS and results in encrypted communication, which secures your communication channel. Let's talk about implementation of TLS in embedded systems. HART-IP APL devices are constrained by available power over APL, particularly so when you are working with intrinsically safe designs. You only have a maximum power of 540 milliwatts. The form factor also is usually very small to fit in small 2-inch size conduits or pipes for many pressure sensors. So your printed circuit space is very small. The design will also most likely be using a system on a chip microcontrollers or SoCs with limited amount of RAM and flash, typically about 256K to 384K of RAM plus maybe 512K to 1 megabyte of flash. The requirement state, the HART-IP requirement state that you must have 5 simultaneous clients that should be supported. You will need an outgoing syslog server connection as well. One needs to pay attention how you use TCP buffers for all these connections, encryption and decryption buffers, and we have to pay attention to minimize the usage of buffers. Since total available power is limited, you may also be forced to run at lower than the maximum frequency of the embedded systems on a chip controller, embedded SoCs. You still have to meet the update rates, the PV process variable update rates, and the response times. You need to support 20 plus update rates per second with a response time of less than 32 milliseconds. The balancing act has to be done. So in some cases, hardware encryption may be required to be able to provide the performance needed by the product requirements. There are several microcontrollers with its own real-time operating system, networking, and TLS support. The ARM Mbed OS has good networking support and TLS support. It has support for tasks, mutex, platform security architecture, security APIs. Free RTOS is also available on multiple SoCs with LWIP, lightweight IP, and Wolf SSL support for TLS. TI processors offer TI's NDK and Wolf SSL support for TLS. STM32, very popular microcontroller, supports Mbed OS as well as free RTOS along with Wolf SSL. Many IDEs are Eclipse based, so moving development from one platform to another is usually a very short learning curve. Now let's talk about one of the SSL TLS implementation. OpenSSL has been widely used in many Linux-based systems. It can also be used in smaller embedded systems. When you are running the function configure, you do it with minimal cipher suite that you really need. In our case, we need only those 3 suites. And features, minimal set of features one needs to make the code size and RAM size as small as possible. If you're doing this for the first time in a small embedded system, you are going to require to put some effort to get this thing done properly. But this has been done successfully, so you should have no problem getting it done. In an embedded application, you are likely to be statically linking library functions, which actually helps you reduce the code size because you're going to be only using the functions that you are calling from your application. The code size should be somewhat readily manageable. If you're implementing client or server application, the use case is pretty straightforward using OpenSSL. I have listed below here a few of the APIs relevant to our implementation. You will need a callback function when the PSK connection is requested by the client side. You will need to identify the client and load the correct pre-shared key in this case. There are examples available in openssl.org and other sites in GitHub. Another popular SSL platform is wolfSSL. wolfSSL is available and used in many embedded SOCs. One just needs to follow the instructions from the SOC vendor how to build the library. Usually it's config.h or other equivalent file. And here it's possible to change ciphers and the features you need, and you need to do a make of the library. The APIs here are very similar to SSL, and usually there is a wolfSSL prefix to the same APIs. Implementing PSK connection in wolfSSL is very straightforward. The SRP feature has been deprecated in the wolfSSL. I have not been able to find any older versions or current versions that fully and properly implement SRP. SRP is a requirement in HART-IP, so you'll have to do some digging and some code writing to implement the SRP handshake function and the TLS state machine to get it to work. Here, I have listed some of the important APIs that are needed to write the server application. To manage the cipher list, use SSL CTX set cipher list. To set the server identity or the server hint, use wolfSSL CTX use PSK identity hint. And you need to set callback like I indicated for the PSK and select the matching key. So that will be the wolfSSL CTX set PSK server callback. So some of these examples are also available in multiple public domain websites and GitHub repositories. You should be able to find them. Few other APIs that you will need to be familiar with. To assign a file descriptor as input-output facility for the SSL connection, you have to use the setFD function of the wolfSSL. In SRP, you will need to write a couple of wrapper functions to set the username and password. You will also need to modify the TLS handshake for the SRP cipher. All the APIs are listed in the link provided below. Yeah, just like the other two SSL packages, it's also straightforward to integrate embed TLS. STMcube IDE has got a straightforward procedure to build and compile embed TLS. Select the package from the middleware lists, install the necessary software packages. You make the embed TLS with minimal configuration. You should be able to customize the features and minimal set you need, modifying the file embed dtls config.h. You integrate it with LWIP and FreeRTOS. Then you can build your application with appropriate APIs. You should be able to write the PSK application in a pretty straightforward manner and get it tested with modest amount of effort. Yeah, here again, just like in wolfSSL and OpenSSL, the APIs needed are very similar. They are set cipher suite, set up SSL context, map the socket FD, set host name, set PSK callback, and to be able to read and write sockets. I have listed all those APIs below, and you should be able to find them also in the embed TLS website. We have seen this graphic before in the introduction of the HART-IP, but there's a lot going on here that bears additional investigation. The initial provisioning supports backward compatibility that HART is founded upon. In the first session, the client can be either version 1 or 2. If version 1, the server will operate from this first session onward as version 1, and HART-IP security will be disabled. This allows new HART-IP devices to work with the installed base of HART-IP clients. These are version 1 clients. End users can continue to operate their networks this way until they're ready to upgrade their clients and server to version 2. On the other hand, if the first client is version 2, then that session is secured using default one-time only security credentials, and the TLS, DTLS are used to secure the communication. During the first session, at least the first user record must be entered. The first user record for the security manager, and only that user is allowed to manage all users. From this first session, the server operates then as a version 2 only server, and every session uses TLS and DTLS from this point onwards. Any session initiated from a server 1 client shall not be answered at all. Version 1 clients are assumed to be an attempt by unauthorized device and thus treated as a threat. And suppose the first version client 2 fails to enter proper user credential 0, then what happens? All the user credentials are scrambled and the device becomes a brick, a doorstop, inoperable. The only way to recover and try again at this point is to perform a factory reset. Now this brings us to the factory reset. And so we have come to another key element in HART-IP security strategy, which is the factory reset. Ultimately, there must be a way to recover the HART-IP device, and this recovery itself must be secure and must not create vulnerability that can be exploited. The factory reset requires physical access to the device itself, and power must also be cycled. These two requirements are security strategy itself. Furthermore, everything in the device is reset back to factory setting. These settings should be in the root of trust and thus immutable. This combined make factory reset difficult to perform and painful to perform, and even more so easily detected. Every HART-IP client will likely know that the factory reset was performed, but the benefits of this ultimate do-over are essential. Factory reset allows a HART-IP device operating in version 1 to be updated to version 2. The factory reset allows the device to be recovered if the initial provision was performed incorrectly, or if the user records in the security manager and or the HART-IP clients are corrupted or lost. So thus the factory reset provides another cornerstone in the HART-IP security strategy.
Communication security provides active prevention of unauthorized access. HART-IP supports defense in depth by specifying two detection deterrent strategies to complement communication security. The first is syslogs. End users often insist on supporting syslog in network devices, and many installed wireless HART gateways already support syslogs. The key to this is an optional syslog server, a database application for recording syslogged events. The syslog server can be simple or have powerful querying capabilities. We use the open source rsyslog in our test registration labs. So you could start there and then gain experience from that. HART-IP device is a syslog client, and commands 544 through 547 configures the device's connection to the syslog server. Basically, the HART-IP device opens a socket, connects to the syslog server, and transmits text formatted message to the syslog server. The text output is sort of like a specific printf that's generated. The format of these text messages are standardized by HART-IP. The other implementation requirement is to detect specified events in the firmware. These events are generated at different places scattered around the firmware. HART-IP specifies a diverse group of events that must be published by devices. These include things like when the server powers up, when somebody changes security credentials, when a session is open or closed, when a configuration parameter changes and which one was it. All of these are time-stamped. If this event is being triggered by a client, then the HART-IP address of that client is also included. So these are a lot of different diagnostics that published that allows you to kind of backtrack through what's going on. For reference, these are example syslog messages captured by our syslog server in the FieldComm group test labs. The bits in yellow are actual annotations from our syslog itself, while the rest is the formatted text messages transmitted by the HART-IP device. The CEF has clearly specified fields and consistent delimiters. This allows even simple tools like grep, awk, or perl to be used to search the syslogs for patterns, unwind things like plant trips or cyber attacks. Audit logs are always available and provide a summary of communication activities. The summaries record a range of insightful client and device actions. In other words, there is always essential records to detect anomalous behaviors. The audit logs require about 7K of RAM. They're volatile and cleared on power up. Due in part to their size, audit logs are accessed via their own HART-IP datagram. And depending on the PHY, they are often read in fragments by a client. Since audit logs are event summaries, they, like syslog, need event detection at various places in the firmware. There are two main parts to the audit logs: the header, which is a summary of the device itself, and client records that summarize each client session. The header includes basic information like when was the device powered up and did it find a syslog server. By the way, a possible threat vector is to cycle the power after a cyber attack on the device. That's one reason for recording the time when the device was powered up. Cycling power on a process instrument should not happen often. It's kind of a giveaway that something potentially bad has happened. Client records provide basic statistics on each communication session: when the client connected to it and disconnected from it, who was the client. You can tell which clients are currently talking because their disconnect time is not available. It also records if the session is faulted or if the clients try to hack into the device. But that's what the bad session init potentially means. This is a circular list, so once the list is full, the oldest sessions begin being overridden. HART-IP requires devices to support field upgrades. Since the security environment is constantly evolving and security vulnerabilities may be uncovered, field upgrades future-proof the devices. Planning and designing for field upgrades must start early in the product development. They affect the hardware and software design, manufacturing, and even field service. At times, your device could contain multiple firmware versions. One solution to this could be including a serial flash memory chip for these duplicate firmware modules. The structure of the firmware should be considered. Perhaps there could be several modules. For example, the HART-IP stack could be a separate module that is updated if TLS or DTLS vulnerability is uncovered. And to be clear, the HART Technology Working Group does anticipate adding additional cipher suites over time. Field upgrades are an attack surface and their integrity must be protected using, for example, private keys, authentication, and encryption. It's possible even to upgrade the keys as part of a field upgrade. I do not anticipate field upgrades to be routine and frequent, but they must be planned for and tested for also. As mentioned, field upgrades are attack surface. Consequently, maintaining the root of trust is essential. To support field upgrades, 2 keys are often used. These keys are flashed during manufacturing and physically unalterable from then on. Access is restricted to prevent their compromise or their corruption. Field upgrade distributions are normally double locked. First with a signature to confirm the distribution can be trusted, and the second key to use and cipher the firmware itself. This ensures the distribution is unaltered in transit. Ultimately, your security team needs to plan, design, and make the choices that work for you, what fits your culture of your organization, etc. In any case, the security chain needs to be maintained. To standardize the mechanics of transferring firmware to the device, the HART Technology Work Group is developing a file transfer specification. The file transfer specification is based upon the block data transfer specification introduced in 2001. This file transfer specification is draft and available from the workspace. If you're interested in it, the HART Technology would love to have you help participate in finalizing this document. This sequence diagram depicts the basic process for deploying a field upgrade. This works with any flavor of HART, HART 4020 milliamp, wireless HART, or HART-IP. Of course, it's a lot faster with HART-IP. Prior to actual transfer, the module is confirmed to match the device. The signature may also be confirmed in this step. Once that sanity check is complete, the actual transfer occurs. The center part of this diagram shows the block data transfer occurring. After transfer, the module is validated, then the device can be instructed to enable and start using that upgrade. This slide provides a few references related to field upgrades for further insights. I suggest you review these offline. For convenience, we put copies of these in the workspace. We've covered a lot of material, so let's step back and think about the key takeaways. We did a pretty deep dive into HART-IP security, and certainly there are plenty of details. But there are certainly a few keys to success that should be considered. A secure HART-IP device requires both a good design, but also needs processes and a security-minded culture that might be new to your team. This touches on security development lifecycle, enhancements to manufacturing, even potentially new responsibilities for your service channel. We talked about HART communication security, and of course there's more than just acquiring a TLS, DTLS stack. Furthermore, your firmware must be designed to detect critical events and push them out to the syslog or summarize them in audit logs. Yes, it's an impressive engineering challenge, but remember, FieldComm Group is here to help. We have HART-IP clients to support your development, a reference implementation, the native flow device that you can use to clarify specific operations, procedures, to benchmark your device against. We also provide great technical support and/or consulting. Thank you.
Okay. That was about 45 minutes on security. Oh boy. Okay, let's get Pran, let's get Sean, Wally, and let's get Cyrus back up here. I've got a few questions that have come in from the audience. What we're going to do is answer these questions, and then we're going to break, and we'll come back again at 45 minutes past the hour, I believe. So let me start out with a pretty simple one. At least I think it's simple. I always think they're simple. So I'm going to shoot this one out to Wally. What's a better practice for securing devices? Username, password, or PSK?
They both work equally well. SRP is kind of fallen out of favor because it's a little bit easier to compromise. But at the end of the day, they're really pretty fundamentally the same. The question is what the plant wants to use. Is it easier for them to remember, a password, or is it easier to remember a, 32 character long hexadecimal number? And once that's programmed in the device, and if your host application takes care of that for you, they both become invisible pretty quickly. So, that's why we wanted to have both.
Okay, cool. Does anybody want to add to that? Nod, shake. Go ahead, Pran. Looks like you're going to say something.
I think, like Wally said, the SRP is easier to set up, and the entropy on that is still pretty high. There are some research papers from Stanford which talk about how you can improve on the SRP and how to set the keys and so on. So, I can try to find those links and send it. But SRP is considered slightly less safe compared to PSK.
So I'm assuming that when you guys use the term SRP, you're referring to username, password.
Username, password, yeah. Secure remote password, yes.
Okay, got it. Okay.
And let me add one more thing to it.
Sure.
The pre-shared keys and the secure remote passwords, they really only used to authenticate the connection. Once both sides said, "Oh, I trust that host," then they switch over to AES 128, and you never see those again. So they're only used during that handshake that Haran showed us, and then from then on, you use the same shit.
Okay, cool. All right. There's another one that's kind of okay. Here it is. In HART-IP specifications, are there mandatory and optional features? I think regarding security, since this was a security presentation.
No, security is mandatory, and if you're a version 2 device, you must do security.
So you must do security, but sounds like there's some. You said it's not a cookbook. Sounds like there might be some variability in how you do security.
Well, I mean, the it's not a cookbook because the security, communication security and stuff are required, but how you implement that in your device can vary because you've got to come up with an architecture to protect all those keys and assets. Mm-hmm. And that affects even potentially your manufacturing process. Mm-hmm. And so one of the things we're trying to highlight in this deep dive into security is that, yeah, you're using TLS stack, but you got to think holistically about the whole security threat aspect for your company. Mm-hmm. That's really was what I mean, variability.
I see what you mean. Okay.
Also, when you consider that, even though it's not called in security section, there's performance metrics you have to meet, like the update rate, response times, and they will force how you actually implement things. For example, the software-based encryption may not be workable, and you may not be able to support it with software encryption. Very likely you need to use hardware acceleration.
Because if you use software, you might not be able to meet the response times and the timing requirements.
Exactly. Yeah.
Got it.
Yeah. Got it. But at the same time, most of these systems on a chip now have got an AES hardware encryption engine that you can use. So
yeah, but I think Pran's point is valid in that there's elements of the spec that will drive you towards a specific security implementation, and you need to kind of pay attention to that.
Absolutely.
Okay. So this question I think is kind of a follow on to this whole topic of security, and I'm going to send it out to Sean. So I'll read it. Different end users have preferred automation protocols: HART-IP, Profinet, Ethernet-IP, and maybe OPC UA. Will field device suppliers and host system suppliers need to support automation protocol specific security methods, or will there be a common security method across these automation protocols?
Yeah, so that has, I guess, two parts to it. First of all, what is currently in the field today and what is currently specified today is whatever it is. So The protocols that exist and the requirements of those protocols as they're currently installed will continue to be requirements moving forward because that's what's there. We do have a coordination between the standards organizations, including those overseeing the protocols you just mentioned. So FieldComm Group, along with the Profibus organization, the ODVA, and the OPC Foundation. And we also have liaison to the IEC IEEE. And with that, we have a security harmonization group. And that group has released an FAQ technical paper, which is published on the FieldComm Group and other organizations' websites. But through the FieldComm Group, you can get a copy of this, and it outlines the commonality of security philosophies moving forward, and also our efforts to try to reduce the number of different tool sets, the number of different requirements, and the number of different, I would say, things that users need to know and put into workflows. So the idea is to have some commonality and harmonization of the tools and the workflows and the requirements around security. And so that's a really good philosophy and something that we're working to help reduce for the user experience.
Okay, good. That's great feedback, and that's, you know, if you're a user, I'm sure you'd be happy to hear that kind of talk that we're trying. You know, so I think the next question I'm gonna throw out to Cyrus. I believe we'll start with him, and then Wally, you can chime in. And it's what must a developer do differently when developing HART-IP with security for Ethernet-APL devices versus Ethernet devices? I mean, intuitively, it seems like nothing, but maybe there's more to the question than that. Go ahead.
Well, with I think actually some previous questions kind of answered some of this, but the hardware you want to look at is you have to pick out the microcontroller, and I think what Pran was saying, you know, you may or may not need hardware support for the encryption. And as far as the physical layer, you'll have a PHY chip associated with that. So you have to pick out your PHY chip and then interface to the microcontroller via a MAC. So you have to make sure your microcontroller has a MAC. That's not a security related thing. But that's, I think, the primary factor there. As far as the hardware is concerned, I think Wally or Pran would answer the software end better.
Yeah. There's it's the reason we use internet protocols because we don't care about what the physical layer is, and so the security doesn't change. Is that a fair statement, Haran?
Yeah. The security, the application layer, the TLS, all that has got no effect on what you do. The same exact code will run. And at least in terms of specific maybe firmware needed for the APL files, I can tell for the Texas Instruments PHY, you can actually set the strapping. There are like, you know, pull up, pull down resistors you can set. They will come up with 0 additional code on your side. So if you write the code for a standard Ethernet interface, you don't have to write any code to bring up the APL if you do the right strappings, because for a transmitter device, we have only a single voltage value, which is like 1 volt peak to peak, no options needed. So pretty much all the options can be hardwired. So you don't even have to program the PHY through what's called the MDIO interface, even though it's still there, but you can work without any firmware change.
Okay, great. You know, we had one question that just came in that we should have probably tried to distinguish earlier. The question is, you know, we talk about HART-IP version 2.1 and version 2.0 and version 1. Wally, can you kind of elaborate the differences? I think we're primarily talking about the new specification that's out for ballot, but please correct me if I'm wrong.
All right. The version HART 1.0, you know, started shipping long time ago, standardized in 2012. It required security, but didn't say what the security was. Version 2.0 of HART-IP, security is mandatory and is specified in detail. and that was released a couple of years ago. And so the real trick, though, is to make sure you can do the backward compatibility, because when you start deploying your devices, all the clients in the plant may still be 1.0, and so you need to be able to work with them. As the people evolve and start moving their clients and make sure all their field devices are 2.0, then they'll switch over, do a factory reset and switch over and bring the security online. And so that's really the difference, is the security was required but not standardized versus security is standardized and mandatory between 1.0 and 2.0.
And from what I just heard you say, 2.0 was released several years ago, so it's not the current.
The current spec, the focus of the current ballot is the safety layer.
Mm-hmm.
Okay. We did add MDNS and DNS-SD in there, so there are some improvements, but those will be phased in over time. So there are improvements, but the real focus was safety on this ballot.
Okay. Got it. All right. Thank you. Sorry, I muted myself while I was talking. My bad. So there's two questions. There's one question and then one more that I want to ask. So the question that I'm going to ask, and maybe Sean, you can answer this question, is the security presentation discusses syslog and audit log quite a bit, and also mentions a syslog server. What type of software is this? It sounds like syslog server is some kind of component in some other software package. Where would it be found in a process automation system? And and just kind of elaborate a little bit on it.
It would be found in your host or control system. So the host control systems that are deployed today, your common large commercial systems, include the syslog server, audit log checking, and they have these features built in. You could also have specific security related tools that could also have access to that, and including from, of course, the host vendors have tools that access this, but also third parties, thinking about the larger asset, capital A, asset management, big data kind of scenarios can also have access to that data and offer some capture metrics and monitoring around it.
Okay, great. All right, there's one last question here that I'm going to address because we're a little bit short on time. I'm going to actually defer it. The question is, if I can find it. The question is, are there suggestions regarding RTOS and stack software for field devices that would meet SIL certification when SIL is required for a given field device? And I'm going to punt on that question because a lot of the presentations that are coming up are going to describe specific product offerings from some of our development partners. And I think you'll get a better answer to that question after you've listened to some of those, and we can. And if you still have the question, please answer it. Ask it again at the end of the session, and we'll try and go over it. So so this concludes kind of what I call kind of the primer materials, where we gave you some of the background on Ethernet-APL, HART-IP, and security, and networking, obviously. Now we're going to kind of shift gears and start focusing on the actual development of HART-IP and APL devices, as well as some of the conformance testing that we'll be undertaking at FieldComm Group. And we'll be doing that after we have our short break, which is only about a minute long at this point, unfortunately. We'll come back at about 8:45, and the next presentation will be Jose Leonett from emBex, I believe, and talking about how to convert a HART device to a HART-IP device. See you soon.
or task. The HART connector. Hello everybody. In this presentation, we will give you an overview of the most relevant topics to be considered in the development process of a HART-IP device. One of the biggest challenges will be to find the right balance between explaining as much as we can, making that interesting for you, but at the same time, taking into consideration that some competitors are also watching. We will do our best. My name is Jose Leonett, Head of the Business Unit Process Automation by emBex.
Hello, my name is Matthias Herrel, and I'm the head of the firmware team development.
Thanks a lot, Matthias. Before we start, few words about emBex. So, emBex is a pure development company. So we develop products for other companies. The headquarters is located in Freiburg, a wonderful city in Germany. Since 2001, development create products for big customers, with more than 200 highly qualified engineers and technicians, with industry-specific know-how, and of course, an extensive experience in the development of industrial products, including explosion protection, cybersecurity, and functional safety. On the right side of the slide, we are the first company worldwide, and still today the only one, with a so-called maturity level 5 for the development process. The most important advantage we offer to our customer is the one-stop shop for the development of products and/or systems. And that from the moment the idea is born, all the way to the transfer in the production and lifecycle management. We have all required competences and experience like software, hardware, mechanic design, and can take care even of the required certifications. Now back to the main topic of this presentation. What needs to be done to move from a HART device with 4 till 20 milliamps to a 2-wire APL device with HART-IP? For this presentation and for this case, we will focus on a HART device which is in the field. In this presentation, we'll assume that there is a HART device that needs to be converted to a HART-IP over APL device. Just in case of question, the image is not a real device, just a dummy device. Please do not try to understand what this device do. This is just a dummy. The most important aspect to be considered are the development as of the hardware, the explosion protection, software, housing, as the mechanical engineering, the functional safety, cybersecurity, conformance testing, approvals and certification. For this example with the HART device and for this presentation, we will focus on the hardware, explosion protection, and software. That will be the focus on today. So let's take a look to a simple block diagram that will help us to understand the main task or functions we need to consider. On the left side, you will see then the generic HART device with the following main related blocks or tasks. The HART connector, which is a 485, the explosion protection, the power supply with approximately 40 milliwatts, just an assumption, a HART modem with a UART interface to the microcontroller, the current loop, the HART protocol, the application, and the functional safety. On the right side, you will see then the generic HART-IP over APL device with following related blocks or tasks. The Ethernet-APL connector, also an Ethernet connector, the explosion protection, the power supply and port profile, we assumed about 500 milliwatts. Then we have the HART modem that will be replaced by a 10-base T1L PHY with a SPI or MII interface, also to the microcontroller. Then we have done on the right side the HART-IP protocol, the application, the functional safety, and the cybersecurity. That's because we have now an Ethernet-based interface in an IoT environment. Because in lack of time, we will not cover in this presentation the functional safety or cybersecurity. There are big topics that we can exclude in this presentation. We will focus our attention into these blocks and the related disciplines: hardware, explosion protection, and software. But let's take first a look to the hardware explosion protection related topics. Now we will focus our attention into the exploitation and power. For the hard device, on the left side, are the blocks explosion protection, power supply, and the current loop. For the device with HART-IP over APL are the blocks explosion protection and port profile with the power supply. What are the related tasks? First, we need to replace the connector. Also to replace the RS485 as assumption, also this hard connector, by a Ethernet 1, conform to the port profile specifications. In a few seconds, I will show you where to find the port profile specs. We have to think about how to separate the data and the power lines from each other, and how we decouple and couple the data. We must design a new power supply and power regulation architecture that meets the port profile requirements and also provides us with the corresponding additional power compared to a 4 to 20 milliamps device. In this example, we move from about 40 to 500 milliwatts. In this context, it is defined what kind of port class the device will be. In this case, it is likely a port class L device that is power from a spar. The power class will be A with 540 milliwatts. Now, related to the port profile specs, to the next slide. You can download the port profile spec from the FieldComm group library, which is well documented and prepared. There you will find all required specification and the details that you will need. In this slide, you can find the link and the related QR code to access this document. Take a look on that. Now back to the list of tasks. In addition, the explosion protection must then be adapted to the new power requirements and, of course, to the new intrinsically safe parameters, as specified in the technical specification 60079 part 47, which is the equipment protection by two-wire intrinsically safe Ethernet concept, called 2-wise. And, as always, the corresponding electronic circuit must be designed and routed in the PCB. Which are the required skills? So you need an expert in electronic circuit design, someone who take care and understand and is expert in power supply technologies, in explosion protection, and last but not least, experience in layout and PCB design. Required tools: electronic circuit design and layout tool. And of course, the required tool for the documentation of the explosion protection measures and calculations. Of course, not only the power supply is important at this point, but also the advantages because the new communication physics. Now we no longer have a 4 to 20 milliamps HART interface, which are very low bandwidth, but we are now talking about a 10 megabits Ethernet. That is a huge improvement. Let's take a look now to the PHY and the microcontroller unit. The decision about the right PHY and the microcontroller is not a pure hardware topic. The decision needs to be made in a close cooperation with the software development team, really with a close cooperation. Taking, of course, in consideration the application requirements. So maybe you will need on your product management. And that is a crucial topic. Then your application performance will be likely more than before. So it will increase. You are now designing a new IoT device. Let's say at least ready to be used as an IoT device, you have an Ethernet connection. And do not forget the very high bandwidth. For that reason, if we are speaking about a development process, we need to speak about the application requirements, but not only for that what your customer needs today, but maybe at least for the next 5 years. This means you are developing a product that will be on the market at least for the next 5 years. We strongly recommend defining the product and application requirements before doing the first step in the development process. This input is crucial for the complete development process. As you can imagine, you will need a well-established team working really as one team. But let's come back now down to our main goal for today, at least and related to the PHY and the microcontrol unit. The decision about the right IP, as a PHY, and microcontroller match is not a pure hardware topic. The decision needs to be made in a close cooperation with the software team, as a hardware and software team working as one team, taking of course into consideration the application requirement and the financial aspects. Let's consider now the PHY and the microcontroller unit. We are talking about the 10-base T1L physics. We have two main options. It's a pure PHY component or a MAC PHY. What are the differences? With a pure PHY component, we have an MII interface that can dock directly to the MII MAC interface of a microcontroller. And of course, can also be used with the full performance of the Ethernet interface. On the other hand, we need a bigger microcontroller that offers the appropriate interface and also a corresponding performance. There are also a MAC PHY chips that have a MAC integrated in the chip. In this case, for example, a SPI interface is available, which of course can also connect to a much smaller microcontroller, and that means limitations in speed and performance. According to the selected PHY, a corresponding microcontroller can also be selected. Either a small one, which will be cheaper, with a small footprint, or a large one, which may be a bit more expensive and offer a better performance. But also very important, of course, should meet the software requirements. What else needs to be done? We spoke already then about the PHY and the microcontroller unit, the selection. That is an important step. But of course, as always, the corresponding electronic circuit must be designed and rooted in the PCB. Required skills, electronic circuit design, also people that really know what they are doing, a microcontroller know-how, layout and routing, and a team spirit. Also, software and hardware working together as one team. Required tools, as always, electronic circuit designs and layout.
Now let's take a look at the software development aspects. The PHY is then connected to the microcontroller via SPI or MII. As José has already mentioned, we start with the selection of a suitable Ethernet PHY. Together with the hardware developers, we determine this. We consider the requirements and coordinate the results to get the best solution. When selecting the microcontroller, we pay attention to the low power design and the requirements of the HART-IP protocol. It certainly makes sense to build in reserves so that new functionalities can be added when the application is modified. For the software development process, we use the V model, which is also known in the systems engineering process. Now, let's have a look at the software development process in detail. If the requirements are not complete, then I would suggest preparing a system and requirements analysis before the software development starts. The results are documented in a realization concept. For complex applications, I recommend creating a software design. For the software architecture, we can rely on tried and tested solutions. For the software implementation, we use a coding standard as a basis and focus on good source code documentation. The process of continuous integration allows the software to be tested automatically according to the specified and implemented test routines. This provides the development team with a uniform and objective evaluation of software quality at an early stage and clear indications of improvements. The CI helps to increase efficiency and quality through automation and is a basis for agile software development also. Let's come to the required skill set and tools. You should have knowledge about operating systems, the HART-IP protocol, the IP protocol in general, and also IP security mechanism. A well-established team is necessary to implement firmware, to develop the hardware, and to integrate the HART-IP protocol. We achieve high software quality through early and automated tests. Thank you. That was the aspects of the software development.
Now let's take a look to the general development process. And this is one of the key points. This is not just technique. As you already know, emBex is the only one company worldwide with a so-called maturity level 5 for the functional safety development process. One of the reasons is the straightforward and effective development process as a result of more than 20 years of experience in the development of functional safety products. So not just standard products, functional safety products. The recommended process is based on the well-known V development process, as you can see down in the slide. On the top of the left side, we start with a consultant-like phase. The main target of this phase is to specify the customer or market requirements, and this is key. I recommend you not to move to the next phase without to know the basic requirements. Better is to know exactly what the customer needs, and this don't change. But this is not in the real world the case. After the concept phase, we know exactly what needs to be done. That is described in the so-called product requirement specification. In addition, after the concept phase, a reliable cost and time estimation are the most important outputs. I strongly recommend not to move to the realization phase without having a clear product requirement specification as a result of the concept phase. Very important. On the right side of the V model, you will find the verification and validation phases, including then the certification. Beside the phases, you will need a strong project management. And the main target is to avoid unnecessary additional development loops in order to save time and resources. Of course, the details are more complex than that what we are explaining, and are much more than that you can see in this simplified overview. Now we are coming almost to the end of this presentation. We have already taken a look to the hardware development, the software development, some hints you have got, and the development process. We want to give you takes away for this presentation. The first one, APL is changing our business. This means new opportunities for you, but also for your competitions. So this is a long-term strategy, but the time to market is crucial. I strongly recommend to define the requirements before you start with the development. Save time. And Matthias?
Please do not forget the following aspects. We have cybersecurity. You should have conformance testings, approval and certification. Experienced and well-established Development team is the key, working as one team.
And of course, please do not try to reinvent the wheel. We wish you a successful HART-IP over APL implementation. Thanks you a lot.
So thanks for joining and see you soon.
Bye-bye.
Hello, and welcome to the Conformance topic. We'll discuss conformance for HART-IP and Ethernet-APL. There are many motivations to register a product. These include interoperability with other products and vendors, proof to customers that the implementation conforms to standards, a desire to use the HART-registered mark. Also, gaining a listing in the FieldComm Group's globally available product registry, which includes listings and FDI packages for registered HART-IP products. Any registered HART-IP product can use the HART-registered mark. HART registration includes testing of the physical layer, HART-IP application and the communication stack, and the FDI package. We'll now go into the requirements and specifics of how to test the HART-IP Ethernet-APL products. Requirements for a HART-IP Ethernet-APL product come from a variety of sources: customers, international standards, industry-specific requirements, and marketing or internal product input. Ethernet-APL and HART-IP test specifications are the source of the test cases. These will be used to determine conformance of products. Remember, HART-IP does not require Ethernet-APL. For purposes of today's discussion, we will focus on Ethernet-APL for HART-IP products. The HART test system continues to serve as the platform for testing HART products, including HART-IP. HART-IP specific test cases were first available in version 3.7 of the tools. The tests have been improved and expanded with Test System 3.8 and will continue to be included in the ongoing work of the HART test system. Today, HART-IP testing is focused on servers. Servers could be field devices, transmitters, actuators, remote I/O, multiplexers, or even connections to wireless HART gateways. When testing the FSK HART devices, we use a power supply, a resistor, and 2 modems. These are attached to the HART test system. The test system uses a test environment such as HTest to send and receive test case data, the commands. HSniffer runs to capture the traffic and provide details of what is on the wire. HART-IP changes this setup a little bit. Similar to testing wireless HART products, the base test system is still present, but other products are required to perform HART-IP testing. The HART test system connects to a switch using an Ethernet cable. The switch then connects to the HART-IP product. If the product under test is an Ethernet-APL product, then a field switch is added to supply power and handle the switching between Ethernet-APL and the multi-wire traditional Ethernet. In addition, a second machine is needed to run the portable HART-IP client, which is an essential component of HART-IP testing. HART-IP testing can take place on an isolated bench or with connection to a larger network. It is critical that the intended usage, whether shared or isolated, is known so the appropriate configuration can be made when we start the HART test system. The portable HART-IP client performs basic assessment. This includes the operation of the HART-IP product without network services. We also test the factory reset requirements and the HART-IP version 1 and 2 operations. Test assessments include configuring the HART-IP product for testing, IP tests including IP port manipulation, HART-IP security test cases, which requires a product that supports HART-IP with security or HART-IP version 2, IP ports and security with multiple clients in the network. The HART test system includes the HART test automation, which covers the HART-IP server tests, the universal application layer tests, and common practice command tests. The HART test system also supports network services, so tests can be run in an isolated network. Services such as DHCP, DNS, NTP, and syslog server can be enabled on the HART test system. These can also be disabled when connected to a shared network such as a lab network or the office network. We also use a switch to LAN the Ethernet cables from the test system, portable HART-IP client, and the product under test. When testing an Ethernet-APL product, the Ethernet-APL field switch is used for the connection to the product under test. There may be additional network infrastructure depending on the product. A field switch, Wi-Fi access point, PoE supply, or an additional power supply may all be part of the overall setup. Remember, Ethernet-APL products could be separately powered as well. The portable HART-IP client tests the commissioning and operation of the product under test with network services. HART-IP security features, such as secure connection to the device and audit logs, are tested with the portable HART-IP client. Hostname, NTP, and syslog are also tested with the client. The HART-IP test system includes a menu for the HART-IP server test cases. These tests are labeled as HIP. There are also updated test cases in universal and common practice tests. The test updates include specific testing of HART-IP requirements, including burst mode. The command line run HIP, run HIP, will run all the HART-IP server automated tests. HART-IP tests are structured very similar to tests for the other types of HART products. Log files are created for each test case. At the end of each test case log is a result of either pass or fail with a specific failure point number that can be referenced in the associated test specification. The HART test system can seamlessly switch between testing all types of HART products. 2-wire FSK or PSK HART, wireless HART, and HART-IP all share the same test platform. As shown in the screenshot, the HART test system 3.8 runs on all HART test appliance hardware, including the oldest test systems. The screenshot specifically shows the HART-IP tests running on an Eden machine, which is one of our oldest machines that we shipped. Here's a reference list for the required universal application layer tests that must be passed for a HART-IP product. The formal list is available in the HART-IP registration procedure. Here's a reference list for the required common practice application layer tests that must be passed for a HART-IP product. Again, the formal list is available in the HART-IP registration procedure. Here is a list for the required HART-IP server tests that must be passed for a HART-IP product. The formal list is again available in the HART-IP registration procedure. Now we will discuss testing of Ethernet-APL products. Here is a block diagram of a basic test setup. In this case, a PC is running test software that uses a hardware interface, power supply, and scope to test an Ethernet-APL field device. We'll discuss testing in more detail. If a hardware developer wants to run the Ethernet-APL conformance test manually, the setup will require a list of equipment similar to what is shown here. The University of New Hampshire Interoperability Laboratory, UNH-IOL, and Telebyte are two organizations that offer test tools. In any of the listed test options, you may need to acquire specific equipment, models, and versions to be able to conduct these tests. You can contact us offline for more details on test tools and equipment necessary for conducting these tests in your own lab. This is an overview of the Telebyte test solution. In this case, a field device is tested using the test software, scopes, arbitrary waveform generator, etc. The specific equipment and tools to create this setup are listed in the Ethernet-APL equipment list, which is available in the FieldComm group website and through our support system. This is an overview of the UNH-IOL test system. Again, specific equipment and tool information is available from the FieldComm group via the equipment list and also from these vendors directly. The most common type of Ethernet-APL product is a field device, which encompasses transmitters and actuators, but also could be the connection to a wireless HART gateway or multiplexers of traditional HART devices. The field device is a load to the spur. So this would be connected to a switch that is the power to the spur. So the switch is the power supply and the device is the load. An example of the test cases for a field device are listed. There are tests for both data, which can be summarized as the formation and handling of the signal, and a separate set of tests are related to the power and noise of the device. All tests are conducted at 3 temperatures, All tests are run at the maximum and minimum claimed temperatures. These results from the min and max temperature are generated by the vendor or a test house that you name. Also run all the tests at room temperature. These tests are then run again by FieldComm group in our test lab at room temperature to confirm the result. So all three sets of tests results are assessed for conformance for the overall registration. The test specifications include the details for each test case, as well as more information on the setups, execution, and assessment of each test. As I mentioned on the previous slide, different test cases may require specific setup. In this case, the setup for the Ethernet-APL data test case 146.1.7, which tests distortion, is shown in a block diagram. Note that there are equipment requirements that are specific to this test. This is the block diagram for the stress receiver test, which is a data test case 146.2.1. This setup is quite different from the one shown on the previous slide. This test requires a cable or the cable emulator to complete the test. The type of packets and allowed tolerances, along with further details of the test, are available in the Ethernet-APL data test specification available from FieldComm Group. In summary, there are three distinct areas of an Ethernet-APL HART-IP field device. These are tested as the HART-IP portion of the device, including the application and stack. This follows the HART-IP registration procedure, which includes the test specs for the HART-IP server, the common practice commands, and the universal commands. The tools for testing the HART-IP communication stack and application include the portable HART-IP client and the HART test system, which is currently version 3.8. The FDI package is registered following the FDI package registration procedure. There are test specs for both the FDI package as well as the DD contained in the FDI package. The tools to develop, build, and test the FDI package for a HART-IP device are included in the FDI IDE, which is currently version 1.5.1. The FDI IDE includes a communication server for HART-IP that enables communication with HART-IP servers such as field devices, gateways, multiplexers, etc. The Ethernet-APL portion of the device follows the Ethernet-APL registration procedure. There are tests for data, power, EMC, and intrinsic safety. As a reminder, EMC tests are often run by qualified developers or third-party labs. Intrinsic safety requirements require reports or certificates from third-party labs. The equipment to test Ethernet-APL is listed in the equipment list provided by FieldComm Group. Acquisition of that equipment is up to the individual vendor. There are solutions to assist with testing offered by partners such as UNH-IOL, University of New Hampshire, as well as Telebyte. Thank you for your attention, and as always, if you have questions, feel free to reach out to our support portal or contact the FieldComm Group staff.
Okay, thank you. I'd like to see Jose, possibly Matthias, if you're there, and Sean join me live. We've only got a few questions this time, but I think that they're going to kind of lend themselves well to sort of a discussion format. And I'm encouraging some interaction amongst the speakers to answer some of these questions. So we'll start out again. I'm trying to start out with some simple ones. This question is about security. And the question is, and I think it ties into a lot of the topics that you guys brought up, honestly, which is for the implemented security of HART-IP and maybe any protocol, I guess, is the use of PSK secure enough, or will certificates be necessary in the future? And I'm gonna have Sean just kind of wax on that one a little bit, and maybe Jose and others, maybe you guys can talk about what your thoughts on security just a little bit.
Sure. So, today what we have with PSK and all the analysis that's been done to date is that the solution that we currently have in HART is the solution that we'll continue with, and that it fulfills the requirements that have been placed upon us by the requirements for secure environments and secure protocol and secure communications with products and authentication. Certificates, of course, are I would say, a another solution, and they are something that we have worked in the harmonization group with other organizations to come up with the future path of how those certificates would be structured, how they would be used, and what they would look like. So there is an opportunity for the future that may well add certificates, but again, we're in the discussion process there, and there's always the working group where we'll actually fulfill that. So it's really going to be up to the HART working group or the HART-IP project group to come up with the specifics there. But for today, I think we're quite satisfied with the solution that's being offered.
Anybody else want to add to that? Can't hear you, Jose. We can't hear you. It must be on your end because it looks like you're unmuted on our side. While he's trying to figure that out, I'm going to actually chime in with something. And Sean, you and I can discuss this briefly. I mean, I think one of the things that I'm pretty sure we're going to see is with HART-IP in APL devices that support PSK, they're going to be shipped with an FDI device package. And those FDI device packages are secure, and they do have certificates. So you've kind of got another layer of security built into that, to the overall software that would be delivered with the instrument. Would you agree with that?
There is another layer there as well. And also I would say that, when you get into topics like TLS and PSK and certificates, and, this really gets into, I would say, a very deep pool of discussion, and it's not something that I can say that from within the working groups, that this was not something that was just handled in a flippant manner. I mean, this had a lot of very detailed discussions, a lot of very strong research, and as you heard Haran say earlier, there academic papers and studies and things that have been commissioned and used as the basis for a lot of the decisions that were made. So it's not just simply an opinion. There was a lot of fact-based decisions made there.
Okay, I'm watching the bits get fiddled back over there at emBex, and hopefully we'll get them online online.
Have you tried turning it on and off again? Yeah. Off and on again.
Can we hear you now, Jose? No, apparently not. Okay, I'm going to go on to the next question, and we'll let you chime in a little bit when need be. This is a question about conformance, Sean. So I know we don't need to hear them. So the question is, this is kind of a FieldComm group specific question, I guess. APL registration and APL conformance, in what way are they different? And probably at a basic level. And I think this might give you a good opportunity to talk about a protocol level versus just the physical layer conformance. And maybe you could chat on that a little bit.
Okay, sure. And now, I'm sorry.
That's okay. Before Sean, since we're a little bit messed up here, Jose, did you have anything you wanted to add on the security topic?
No, regarding this aspect that Sean mentioned, we are 100% agree. The only aspect of cybersecurity for a device, please consider also the hardware aspect. So cybersecurity is not only software. You can implement software security also in the hardware. As example, separating the communication architecture with the process architecture. So separate these ones. There we have done some solutions on that. So take in consideration that you have to consider on everything. Thank you, Paul.
Yep. Okay. So
Sean, I would say also security also goes into manufacturing, secure onboard storage. I mean, it's a very deep pool there. Okay, so conformance. Yeah, so a product, of course, as we've heard, is made up of physical components, and also there is the software components. So if you think about the driver side, the FDI package, we will create the FDI package. Those will be tested and registered. You create the HART-IP communication stack and the HART-IP application, which of course is a HART application, and those will be tested and registered. And you also have the physical layer which is really can be separated into the APL, let's call it the larger APL, and then specifically to the intrinsic safety. And so for APL, we have the requirements around EMC. We require you to be intrinsically safe. We require that the product meet the data and the power requirements. The data and the power requirements are things that we'll test at the FieldComm group. Intrinsic safety certification will come from somebody, FM, CSA, to whoever. So but the key here is that the APL hardware could, or in our case, the APL hardware will support HART-IP, but also could support other protocols. Based on power, based on memory, based on processing, it could even support multiple protocols and multiple things on the single implementation. Or it could be a platform where you have a single processor, a single PHY, a single intrinsic safety circuit setup, and you take that and you say, okay, now I'm going to flash it for HART-IP, and now I'm going to flash it and it's going to be some other protocol, but that hardware remains the same. Maybe I plug a display in it sometimes I don't have a display, sometimes I add a particular sensor, sometimes I add a different sensor, but the core hardware might remain the same for all those different products and different protocols. So in that case, you can send that hardware to the FieldComm group, and we will test and register the Ethernet-APL. We will also test and register and issue a HART registered certificate. So of course, to get HART registered, you must be the HART-IP product that has the full proper implementation. And that includes that your APL hardware is compliant.
Okay, good. Okay, we're going to come back a little bit more to conformance and what's required to for a supplier to do testing and things like that for their APL instruments. But I want to shift gears just a little bit because you touched on something that was raised in one of the earliest questions that we got during this session. And it's something that is always I've always kind of wondered about, but it doesn't seem like anything that current hardware suppliers, current instrument suppliers do regularly. And the question is, does it make sense for a single device, let's focus just say on the hardware, to support, say, both HART-IP based APL and Profinet-based APL? Or when people support HART-IP in the first phase and then Profinet in the second phase? I'd imagine these would be two different models of the device, one HART-IP based, one Profinet based, but couldn't they be the same device and maybe just reconfigured slightly different? One question is, first question is for you, Sean, from just purely a technical standpoint, and then the second question is for kind of Jose and Matthias from an actual product development standpoint. Do you see differences in these types of products that are essentially supporting the same physical layer with just a different software architecture? So Sean, you go first, then Jose and Matthias, please.
So the protocols are not going to have a change requirement in the hardware. So you could have a single device with, let's say, 2 ports. You could have 2 outputs, and one could be talking Profinet, and at the exact same time, the other one talking HART-IP. And you could have a 3rd port talking Ethernet-IP and a 4th port talking OPC, all on the same device. But there's going to be a limit on the processor and the memory and what it's going to take to do that. So most likely what you'll find is the device will have a single port. It's probably going to support a single protocol over that port at any one given moment. But there is only the limitation of how much memory that you would have on the device as to whether or not it contains a single image that can do multiple things and you flip the software bit, or if it contains multiple or a single image that you then have to reflash it to do different protocols.
Okay, that's a good answer, Jose. Matthias, what do you guys want to say to that?
I will pass on to Matthias, and now we need my camera and Matthias, which is the camera not working. Yeah.
So perhaps we can agree with this. You can build up one device with one hardware, and you have to look at the application. If you have fast application, then you need fast communication also, and it depends which communication system you will using then in this case.
Correct. But we can say then also that you don't need to modify the hardware, as Sean has said, and you could have the same device, the same hardware, and only then changing then the protocol on the device. For the vendor, for the one who manufactures, are two different devices. One with Profinet, one with HART-IP, as example, protocol. But in the device by themselves is exactly the same. The only thing which is changing is the protocol, and could be in the production just a configuration, or a design of the customer, which normally will not make sense, but could be technically also a configuration to change from HART-IP to Profinet, as example. Make no sense, but it's technically possible.
Okay. It may make sense from a stocking and an inventory standpoint if you've got 1,000 instruments across several systems that use different protocols. I don't know, maybe.
Yeah, the only thing that the one who will use it have to take care which protocol this device will have.
Of course. Of course, but that might be cheaper than buying an extra 1,000 instruments for that other protocol. I don't know.
Correct. Correct.
Okay, so a kind of a similar question is, I think it's clear, but we want to state this explicitly that for a HART-IP APL instrument, there is no need for a 4 to 20 milliamp current loop. So the instrument would probably not have a 4 to 20 milliamp current loop on it. Although I suppose there's no reason why somebody couldn't design an instrument that has both a 4 to 20 milliamp current loop for maybe handheld configuration out in the field, because there's so many people that still configure instruments that way and operate. But from an operation standpoint, you use the APL stuff. Is that possible, or is that not even practical?
I would say first, with Ethernet-APL, this is no need for the 40 till 20 milliamps, no need. And to be honest, I don't think this will make sense in the most of the applications. Normally, you are going in an environment where you have a digital communication, so base, and it will not make sense to have normally to have a additional output than from 40, 20 milliamps. Normally not.
Anybody want to add to that?
Nope. Yes.
I would just say I agree that it could be done. If we talked earlier about adapters, right? The idea of going from a 4 to 20 milliamp existing device into an APL device, or a small I/O, where you maybe have a collection of devices that are 4 to 20 milliamp that you want to bring into APL. That would be one possibility where you may have 4 to 20 milliamp on a device. You mentioned the idea of like a maintenance port, like we have on a wireless HART device. That could be possible, but what you have to remember is now you're adding a current loop chip, and you're adding some interface, HART modem chip, excuse me, for that interface, and you're adding an additional component to your design, and you still have to stay within your power budget. But that's to Jose and Matthias and their team to that you can work out those kinds of details, right?
Yeah. Okay. Got it. So I was very intrigued by the section that you did, Jose, where you guys talked about the choice of components between the MAC-PHY and the microcontroller, and whether you pick kind of a heavy-duty MAC-PHY combination with a lighter microcontroller, or a separate physical layer chip with a heavier-duty microcontroller. And I guess from the perspective of the instrument supplier, who has heretofore only done 4 to 20 milliamp instruments, is there any kind of way that you might want to break that down depending on, say, the instrument that you're making? Like maybe for a pressure transmitter, it makes sense to use one implementation, but for maybe a Coriolis flow meter or some heavy duty instrument, it makes sense to do it another way. Is there any rhyme or reason for why somebody might make a choice in one direction or the other?
Yes, but what you mentioned is correct. The Coriolis flow meter have a lot of parameters and a lot of calculations. So it's a lot to do. So the microprocessor will be a very heavy one, a very expensive one normally. But it could be they separate the process PC board from the communication one for the modular concept. And in this case, for the implementation of the APL, for the APL communication, you will not need necessarily a very powerful microcontroller. So a heavy device with a lot of parameters. Could be for the APL implementation, they don't need an additional heavy microcontroller. For a simple pressure transmitter or temperature sensor, you will not need necessarily only for this task a powerful microcontroller. This will be done enough, a simple one. The topic is if you are having now Ethernet connection, not anymore the analog information of the 4 till 20 milliamps, and you have now the capability to transfer more information, like for predictive maintenance. Could be the vendor will say, oh, now I could implement that and that and that and that in this simple pressure transmitter or temperature transmitter, and implement additional benefits for the customer. And it could be you go down from a very simple one to a very heavy one, microcontroller. So at the end, it's depending on the application that you will have, the benefits, the additional benefits you have to give or you want to give them to your customers, and architecture that you have for your devices.
Okay. Yeah. Would either of you other gentlemen like to add anything to that?
Mm-hmm. Matthias, something additional to add?
No, thanks.
No? Oh, I spoke too much. Matthias has nothing to add.
Well, what I think I heard you say, and just play this back to me if I got it right, what I think I heard you say is that the actual microcontroller PHY MAC combination that's needed just to do the communications portion doesn't have to be that heavy duty. It can be a very lightweight microprocessor. So then, if your instrument itself is a heavy duty instrument, then you may have a choice of using a bigger microprocessor that's doing both the comms and the instrumentation functions, or maybe you have two microprocessors, one that handles the instrumentation function, one that handles the communications function. And it's up to you as a supplier to determine how you want to architect your entire system to maybe take advantage of that. So maybe if you're doing multiple instruments of varying levels of sophistication, you may use the lighter weight communications processor across all of those products, and then scale in the instrumentation function depending on the complexity of the instrument you're creating. Got it.
Exactly, Paul. And that's okay. It's not only done the single optimization of the cost of a PC board for the communication is the complete product family. That's what you want. Exactly. The modularity. As it's not easy. Sometimes we have the feeling at the end for the one who produce it. At the end, this is like a philosophical decision.
Yeah, sure. Well, it's a product line management question, basically.
So,
yeah. All right. So we've got a couple more coming in here. This one is going back onto the conformance and registration for Ethernet-APL devices. And I think, Sean, think about the answer here for this one, because it's I think this is a question that we're going to get more and more as instrument vendors start creating APL instruments with whatever automation protocol they're going to need. They're going to need to acquire some equipment, acquire some test tools, acquire some systems that they don't currently have. And I think this question really says, besides the test tools provided by FCG, so if we provide a HART test system or HART-IP test system, what else are you going to need to make sure that you can submit and register and create a conforming APL product? And do you have to get a lot of expensive equipment, or can you rely on something like FieldComm Group or another test lab?
Yes. Okay. So there's quite a bit there. So I'll start at the end and work backwards. So can you rely on FieldComm Group or other test labs? Yes. So the short answer is that, absolutely you can send products. FieldComm Group will do physical layer testing, and we can do physical layer assessments. There are also other folks that can do testing. I'm sure if you work with Jose and emBex, I'm sure they're equipped to do testing there as well. So if they're working with you, they can probably generate the reports and the requirements for you as well, and or working with other development partners, the same thing there. So in those cases, you wouldn't need to acquire the equipment. If you do want to acquire the equipment because you're going to do your own testing, or because you're going to have a large number of products, or for whatever motivation you may have, there are really, there's, I would say, 3 options there. So one option is that you could buy a solution from one of the 2 vendors that are out there today. So the UNH-IOL solution, which has its own equipment and its own requirements. Then you also have the Telebyte solution, which has its own equipment and its own requirements. Or you can use the equipment list that we've provided with the with some very specific models and specific types of equipment, that with that type of, or with that list of equipment, you could implement the testing of the product and do so in a manual way without using the commercial solutions. I guess really, and there's a 4th option, that you could develop your own test rig and your own test tools to test. And I can say that from my experience of working with the companies that are engaged in APL to date, that the answer is all of the above. Companies have done all those answers, everything from building their own custom setups to using tools that they just buy something from a vendor and it comes in a package. As far as pricing goes, yeah, this is, you know, the tooling, when you look at scopes and you look at AWG and you look at power supply, and if you assume you have 0 to start with, then you have to acquire a digital multimeter, you have to acquire a scope, and you have to acquire the function, or the AWG and the power supply. Each of these items, you know, when you start adding it up, I mean, you know, you could spend, you know, 50, 60,000 US dollars to acquire that equipment, depending on what you acquire. And of course, you could spend a lot more than that. You could possibly spend less than that. But it's just to give a guidance. Like I can say that FieldComm Group, we already have programmable power supply, we already have an oscilloscope, we already have, you know, an AWG arbitrary waveform generator. You know, these are things that we have in our lab because of working on Foundation Field Bus and HART in the past. So some of these things you may already have.
So you mentioned that there's a list of equipment with model numbers. Is that in the engineering guidelines, or is it in?
No, it's in the equipment list, which is published on the FieldComm Group website.
Equipment list on the FieldComm Group website. Okay, got
correct.
Got it.
Now, I would say that, you know, before you go and buy everything in the list, you know, talk to us, because you don't need everything in the list. There are options, right? So there are, for some of those items, there are choices. And so you can definitely speak with us and we can give you some guidance there. But also keep in mind that if you're going with a solution, like if you want to work with a vendor who's providing test tools, then you would want to also work with us so you understand which of the items to acquire depending on which path you want to go down. So, you know, if you bought everything on the list, you would have redundant items that are overlapping. And so you don't want to just use the list as a shopping list.
Okay, good enough.
List with any options.
So
that's the great thing, is there are a lot of different options here.
So this last question, I actually think you guys might have a little bit of fun with this question, because it could be so exhaustive. But the question is, if you're going to certify an Ethernet-APL and HART-IP device, including intrinsic safety and meeting power requirements of APL, how many certifications are needed, and which bodies are going to issue those certifications?
You need 2.
Really?
Yep.
Really?
You need the certification from an intrinsic safety body.
Okay.
And you need the certification from the FieldComm Group.
Okay.
Those are your base requirements to achieve registration.
Wow, I thought there'd be a lot more than that, but go ahead. Jose?
I can confirm that. So
it's
topic.
So an intrinsic safety body is like TUV or somebody.
TUV, CSA, FM. There's a whole number of alphabet soup organizations that do that.
Got it. And then you come to FieldComm group to get your protocol and to get
the APL.
The conformance for the APL.
Now, there's the thing that we'll often that I want to emphasize here is that we have experience with HART and Foundation Field Bus in this collection of folks that are participating today, and we all know that EMC testing in the past has been, I would say, rather open and not very tightly defined. For APL, the EMC tests, we have requirements. We have industry, whether you're marine, if you want to do industrial, if you want to do automation industrial and follow the NOMORA EMC requirements, right? All these are different layers of requirements. But if you look at EMC in general, we have a set of requirements that we have to meet for government standards and to be able to ship products on a global basis. But for APL, we also have a specific set of EMC test setups and requirements that have to be run and fulfilled. Those tests have to be conducted in the way they're described. They have to be passed. They are reviewed as part of the registration process, and they are, I would say, in addition to what we're used to in the past. Those specs, the EMC specs from IAC have already been updated with this information, but you can also look at kind of the change bars, if you will, for just the APL portion through FieldComm Group. And those tests, a lot of companies to date have done their own EMC testing, and sometimes they outsource it. So, to your question about what agencies are involved, again, if a company has on-site EMC lab and they're qualified to perform EMC testing, then they would do these tests as part of their development. If they are not in that area currently, then they would either need to become proficient in that area, or they would have to outsource that to a third party.
Okay. Perfect. All right. Well, this. Thank you, gentlemen. This concludes the questions from these two most recent segments. At the outset, I kind of mentioned to you that we have about a half a dozen development partners that have helped us put together some of this content. Thus far, you've only heard from a couple of them. To kind of close out what we were calling the morning session initially, we have some videos, some promotional videos for all of our development partners and folks that have helped us put this together. We're going to roll that next, and then we're going to be on break until 10:15. We come back, and we'll start the real heavy-duty, detailed discussion topics. So thank you for sticking with us. Listen up on this next segment. It should be 20 minutes to a half an hour, I would imagine. Then you get a little bit of a break. So okay, thanks
Thanks a lot. Bye-bye.
Yep.
Have a nice day.
Hello everyone, my name is Arnold Offner. I'm the Strategic Marketing Manager for Process Automation Infrastructure here at Phoenix Contact. And today I'd like to introduce you to a brand new product that we are launching at AKIMA 2022, a 24-port Zone 2 Ethernet-APL switch. What makes this switch so interesting is of course that it's designed for intrinsically safe Ethernet-APL field devices. My engineers, of course, always keep reminding me it's not a 24-port switch. It actually is a 30-port switch. And so if I remove the cover at the top here, you will notice some additional connections. Firstly, we have the trunk connection. We then have also separated here the auxiliary power connection, and we also have a cascade connection, which allows me to actually add a second Ethernet-APL switch, so you can connect up to 48 Ethernet-APL field devices. The product can be mounted either on DIN rail or be panel mounted. For more information, visit our website at phoenixcontact.com/Ethernet-APL.
Smart manufacturing, intelligent process automation, and sustainable buildings are supercharging their operations with access to new data from remote field or edge devices. This increases productivity and operational flexibility, drives asset utilization, and reduces energy consumption. Seamless Ethernet connectivity from the edge to the cloud is now possible with 10-base T1L technology. It provides long-reach, robust Ethernet connectivity with power and data over 1 kilometer of single twisted pair cabling. In addition to measurement data, it gives direct access to configuration parameters and asset health information. Unlock your edge device's data, simplify your communication networks, and optimize the commissioning process with Ethernet. Analog Devices' unique portfolio of 10-base T1L solutions enables flexible system architectures while optimizing the system power budgets. For 10-base T1L sensor or actuator nodes, Analog Devices Mach-PHY provides lower overall system power consumption. With simple Ethernet to SPI connectivity, it enables the use of processors without integrated MAC. For 10-base T1L field switch designs, Analog Devices' 10-base T1L PHY and system-level evaluation platform enables 4 10-base T1L spurs, gigabit trunk, and the potential to cascade multiple stages for higher port count switches. Proven, robust, and fully tested for auto-negotiation mode of operation with a reach of 1.7 kilometers, Analog Devices solutions are designed to support intrinsically safe and Ethernet-APL applications in process automation. Seamless access to data with 10-base T1L technology from Analog Devices will create more efficient carbon-neutral buildings and more flexible, intelligent process automation systems. These solutions are available now.
At emBex, we develop your product or system from the initial idea to series production. Our headquarters are located in Freiburg, a wonderful city in Germany, at the border of the Black Forest. Since 2001, we have been developing great products for the automation industry, with more than 200 highly qualified engineers and technicians, with industry-specific know-how and extensive experience in the development of industrial products including explosion protection, cybersecurity, and functional safety. emBex is the first and only company worldwide to achieve maturity level 5 for the product development process of functional safety products. emBex is a one-stop shop for the development of industrial products and systems. From the moment the customer's idea is born, design and engineering, all the way to the transfer into production, certifications, and lifecycle management. emBex is a leading development company. We develop products for world-class automation companies. 8 of the global top 10 automation companies are already emBex customers. emBex competencies and services include software, hardware, mechanical engineering, and a strong system engineering competence. In most European wind turbines, you'll find emBex expertise, like the pitch control with energy storage, and the functional safety stop using rotor blade pitch control. We develop complete systems and take responsibility for the interfaces between all disciplines. As part of our wide range of development services, we also offer housing designs for protecting your electronics. We synchronize the hardware and electronic development teams to produce explosion-proof enclosures, protection against environmental influences like moisture and splash water, vibration and shock resistance, thermal installation, EMC and shielding technology, radiation protection, and safety. We also develop products and systems for hazardous environments. We are the leading development company in Europe that offers expertise for intrinsically safe electronics, pressure-resistant housings, and explosion protection against gases and dust. emBex provides an optimized and smooth development process for ATEX and IEC compliant products. The development of functional safety industrial devices and systems is one of our key competencies. emBex is the first company worldwide with maturity level 5 for the development process. That is the highest maturity level, which is the result of more than 20 years of experience with a large number of successfully implemented functional safety products. Today, cybersecurity must be considered as an indispensable design goal in the development of networked industrial products. emBex is a leading development company for embedded cybersecurity and offers a comprehensive range of services, from the idea and development of the product lifecycle, including comprehensive PSIRT services. The certified emBex development process covers both safety and security requirements. We develop approval-ready products for international markets and carry out type testing to check and compare with applicable standards, directives, and specifications. Our developers are in constant contact with all the well-known accredited inspection bodies to prepare and support approvals for our customers with documented product tests. The certification of products is as much a part of our daily business as the development of innovative products and systems for the industrial automation market. We will be happy to support you with your next development challenge. Just contact us. emBex, engineering the embedded world.
Founded in 1985, Relcom has been providing innovative and reliable solutions for industrial applications. Located outside of Portland, Oregon in scenic Forest Grove, Relcom's close proximity to a hub of Northwest technology development means quick access to complementary services. Relcom has a long history of designing, manufacturing, testing, shipping, and supporting high-reliability industrial products.
Relcom is an industrial electronics design and manufacturing company. We've been doing this for over 30 years, and we design and manufacture our own products as well as products for other companies. Relcom focuses on the process control industry. This is an industry that requires the plants to run 24/7. It's a very challenging industry to provide products for. In a process control plant, downtime can cost a lot of money. It can be tens of thousands or even millions of dollars a day. Process control plants also need to be able to operate for decades. Continuously needs to run reliably, 24/7. The types of plants that are included in that industry might be oil and gas, pharmaceutical, chemical, wastewater treatment, and nuclear power plants. In this industry, you have to deal with harsh environments, low and high temperature ranging from minus 40 degrees C to plus 70 degrees C typically, or moisture being present. Corrosive gases can also be a problem. The customers require, even in these harsh environments, that the products be very reliable. They need to have a long product availability. So not just produced for a year and then next year it's something new, like in a consumer electronics, but for 10 plus years, the products need to be available as replacements. The equipment is often installed in hazardous areas. In these areas, explosive gases could be present, and the equipment must not produce heat or a spark that could cause an explosion that would hurt people or damage the plant in any way. Relcom has a lot of experience dealing with products that are installed in harsh environments and hazardous areas. We are familiar with and have gotten certifications for intrinsic safety, increased safety, encapsulation, and others from IEC EX, ATEX, the Chinese CCC certification, CSA, and FM. In order to manufacture our products to these hazardous area certifications, we have to maintain our quality management system to the ISO IEC 80079-34 standard. Relcom has also been approached by companies that need to redesign aging products. We recently had a product that was over 25 years old and facing component obsolescence issues
was for a temperature multiplexer system. The customer wanted to improve the design, bring it up to date, and add some features as well. And we took on that project, and it is now in production. We believe it's important to maintain contact with the customers and end users to have a successful product. The end users and customers have expectations, and we want to make sure we meet and exceed those expectations. We often will go to an end user site in order to get that input and make sure that the project will be successful. As a smaller company, Relcom can be more flexible and agile. In addition, we're willing to take on projects that a larger company may consider below their waterline or just not big enough for them to be interested in.
Smart Embedded Systems has been involved in the HART technology for more than 10 years. We are focused on fundamentals of engineering a product. This includes the hardware design, the firmware development, and software development. We have done work for several leading field instrument companies. We also have worked with multiple semiconductor vendors. Texas Instruments is one of our design partners. We have done multiple HART reference designs and firmware development for them. We also have done designs for other transmitter vendors. SES is the first company to implement a viable loop-powered high-speed HART modem and a transmitter. We have multiple patents on the efficient implementation of the modem algorithms. We have a compact modem module you can easily solder to your existing instrument and verify the viability of the high-speed HART in your application. We also have a companion USB modem. We developed the HART-IP gateway to complete our HS HART ecosystem. This HART gateway supports both FSK and high-speed HART field devices. We have been shipping our HART-IP gateway for more than 2 years. We also support 4, 8, and 16 channel configurations. We also have been developing HART-IP 2.0 product as the specifications are currently evolving. We are prototyping and testing HART-IP security functions as the standards and test plans are being developed. We are using our experience in the HART-IP technology to enable the HART-APL designs, which is IP-based. Here we bring forth our expertise in electrical design as well as firmware expertise in IP networking. We want to enable our customers to be successful and help them speed up their time to market. When we offer a solution, we provide solutions that cover all aspects of the development. As you see here, we offer the APL to Ethernet switch that will make the development flow easily and provide an end-to-end connectivity in a lab as well as production setup. How can SES help you? We can significantly shorten your learning curve in moving from HART to HART-IP APL. We will handle all the evolution and specification changes and keep you up to date. Leverage our experience and knowledge in your design. Please contact us for any further information regarding our technologies and design offerings. Thank you.
Hi, I'm Christian from Softing Industrial Automation. I'm pleased to introduce you today to our offerings for networking a wide variety of automation components. You will see a brief overview of our entire offering, followed by our specific portfolio for networking field devices and control systems.
In today's global economy, industrial production environments are faced with various challenges. These include individualized products and higher efficiency in the use of energy and resources. Accordingly, value creation processes need to be optimized based on different criteria such as flexibility, costs, and resource consumption. The key to this is digital communication. Softing provides essential products and services that ensure a boundless data exchange between machines and facilities. The effective integration of automation in higher-level IT systems generates valuable potential for optimization. Networked industrial facilities and production processes demand an integrated digital communication of all components. You require solutions that implement future-proof networking across technical boundaries. We at Softing take on your specific tasks and ensure a real-time digital data exchange in the field. To establish an interoperable communication of your facilities, we provide interfaces, gateways, and associated software tools. We empower your devices and networks with relevant field bus and industrial Ethernet connectivity. That's what we call data flow. Consistent digital communication in the field sets the conditions to access relevant data for subsequent processing and analyses. You require vertical data integration across levels and technologies. We at Softing meet your needs by providing products for a highly functional and secure data exchange, all the way from production to the IT level. To achieve an effective and flexible distribution of data for higher-level processing, we bridge technological gaps by providing the required connectivity on-premise or into the cloud. We call this data feed. Plant network communication failures provoke costly production downtime. Softing supports you in establishing and maintaining reliable communication and robust networks. The data exchange in your production lines is strengthened and safeguarded by Softing monitoring solutions and troubleshooting tools. Our term for this is data check. As a recognized expert for digital data exchange in industrial applications, we help you in establishing an integrated automation. This is the foundation for a highly flexible and resource-efficient production. Softing provides you with data connectivity, network health solutions, and process insights. Optimize. Networked industrial facilities and production processes demand an integrated digital communication of all components. You require solutions that implement future-proof networking across technical boundaries. We at Softing take on your specific tasks and ensure a real-time digital data exchange in the field. To establish an interoperable communication of your facilities, we provide interfaces, gateways, and associated software tools. We empower your devices and networks with relevant field bus and industrial Ethernet connectivity. That's what we call data flow.
Thank you for watching these introductions. An important part of Softing's data flow portfolio are Ethernet-APL products such as our field switch and the new core module APL. If you are a vendor of hard field devices, this little piece of electronics will bring your devices the APL connectivity they need in extremely short time and with very low development efforts. We will have more on this helpful little module later. I hope you'll join us again. Thank you.
Hello everyone, welcome to the new technology booth of SUPCON. Before I start, I'd like to give a brief introduction of SUPCON. SUPCON is a company who has dedicated to process automation industry for almost 30 years. And after this year's development, SUPCON has now get very good reputation from the market and the client. As for our core product, DCS, we have continuously kept the #1 market share in China market for the past 11 years. And for last year, we have got more than 33% of market share in China. And for the other product, SIS system, we have got the #2 market share in China and more than 25% market share. As for our global presence, our business footprint now is covered more than 50 countries. The head office of SUPCON locates in China, and we have set up 3 global service centers, 1 in Singapore, 1 in India, and 1 in Saudi Arabia. With the support of the service center and the regional offices, we can provide a service and the fast response in the local market. Now, I'm going to give the introduction of APL-based advanced industrial network solution of SUPCON from the 3 aspects. 1 is the definition of APL. 2 is the product and solution. 3 is the highlights and value of our solution. As we all know that, in year 2021, the international standard for APL has officially released. Ethernet-APL is a 2-wire Ethernet physical layer especially suitable for the process industry. The power and the data can be transmitted on the same 2 wires. The transmission rate of APL is up to 10 Mbps, much faster than HART and Fieldbus, and the maximum distance is 1,000 meters. Actually, APL defines the network architecture of trunk and spur. Like what we can see here, the orange cable represents the trunk, which connect the APL power switch and APL field switch. And the blue cable represents the spur, which provides a connection between APL field switch and APL instrument in the field. SUPCON is available to provide the total APL solution to the customer. The system includes APL power switch, APL field switch, and the APL field instruments. And we can see furthermore, we can also provide the APL Smart EIO and the APL wireless gateway for the traditional instruments, wireless instruments access into the APL system. And we can see here, this is the 12-port APL field switch, and it supports 2 trunk ports and 12 spur ports. The 2 trunk ports can be used for redundancy, and the field switch is integrated with the junction box, which has the IP66 protection level. It has 12 spur ports, the same interface quality as the field bus junction box. With IP66 protection, wide working temperature range, and the intrinsically safe explosion certificate, it can be used in Zoom 2 directly. This is 8-port APL power switch. In this power switch, it has 2 fiber and 2 network cable uplink. The 2 fiber and 2 network cable can be applied for redundancy. Besides, the power switch has 8 trunk ports. Each port can provide 57.5 watt power supply. It can be used in cabinet room and Zoom 2 both. And we can see here, this is the APL instrument. Here is the APL pressure transmitter, and here is the APL temperature transmitter. Now, the protocol running in the transmitter is HART-IP. So existing intelligent device management system is suitable to these APL instruments. Well, like what we can see here, SUPCON APL solution supports ring topology and also the star topology, and also redundant and non-redundant network. With the network intelligent diagnosis platform, we can realize auto-recognized device online and offline status, and also auto-draw system network topology, and also the diagnosis on network devices and link quality. Distributed and flexible deployment combines power supply and data communication on 2 wires can save a lot of cabling and deployment cost, and also can shorten the commissioning time for the new project. So actually, now we can see that SUPCON APL solution has many other features and highlights. If you are interested in SUPCON APL technology and the solutions, please feel free to contact with us. Thank you so much.
Connectivity is the backbone that keeps the entire industrial ecosystem together. Data generated at the field level are analog signals, which, when traversing through to the enterprise level, transform themselves into diagnostics, insights, and inferences. This exchange and metamorphosis of data from field to cloud is facilitated by specific connectivity solutions. That is, communication protocols and physical mediums. Protocols like Modbus, HART, Profibus, Ethernet-IP, IO-Link, etc. have primarily fulfilled the connectivity needs of the OT world. But the growing emphasis on automation and digitalization has necessitated speed, determinism, intrinsic safety, and interoperability as critical aspects for having an effective OT network. With emerging technologies like 5G, TSN, Ethernet-APL, and OPC UA-FX, the connectivity across OT networks is already seeing a huge shift. Edge computing is already a preferred converged solution, processing and relaying diverse sets of field data directly to the cloud, flattening the automation pyramid. Just like the field layer, OPC UA enables interoperability and scalability beyond the edge into the IT world. OPC UA is tying all the layers of automation pyramid into one common connectivity fabric. Well, there are innumerable protocols that can be fit for different purposes. What is your connectivity need? What is your choice of physical medium from serial to Ethernet, to wireless flavors to cellular? How do you wish to enable your industrial asset? Hardware or software for connectivity? Do you aspire to make standards-based solutions? Consult with us and make the right move towards digitalization.
Okay, thanks to all of you in attendance today, and also an incredible thanks to the FieldComm Group member companies that have helped us put together this event. We have over 200 people registered for this workshop, and according to Stephen Mitchke, who is actually manning the control room behind the scenes, many are in attendance now. As I outlined at the outset, the initial sessions today were intended to first provide you with a baseline on the core technologies of Ethernet, Ethernet-APL, and HART-IP, and then give a little more of a deep dive into HART-IP security, what it takes to convert a HART instrument into a HART-IP with APL instrument, and what we will be looking for at FCG as your products are submitted to us for conformance testing and registration. We closed out the early sessions with brief capabilities overviews from the partners that have helped with this event. While some of these partners focused on their development services efforts, others highlighted product offerings that they've created for this emerging market. What's important is that all are currently engaged in developing products for Ethernet-APL, and many have prior experience in HART-IP. All of these partners have significant OEM product development capabilities, so please reach out to them as you begin to educate yourselves about HART-IP and Ethernet-APL. You can find their contacts on the microsite. Speaking of education, the folks here at FieldComm Group also had to go through an education process when we started working on HART-IP at the field device level, as well as Ethernet-APL technology over the past few years. Back around 2018, 2019, don't quote me on the exact year, We felt that we would need to provide development tools to our members to help them educate themselves on HART-IP and Ethernet-APL, as we were even then convinced that over time these technologies would become very relevant in the process automation market. Of course, at that time, components for Ethernet-APL were not yet on the market, and prototype hardware was only available to the 12 industry partner members of the Ethernet-APL project. But we recognized that with Ethernet-APL being just a physical layer, the bulk of the development effort would end up being centered around software. So to make things simple, we invested our efforts into creating a development platform centered around a commercially available, off-the-shelf hardware platform, the Raspberry Pi. Now fast forward to 2022, hopefully post-pandemic, and we find ourselves in a supply chain crunch, and what was then a readily available development platform is now in scarce supply. Who knew? But the software is still relevant, and some of it has already been described in prior presentations by Wally and others, but I digress. Anyway, in 2020, we started marketing the Raspberry Pi platform as a sort of get-started kit to help developers learn about the technologies. In addition to the Pi, the kit contains a HART-IP server, that's the software that goes in the instrument, a HART-IP client, the software that a user uses to connect to and operate the instrument, and a sample application. In this case, it's a flow transmitter application to provide a real-world use case. Now, today, a number of members have used this kit to educate themselves on the technology, but we all know that a Raspberry Pi is not an industrial platform, and also the kit did not include an APL interface since at the time none was available. So last year, we considered creating an embedded development kit and offering it to the memberships. Many of the development partners on this call helped us work out the details of what might be required for such a kit, and I hope that our conversations may have helped them with their own product offerings. But ultimately, because of multiple geographies, familiarity with different tool chains, component availability, cost, and business model, we decided to refocus our efforts on education. And the result of that decision is this workshop. But the software that has been created for FCG's Raspberry Pi development is still important. And the learning curve that FCG has gone through in our own tool development efforts is still relevant. And this leads to the content of this second set of sessions. The first session is led by Tim Johnston. Tim is a senior developer here at FCG, and he has been instrumental in the creation of our HART-IP developer tools. The topic that he is going to focus on is, in our mind at least, one of the most important topics for you as member companies and potential product developers to concern yourselves with. Tim is going to walk through a demonstration of a product that we call the Portable HART-IP Client. This piece of software is important because it forms a key portion of the functionality suite that we will use to validate your device for conformance with the HART-IP standard. Tim will first walk through an overview of the product and then close with a demonstration of how it is used to implement a specific HART-IP test case. When Tim is done, we'll take a short break and answer some questions. Afterward, we've asked several of the development partners to speak. Some will discuss specific aspects of HART-IP and Ethernet-APL design. Others will highlight their specific OEM product offerings, and at least one will discuss their early experiences in creating Ethernet-APL products. These presentations range from 5 to 25 minutes, and we will break after each group of 3. Finally, Heather will give us a brief overview of the microsite. We'll handle final questions and conclude the workshop. So without further ado, here's Tim Johnston.
Today we have a demo of the portable HART-IP client. We'll cover an overview of what the client actually is. We'll walk through operating the client, its various features. And lastly, we will cover using the client in a conformance test for one of the HART-IP security test cases. FieldComm usually produces client software for its various protocols. These clients allow the developers to communicate directly with devices. They are reference implementations helpful for the developers of host systems, and they are not suitable for use in production environment. Some may remember that we included a Windows client with the first release of the HART-IP developer kit. With this release, we are including a new client called the Portable HART-IP Client, PHIP, which I am demonstrating today. It supports version 2 of the HART-IP protocol, which uses TLS encryption with a pre-shared key or a username password. This new client will support both protocol versions 1 and 2. With it, device developers can work directly with secured devices, and developers can use it to manually run the security test cases which are not yet automated. The client includes a simple application that remembers the security credentials for the devices on your network, freeing the user from this tedious task. This client was designed to operate in the major operating systems, Windows, Mac, and Linux. We have examples of this client running in all 3 operating systems. The one we are delivering with this kit is a Windows client. It requires Windows 10 or later and a 64-bit operating system. The other element of portability is the user interface, which runs in a web browser. Strictly speaking, this client is a server in itself. It is a client of HART-IP devices, and it serves as the human interface through a web browser. What else does it have? This client uses the new device info technology to translate binary HART messages to and from human-readable formats. To enable this, the client keeps a database of device info files, 1 per registered EDD. A device info file can be created for any registered HART device that has a registered EDD. If the device info file is available for a device, this client will produce human-readable output that is specific to the device, using its specific labels, status codes, and process variable definitions. If a device info file is not available, the client will use a universal device info file, which provides the best human-readable output possible without an EDD. The device info tools ship with the FDI IDE, so all developers can create these files. This is the standard configuration for testing HART-IP version 2 devices. The physical layer may be APL or 4-wire Ethernet. HART-IP devices interoperate because APL also uses the IP transport layer. A particular device will support either 4-wire Ethernet or APL, but its software depends only on the Internet Protocol software stack. This configuration is described in detail in the FieldComm Group publication, HART-IP Registration Procedure. Let's get started by opening a browser on our PC and setting the IP address in its address bar. In this video, I have the address set to localhost because I have the browser running on the same computer with the portable client service. Connecting from another computer to the portable client, you would simply put the IP address of the client into the address bar here. The number 5005 after the colon is the port number that we connect with. This portable client uses port 5005. When open to this address, the browser will show a settings button near the top and a connect button to the right in the menu bar. We will click the settings button to configure the HART-IP connection to our device. Here we see our configuration information. We can select either version 1 or 2 of the HART-IP protocol
It is version 2 that offers secure operation. If we select version 1, then the Connect button will give us the connection dialog for HART-IP version 1. It shows the information required for an unsecure connection. You can connect to the device using its host name or its IP address if you know it. And you have a selection of UDP or TCP protocols. Port number 5094 is the well-known port for HART-IP devices. I will cancel this dialog and change to version 2 to connect securely. This dialog has additional security information that must be entered: a username and a 64-bit pre-shared key, which is entered as 4 sets of 8 hexadecimal characters. Shown here are the default settings for the first connection to the device, which is always the security manager. Slot 0 is dedicated to the security management function. The other slots are available to the device's other clients. This business of individual users having unique keys for each device becomes complicated with more than one user. The Security Manager service, which ships with this client, simplifies this process for lab-scale operation. Click the Connect button to complete the connection to the device. With a successful connection, we get the device's information near the top and additional status information at the bottom of the page. Click the Devices button. Here we have a list of the connected devices showing useful information for each: long tag, device ID, HART version, and so forth. Click the Details button to interact with any of the devices. Along the top, you can see the session number and the long tag of the device. You also have a menu of options for interacting with the device using a wired PDU, a direct PDU, and so forth. Here you have the opportunity to enter a HART command. We will send HART command 0, which has no request bytes and returns the identity information for the device. Enter a 0 in the command field and click the Send button. There is a success indication at the bottom. In this case, the response code is 0, and you can see that that English translation is success with no error. A developer can view specific elements of the HART message by using the 4 buttons at the lower left. The Bytes button gives us the entire HART-IP message in hexadecimal. If you click the Header button, you will get fielded HART-IP heading information with meaningful names for the parameters. The Frame button shows the parameters that describe a HART message frame. The Body button shows named response fields with their values and hex values. Note that the text strings displayed in this client are drawn from the device info file, which is derived from the device's EDD, so whatever strings are included in the EDD for this device will display here. We are connected to a running device, so we can view its process variables in real time using the value chart page. Up to 4 process variables that are defined for a device will be displayed here. To show live data, we set the sampling interval in milliseconds and click the Set Refresh Interval button. Then click Start Burst to show the data values sampled at that rate. The next page is the Device Provisioning Wizard. This leads a user through the initial provisioning process for a new or factory reset device. The first step is to provision the security credentials for the Security Manager user. Here you can change the default username, password, or pre-shared key. This is highly recommended. Step 2 shows the results of Step 1. In step 3, the user can specify the device's host name. In HART-IP, the long tag and the optional process unit tag are also used as a device's host name. This means that the DHCP network name for the device is the same as the tag name, making it much easier to find a device on a network. Step 4 shows the results of step 3. In step 5, we configure the host name and port number for the syslog service. Step 6 shows the results of step 5. After this provisioning, the device is ready to be attached to the field network. This page provides convenient access to the audit logs for your device. You can view them in this client instead of using a separate application. The various connections to the devices are logged here. You can see the source IP address and port, the connection times, configuration change counter, and other useful information. This page retains the most recent responses from the device. Click the Decode button to review the contents of an individual message. The portable HART-IP client for Windows has a standard Windows application installer. A wizard leads you through the installation process. When you finish, there will be 2 new services running on your computer, the HART-IP Portable Client Service and the HART-IP Security Manager. These 2 will start whenever you start your computer. The installation is described in this FieldComm group user guide, HART-IP Portable Client for Windows Installation. One important use for the client is to run security-related test cases from the HART-IP registration procedure. These HART-IP test cases have no automation, and these manual procedures will be used until there are. Device developers will want to use this client to run these security test cases against their devices before submitting them for registration. We have selected Common Practice Test CAL 541, Managing Security Credentials, Test Case B, for this demonstration. This case tests the basic functionality for setting pre-shared keys on the device using Command 542. To execute the test, we will simply step through the test procedure using the portable client. We will be able to use the text directly from the registration procedure and copy-paste it into the client to simplify our effort. We are still connected to the client in slot 0, which is specialized for managing security credentials on the device. To begin, we will pull up the page that allows us to send messages directly to the device. The test specification indicates that we should use the direct PDU function to communicate these messages to the device. The first step in the test is to check for the correct response to a correctly formed Command 452 message. To do this, we will enter the command number, and then we will enter the parameters by copy-paste from the procedure document directly into the client, then click Send. This test case requires a success response. We can click on the body icon to see the human-friendly response information for our command. We use these values to verify that we have a success response. The next step tests that the device responds correctly when the key value is too short. The required response is unsupported key length with a byte count of 1. Our device passes this step. The next step checks that the device answers with the correct error response when the request has a bad CRC byte. The device answers correctly with the status, key change failed, and a byte count of 1. The last step in this procedure checks that the request is properly filled with null bytes. Again, the device answers correctly with client identifier or key value is not null filled and a byte count of 1. The device succeeds at all these steps, so it has passed test case B.
Okay, we've had a few questions stack up. We've had a few questions stack up in the interim, so we're going to fall a little bit behind and try and address some of these. Sean and I can handle most of them. It'll probably knock them out in about 5 minutes or so, and we can move on with the rest of the program. First question, which I'll handle, is what's the recommended body for IS? And are there any particular types of IS that need to be considered? And are IS standards the same as EMC? So the simple answer to that question is IS and EMC are not the same. IS is intrinsic safety. EMC refers to electromagnetic radiation being emitted from the device. So you need to go to two separate separate testing bodies to get this done. A lot of times the testing body you'll choose is dependent on where you're developing your instrument or the region that it might be sold in. So in the US, we have things like FM certifications for IS. In Europe, you have TUV and other organizations. A lot of the larger companies have their own EMC testing services, but there's a lot of labs all around the world that do EMC testing, and I would encourage you to go to them to do EMC testing. So that's the first question. The next question I'm going to throw over to Sean. Do we need to get intrinsic safety certification before submitting to FCG for APL certification?
No. The answer is no, you do not require that before you submit. However, it is required before you have your final registration certificate and listing on the website. So you could be in process when you submit it to us, but we will not issue the final registration with an APL product until you have that certificate.
Okay, so the next question is similar, related to intrinsic safety, and the question is intrinsic safety mandatory for APL or for HART-IP? And I think the answer to that is no, but please confirm.
So intrinsic safety is not required for HART-IP because HART-IP supports numerous physical layers. You could put it on single pair Ethernet, SPOE, formerly known as Poodle. There's a whole lot of specifications out there for 2-wire and other types of Ethernet, Wi-Fi and others that you could put HART-IP on. But Ethernet-APL is a specific physical layer. And for field devices in Ethernet-APL, you're either class 1 div 1 or you are zone 0 or you're class 1 div 2. And so the requirement for field devices is to have intrinsic safety on the field device.
Okay.
You think about our core market, process automation, makes a lot of sense.
So I'll take the next question. The question is, how is FDI connected to APL/HART-IP? And the simple answer is that FDI is an integration technology, much like FDI it's an integration technology, and you need an integration technology to integrate any type of device into any type of system. So it's independent of the protocol or the physical layer or whatever. So it's really kind of not an analogous thing. So our expectation is that all HART-IP devices will also come with an FDI device package, which happens to include things like a DD, which has been used for 20 years now to be the integration software piece between any type of instrument and any type of host. So there's really not a relationship between FDI and HART-IP or APL per se. Okay, one's an integration technology, the others are communications protocols or physical layer protocols. Okay. Next question is, The next question we're just gonna table. The question is there a commercially available HART-IP stack? And I think that what you've seen from some, or at least has been alluded to from some of our development partners, is that yeah, there are some commercially available stacks, but it's probably best to listen to those presentations which are coming up next, and I think you'll get a better answer to those questions at that point in time. One last question for Sean. Let's see. Yep, one last question for Sean, which is how do I get this portable HART-IP client that Tim was discussing in the last? It was a great demonstration, but we never described where you get it. So can you elaborate on that?
Yeah, certainly. So the portable HART-IP client can be found through 3 ways. One is through the HART test system license holders with the HART test system 3.8, which is the version that we're pushing out the door now. With that version, there is the portable HART-IP client as a download in your in the same folder where you find your distribution of your test system. Also through the HART-IP developer kit that Paul spoke about earlier, and that has been alluded to throughout the discussions. With that kit, you also have access to the portable HART-IP client. And so you get it through download from FieldComm Group. It's an installer. As Tim said, you can install it on different types of products or different types of operating systems. You could even run it on a Raspberry Pi, for example. But as I showed in the conformance portion, we install it typically on, for example, a Windows machine. Could even be a notebook. It doesn't have very much requirement for resources. So you download it from FieldComm Group, you install it on your machine, and you use it for testing or for exercising your product.
Okay, thank you. All right, so that clears out the backlog of questions, and now we are ready to move on. Thank you, Sean, for your time there. And with the way we're doing this is we're going to do these in 2 groups of 3. As I mentioned about a half an hour ago when we had that introductory video to this section. The first 3 up are going to be analog devices, emBex, and softing. They all have interesting things to say. I'm sure you'll find it fascinating. Stick with us after these 3 are done. The 3 speakers will stay online, and we will answer any questions that come up during the course of their sessions. And again, please throw some questions at us, because that's the way we keep this interactive, and we know you're listening. So without further ado, then let's turn it over to ADI.
Hello, my name is Michael Brychta. I am System Applications Engineer with Analog Devices. I'm going to talk to you about the 10BASE-T1L and Ethernet-APL solutions. First, some context about Analog Devices and our involvement in industrial standards. And we will talk about industrial connectivity, briefly look at the field switch, and then in maybe a little bit more depth into the field device. Then we talk about Analog Devices and what can we offer for the 10BASE-T1L Ethernet-APL solutions in terms of the products and tools. And then what we see as Ethernet-APL as emerging success of the technology. Analog Devices has been active member of the FieldComm group for many years. You may see my name on some of the versions of the physical layer specification for the HART communication. We've been contributing to the IEEE 802.3 and 802.1 standards for industrial Ethernet, and specifically for the 10BASE-T1L. Analog Devices, my colleague, co-presenting the call for interest, which is the start of the project, and we were going into IEEE through the full cycle of the 10BASE-T1L standard definition. And then Analog Devices is one of the partners of the APL group and APL activities. When we look at the connectivity in process control, in industrial process control, on the left-hand side is more traditional connection of the field devices at the bottom to the controller on the top. The connections are by principle very simple. There is a pair of wires all the way from the device to the PLC DCS. The challenge comes with a scale, because if there are many devices with the many field junction boxes and multi-core cables connecting those to the marshalling cabinets, with the scale come some challenges. And also, while the 420 mAh and HART is well established and proven technology, it comes to some limitation when it comes to speed of the HART, and also when it comes to seamless connectivity from the instrument up to the upper layer of IT technology or even the cloud. On the right-hand side, there is the APL solution to that. It's bringing Ethernet down to each sensor. Each sensor can have an IP address and connectivity seamless up to as high in the IT hierarchy as the plant manager is happy with, and happy to secure the communication. We talk about a little bit more about that. So it's APL solution. You can see that the network topology looks simpler. It's from the DCS through a power switch, connects through the trunks, and then individual spools to the individual instruments. So the network topology is easier to maintain and expand and so on. And again, it's seamless connectivity guaranteed by Ethernet. When you look at the field switch, and I'm representing a semiconductor vendor, so we have, of course, many components that we can offer to the field switch. Start with Gigabit Ethernet PHY. We see some of the trunks being realized by 100 or gigabit Ethernet, so we can offer solutions there. But then mainly we can offer solutions for the 10BASE-T1L connectivity down to the spools. We have 10BASE-T1L PHYs. We also can offer some help with the control of power going to the spools, not the intrinsic safe protection that is still going to be realized by resistors and xenodiodes, but to monitor the power delivered to the spools and short circuit protection, so we don't need to blow any fuses. We can offer solutions there. And we are working on some solutions on the switch fabric as well. You can hear from us on that topic in next while. Then if you look at the instrument, we look at the traditional 420 mAh instrument. On the left-hand side, sensor with some signal conditioning, A to D converter, small microcontroller, and then driver driving analog value, analog signaling of 4 to 20 milliamp to the host. And indeed, HART modem for digital communication, and again, proven technology, and with some limitation of what HART modem can deliver in terms of the speed, and also necessary translations of the HART protocol to HART-IP through some gateway and so on. If you look at the APL instrument, it's not that much difference. It could be same sensor, same signal conditioning. The microcontroller needs to be a little bit bigger with larger memory footprint, both on the flash and SRAM. Also need to run a little bit faster. And that's depend on the industrial protocol used. I'd like to highlight that the HART-IP is one of the lightest, less demanding protocols, while it provides all the necessary properties. It is still probably the least demanding in terms of the processor footprint and speed in the context of the process control applications, APL devices. And then instead of HART modem on 4 to 20 millimeter driver, we have PHY or MAC-PHY, depending on the level of integration and connection to the field switch. When we look at these two architectures from the power point of view, we know that the 4 to 20 milliamp blue, while at 20 milliamp, the system still needs to be able to deliver almost half a watt of power. The power left for the instrument itself at 4 milliamps is 40 milliwatts. And when we take what could be the consumption of the modem, output driver, efficiency of the power converter, for the measurement itself, we are left with barely 25 milliwatts. And that's the limitation that everybody who has designed for the 20 milliamp device knows very well about the challenges there. When we look at the APL device, in contrary, the system power delivered to the spool is again about half a watt. And although we spent more power on the microcontroller running some IP stack and industrial protocol, and the Mach-5 takes a little bit more power, we spend more power on the protection. But still, the instrument as a whole gets almost all of that half a watt of power. And for the measurement itself, it's about 250 milliwatt, more or less. And it's about 10 times more than the 4 to 20 milliamp, which allows you to use more sophisticated sensors and also transfer some of the sensor that traditionally would have to be 4 wires with additional wiring for power supply. We can convert it to 2-wire solution connected to APL. Then we look at the explosive safety. The principles are the very same as they have been in the 4 to 20 milliamp loops. Same principles of protection, protecting the surface temperature of anything that is inside the device, limiting any accumulated energy, staging the power levels, limiting the capacitors and inductors that need to be in the instrument. APL brings a little bit of specifics of the power coupling inductors, so they need to be protected by a series of diodes. And that's the reason for the APL spools using 1 volt peak to peak amplitude. One of the reasons is overall power level, but the main reason is really how to realize the protection of these power coupling inductors, and that in that case, the 1 volt peak to peak amplitude is a great help how to design the instrument. And then for instance, safety, because of higher power available, we have a little bit more power to dissipate, but that's nothing really new in the industry. The foundation field bus instruments operate at the same maximum power level for intrinsic safety. So there shouldn't be that much new in terms of protecting the device for explosive using the intrinsic safety principles. When we look at the functional safety, we all know, and the principles on the sensors and diagnostics and redundancies on the sensor side are the same again for 20 milliamp or APL, no difference there. But what is different is the communication itself. For 220 milliamp, there has to be a lot of diagnostics on both the 420 milliamp transmitter side and also the analog input side, or vice versa if you're driving to a valve, because any value between 4 and 20 milliamps would be a valid value representing a measured property or a valve opening, for example. And therefore, it has to be sure that what is driving, that we think we drive 5 milliamp, it is really 5 milliamp. In contrary, the APL device, the communication itself is black channel. So it either works or it doesn't work. It's very simple. You either do get correct Ethernet packets or you don't. And as long as there is some safety implemented in the protocol, the communication channel is actually easier in the APL field device or any APL device when it comes to functional safety. And then we look at security. There hasn't been much security implemented in the 4 to 20 milliamp loops. There has been security being implemented in the HART protocol itself. But here, because we do have a connection and IP addressability down to the sensor, and that goes both ways, somebody can do something wrong to the sensor by attacking it from the cloud, or somebody can connect a rogue device into the network and can cause a damage on the operational network. There needs to be applied principle like secure boot, that we run the firmware on the microcontroller that we intend to run, authentication, that the controller is sure that it's talking to the device that is intended to talk, and vice versa. If we are getting some instructions from the controller, that the instructions are correct, include some encryption. And there are solutions for that. Analog Devices has a portfolio now with the former legacy Maxim portfolio. We have microcontrollers with embedded security. We have dedicated secure authenticators, so we can provide solutions there. And more to the components. Once I started components, we do have components for the core of the APL connectivity, which is 10BASE-T1L. We have now more than a year on the market 10BASE-T1L PHY. The PHY is very low power. We know that while the power available in these field APL instruments is higher than 4 to 20 milliamps, still to fulfill the explosive intrinsic safe design, the power is extremely limited and extremely important. So our PHY design focus has been for low power, and we can guarantee 10BASE-T1L IEEE compliance, and with few and more devices passing the APL certification, we are quite confident that our products are also APL compliant. So that's why with standard MII, RMII, RGMI interface to the media access controller in the host. And then we also offer a MAC-PHY, which is a level integration above that. So we integrate media access control on our chip for very little more power. If you compare 39 milliwatts of the PHY to 3 milliwatts extra for the media access controller. And now we can offer SPI connection to the host processor. And it enables few things. It enables a much wider selection of low power microcontrollers to be used in the end instruments. And it also offloads a lot of tasks on the network by packet filtering and queuing the Ethernet packet coming in. So the host processor doesn't need to be that busy handling the Ethernet communication, which again leads to low power consumption of the controller because you can just simply run it slower. So again, PHY and MAC-PHY. PHY we will typically see used in the field instrument, connecting to a switch fabric of the Ethernet. And then in the end instrument, in the edge devices, we can see both the PHYs and again MAC-PHY with the advantage of offering more efficient, from the power perspective, more efficient solution. And then what other tools we offer for 10BASE-T1L? One interesting thing about 10BASE-T1L, how is it defined, at least in the IEEE standard, and the APL has done a great enhancement over that, because APL at least defines some level where the cable should be foundation field bus or field bus cable type A. But still, the cables that has been used for the foundation field bus are not always performing in terms of the frequency bandwidth. And then we can envisage some people would for sure use 4 to 20 mm cables, which by far are not meant for the APL. I'm sure that some people will try to do that. So the 10BASE-T1L defines link segment instead of the cable. So it's no Cat5, Cat6 as known from Ethernet. It's just electrical property of the cable. And if somebody is asking if the cable that they have in the plant is sufficient for APL communication, our chips can provide some tools for that. We can measure mean square error on every of our chip, PHY, MAC-PHY, which is basically characterization of the signal-to-noise ratio. And based on the signal-to-noise ratio, by statistics and the communications theory, we can predict what is going to be the bit error rate, what's going to be reliability of the link. And we can flag based on the value read from the register on the chip. We can tell if the link is good or is just marginal, or is it really poor. So we can offer these tools, and the end user can use the tool on the switch or on the device, and these can be passed to the end users and can give indication what is the quality of the link before they run into any issues, or if they are running new installation, are the cables that are there fit for purpose. We offer many other tools on chip, loopbacks, frame generator, frame checker that would be more useful in the design cycle for the instrument. And then if the cable gets disconnected, if somebody cuts the cable, we can offer a great enhancement above the 4 to 20 milliamp. You can tell if the 4 to 20 milliamp is open, yeah, there is no current. Short, you run into limitation of the current. The current goes either below 4 milliamps or above 20 milliamps, so we know there is some issue. But with the APL and our implementation of 10BASE-T1L serving APL, we can offer time domain reflectometry, and we can not only say that there is open and short, but we can also tell what is the distance. Time domain reflectometry principle very simple. We inject some pulses to the cable. We look for reflection, and depends on the polarity of reflection, we can tell open, short. And from the time, how long does it take, we can tell what is the distance. And we can tell it quite accurately. If we know roughly what the cable is used, we are achieving accuracy in order of well below 1% on the APL spurs. If we don't know what the cable is, and there is a variety of the speed of signal over different cables, but still we can guarantee, I'd say, 10% accuracy. If we blindly just say we don't know what the cable is, we can still tell if the cable is open or short and what is the distance. Is it open at the end device, or is somewhere open in the interconnection in the field cabinet? We can help a lot, and again, this can be passed to the end user, to the end plant manager when they are maintaining the network. And we can evaluate our solutions now. We have evaluation boards. The PHY evaluation board you can really evaluate the technology. We have graphic user interface running on Windows PC. You can play with registers. You can play with many things. You can use it as a media converter, or you can use it for your prototyping. There is a connector on kind of the header on the bottom of the board that contains the MDI and MII, RMII signals. You can, on short wires, because it's a fast interface, but you can hook it to your own controller and start prototyping with our board. Again, play with the technology, try different loopbacks, test modes, I2V test modes, play with the time domain reflectometry. That feature is not on the web right now, but in next week or so, I believe there will be available on our web as an upgrade to any of the existing evolution boards that we have out in the field. And then as I said, we can use the evolution board as a media converter. So if you have a field device they are developing, and you want to connect it to a laptop or Ethernet, normal classical Ethernet switch, or a control system, you can use our board as a translation from on the physical between 10BASE-T1L and standard Ethernet, and use it for your own debugging. We also have evolution board for MAC-PHY. We provided this our driver and as a demonstration lightweight IP stack and simple web server, so you can connect the board to your APL switch, and you can use it as a kind of very simple device showing link property and board temperature. You can again use it for your own development, connect to you can use it with the ST micro that is on the board. For that purpose, we provide the JTAG connectivity, and if you use and software example on our web, you can start the software development there. Or if you have some other controller of your choice, you use something different. And we are preparing solution for our Maxim microcontroller, our microcontroller portfolio coming from Maxim. We will have solutions for that. Or we have seen our board connected to Raspberry Pi over SPI, so there is no limitation how to use the board. And then one more thing to mention is power. APL defines its power classes, and for powering the device, there is a power coupling on the switch side, and power device is the APL field device. There are two standards. One is your APL used in the process industry. There is also another power standard with their own power classes defined in IEEE. Analog devices can help you with both. Specifically on IEEE, we have recently released some controllers both on the power sourcing and on the power taking side of the link. But if you need something very quick, you can use the evaluation board that we have right now. Plug into a little module, and that module is available. If you need one, request it. We plan to put it on the web very shortly as well. You can just plug in the module, and you can again use the board as a media converter, including the power. You need to provide the power level appropriate to the APL class. So provide external power to the barrel connector, 15 volts, and off you go. You can connect your device and use the 10BASE-T1L and power as APL device. And then I like to mention what we see as a success of the APL. This is from ACHEMA trade show in Frankfurt, where I was in August. You can see there was a cluster of organizations, all happy neighbors, or sharing the common space. There was the FieldComm group and Profinet and ODVA all in one place. And then if we looked at and we presented as analog devices, we had a little demo there showing our cable diagnostics. And if you look at the wall there are many APL devices already there from different vendors, switches, flow meters, pressure meters, level meters. So we can see, and ourselves are convinced that APL will be a success story, and we can work on the APL solutions together. So that's from me. Thank you. And if you are interested in any solutions that we can provide as analog devices, please feel free to contact us as analog devices for Ethernet, APL, 10BASE-T1L solution. Thank you for your attention.
Good afternoon, ladies and gentlemen. I'm Martin Lange from emBex, and I want to talk today about how to develop safe field devices with HART-IP and APL. Safe HART over APL offers a whole new world of possibilities for safe field devices. Why? In today's world, safe communication of field devices is limited to the 4 to 20 milliamp interface, which we have with HART devices. With Safe HART over APL, it will be possible to transfer any data which can be digitally coded. This could be, for example, frequent commands as do partial stroke test, or maintenance data like time of operation absolute minimum maximum values of process data, and so on and so on. If these current limitations have prevented you until today to transform your field devices to safe devices, I would like to tell you how you can do this now. What is Safe HART? There's a draft of the spec which is expected to be released in the beginning of 2023. If you take a look at Safe HART, you will find out it is essentially HART with some additional safety features. There is a CRC for data integrity. There's a sequence number for sequence and time monitoring. There's a request response mechanism for safe process data. These additional data will just be ignored by non-safe HART devices, so there's complete interoperability of safe and non-safe HART devices. And just for those of you who wonder, Safe HART is not a black channel protocol like ProfiSafe or ZIP Safety. Instead, the protocol implements all safety features on the lower communication levels. Today, I will not go into details about what Safe HART is. And I will neither talk about how to implement Safe HART. There will be stacks available on the market in the near future, so there is no need to implement all its details on your own. Instead, I want to give you a general impression on what it means to develop a safe field device. Before we dive into the details of development, let's have a short look at the underlying standard that we are talking about, IEC 61508. IEC 61508 has come to life more than 20 years ago. It is the international basic standard for functional safety. And it is theoretically applicable to any kind of safety critical application. Currently, we have the second edition from 2010. We are already working on the third one, which is expected to be released in about 5 years from now. When we are talking about safe field devices in the process industry, almost all of them are classified as ZIL2 low demand with respect to IEC 61508. What does this mean? Low demand means that the devices are only applicable where less than one demand on the safety function is expected per year. Luckily, it is assumed that this is true for the typical process industry application, which is controlled by a standard non-safe control system and which is only supervised by a safety system which is to safely stop the process in case that there is any dangerous failure. Developing low-demand devices is much easier than it would be with high-demand devices. ZIL2 for low-demand systems means that the probability of a failure of a malfunction when there is a demand of the safety function must be less than 1%. Since there are usually several devices involved in executing a safety function, there's a convention to distribute this failure budget in between these devices. The sensors get 30% of the budget and the actuators get 50%. But this is not all. There's an additional requirement on the behavior of safety devices. No more than 10% of all failures occurring in the hardware may be dangerous. This means for you, you have to implement mechanisms for online diagnosis which detect 90% of the dangerous failures in your hardware. If you wonder how you can prove that these requirements are fulfilled, what you do when your schematics and your online diagnosis is designed is you calculate the rates of the dangerous and safe detected and undetected failures based on reliability data for the individual hardware components. However, safe field devices don't only contain hardware. There will also be software for which until today it is not possible to calculate any failure rates. So instead, IEC 61508 gives requirements on how your device and especially your software shall be specified, designed, implemented and tested. We will come later to what this means. Let's now have a look inside a typical safe field device. Starting from the right side, we have the APL network. In the device, in most cases, you will have a barrier for explosion protection. Then there is a PHY which manages the APL hardware and, in parallel, a power managing block which gets the required power from the APL lines. These 4 blocks can be considered as not safety relevant. Telegrams, which have been decoded in the PHY, now come into the microcontroller where they are handled by the Safe HART stack. As said before, I will consider the stack to be ready to use and that you will not develop it on your own. There will still be some application software in the microcontroller. To the left, there will be either a sensor front end or an actuator front end, together with some hardware which evaluates the input from the sensor or controls the actuator. We will now have a walk through the individual components of this device and see what the standard requires for them. Let's start with the microcontroller. First of all, there shall be measures to detect all the possible hardware faults inside the microcontroller. As said before, the diagnostic coverage of these measures must be 90% or higher. Typical faults you have to consider are memory faults in RAM, ROM and core registers, stack over and underflow, missing or undesired interrupts, stuckets, shorts and GPIOs, faults of the internal analog-digital converters, faults in the program sequence, wrong timing, and over- and underclocking. For the latter three ones, you will have to integrate an external watchdog. Assessment bodies today do not accept the use of the internal watchdog if it is not a safety-certified microcontroller. If you plan to use a more complex microcontroller in your device, be aware that there will be additional sources of possible hardware failures, like for example memory cache. And it can become quite impossible to detect failures in these without detailed knowledge of the chip design. Luckily, there's an increasing number of chip manufacturers who offer self-test libraries for the microcontrollers. And I would recommend using them if you can. You should just make sure that the library you use is certified for ZIL 2. Libraries, for example, for household applications will not be sufficient. However, there are not only internal failures which can make a microcontroller unsafe. You must guarantee that the microcontroller is always operated within its maximum ratings, with respect to voltage, temperature and clock frequency. So you have to implement diagnostic circuits and hardware which will be able to switch the device to a safe state whenever any of these limits is violated. For sensors, the safe state usually means don't send any more data. For an actuator, it can mean anything. For example, for a valve, it can be either open or closed, depending on the application. Anyway, in general, you will select a valve which goes to the safe state if supply voltage or current is switched off. Let's switch to the hardware which controls your actuator or processes your sensor signals. As said before, the overall probability of a dangerous failure for your device shall be below a defined limit. But usually this is not a problem to be achieved by discrete hardware. What makes it much more a challenge is to make 90% of all failures to be safe. The straightforward way to achieve this will be identify each possible dangerous failure and implement means to detect it. If this proves to be impossible for a certain component, you can still try to tolerate this one failure and prove that the share of dangerous undetected failures is still below 10%. At the end, this proof will be given by an FMEDA. But I would very strongly recommend to do a failure analysis already at the beginning of your hardware design based on a block diagram and define the required diagnostic measures already on this block level. We now come to the actual front end of your device, the point where safety really takes place, since here the interface to the physical world. And if you go to the IEC 61508 to find any guidance on how to handle this so important interface, you will be quite surprised. You will find just nothing. Any interface of electronics to the physical world is completely neglected by our basic standard for functional safety. So, what can we do in this situation? The target is clear. Your front end shall do what it is supposed to do under any possible circumstances to be considered. And this is not only a matter of safety, but also of availability, since your customer will not be too amused if your device spends most of its lifetime in its safe state. What I therefore recommend is do a very careful analysis of all the physical variables which could possibly have an impact on your device's safe function. That might be its action as an actuator or its measured values as a sensor. These physical variables might be temperature, vibration, external electromagnetic fields, radiation, corrosion, inhomogeneity of the medium, deposit of material, and others. For sensors, there are mainly three possible ways to handle such possible impacts. Compensate them, adapt your measurement accuracy in order to cover them, or limit the field of operation for your device. In any case, you should document your analysis and the decision which have been drawn from it. And let me just mention, at emBex we have developed a procedure for handling the interface of sensors to the physical world, which has been successfully applied in a number of development projects. Until now, we have only talked about technical requirements of the standard and ways to design a technically safe device. But IEC 61508 also contains requirements on the way how you develop a safe device, requirements on procedures and management of your development project. The underlying picture is always the V model, as you probably know it already. Essentially, the V model means two things. First, any requirement that you write down must have a test or a check, a review, or an analysis for its verification. If you specify, secondly, your requirements on different levels, for example, product level, component level, and software hardware level, then there must be traceability of requirements between the different levels. If you are used to agile processes, and if you wonder now whether this goes along with functional safety, don't worry. Agile safety development will just mean that you pass through many small V models for each feature that you implement. Besides the overall idea of the V model approach, there will be more procedures which will be followed during your development. For example, configuration management, review processes, and many others. IEC 61508 just requires that these procedures are defined when you start your project, that they are followed and that they are monitored. If you have a stable quality management, this will already cover most of the standard's requirements. One special requirement of the standard in this context is that roles and responsibilities shall be clearly defined. And on top of this, evidence shall be given that all members of your team have the necessary competence for doing their job. Until now, all these requirements apply to hardware development as well as to software development or development of your physical front end. On top of these, there are additional requirements which apply solely to software development. The requirement to start with is the requirement on your tools. Funnily, today there are no requirements on the tools that you use for your hardware or system development, but this might change with the standard's new edition. For all software development and testing tools, there shall be evidence that you can trust them and that they will not insert failures into your code. The most critical tool here is, of course, the compiler. You might either argue with long-term experience with the compiler you use, or you will have to turn to a certified one. Second, if you use C or C++ for your development, there are awfully many features to these languages with which you can do a lot of nonsense. So if you want to do a safety development, you shall prevent the use of the most dangerous features of your coding language. To start with, MISRA standard is a good starting point. You might want to add additional rules, especially for naming conventions, which help to make code readable within a team. Whatever your coding standard looks like at the end, you shall always prove that it was properly applied. Yes. This might be done by code reviews or, preferably, by automated static code analysis. Third, IEC 61508 requires that you prove that you have covered your complete code by your software tests. You can do this either by module tests or, if possible, on integration level. For SIL 2, only statement coverage is required, but from experience I would recommend to check for at least decision coverage, because this will help you to find more of these just so subtle little bugs. Finally, since you have implemented a bunch of diagnostic functions to detect failures of your microcontroller's hardware, you will also have to verify these measures. This will be done by simulating these failures by additional test code in your code in order to prove that your software will properly detect these failures and performs the right failure reaction. If now at the end you have decided, yes, we want to develop a safe field device, there might be one last question. Do we need to involve an assessment body and get a certificate? The answer at first is no, you don't. The standard allows that any independent person in your company assesses and confirms the conformity with the standard. But at second, and this is just a recommendation, I would say yes, go for a certificate from an independent institute. And there are two reasons to it. First, a certificate from an approved certification body is the best sales argument for a safe device, and probably most of your competitors will have one. And second, in case that there might be any incident in the future, and we all hope there won't, a proper assessment of your development will probably limit your liability. So, if you decide to involve an assessment body, there's one basic rule. Be transparent. Don't hide anything. Don't claim you have done something which you haven't. This would make your certificate worthless. And involve the assessor as early as possible. Get yourself already a concept approval. It is the best measure to reduce your project risks. And if now you still fear whether you will manage to do your first safety project successfully, we are ready to help you. Thanks a lot for listening. And now I'm curious for your questions.
Hi again. I'm pleased to have you with me for our session, Your Quick Start for Ethernet-APL, where we will see how easy it can be to migrate an existing HART instrument design to Ethernet-APL. When we have a look at process industry today, there are tens of millions of devices installed and millions added each year, ranging from simple sensors to complex analytic instruments. Most of these devices use still 4 to 20 milliamps technology, maybe enriched by digital point-to-point communication using HART. Even with the advent of digital buses 25 years ago, this didn't change much. Getting access from the control room to the devices and to much more information from the field was then possible, but required dedicated equipment, additional software components, and expert skills. This is probably why even today the field bus share isn't greater than about 15% of all installed process automation equipment. Today, integration of the field level into the IT world still requires specialized gateways and a lot of expertise. Now imagine a digital communication that provides everything needed for the convergence of OT and IT, from the field level up to the cloud. Use all your known protocols on all levels without any gateways required. Overcome the restrictions of typical IT networks. Long cables are possible, while data and energy use the same pair of wires. Also, intrinsic safety is now possible with Ethernet-APL. And even better, the ease of use and transparency of Ethernet-APL reduced the complexity that prevented Fieldbus from gaining a larger market share. This will lead to rapid adoption by the industry users and create fast-growing demand for field devices that implement this new technology. Another good news is, if you are a vendor of instruments for process automation, Softing can help you with your ticket to APL. You may already have experienced how cumbersome integration of communication technology into field devices can be when you need to take care of every detail. If we have a look at the tasks involved when developing a new Ethernet-APL field device, we see quite a long list that by far isn't complete. On the hardware side, we need to implement the new T1L Ethernet physical layer, as well as the required power management. If the device is targeted towards applications in hazardous environments, we also must obey the requirements for components used in explosive atmospheres. Software-wise, we have to bring a fitting TCP/IP stack to our hardware, add the layer 7 industrial protocol, and implement the application profiles our device needs to comply to. In addition, we may want to integrate other TCP or UDP-based features like a web server, OPC UA, or edge connectivity. Finally, we must write an application program that links all this together, permitting control over the device's real functions via the Ethernet-APL network. From earlier device developments, you probably know that this kind of development approach easily can take many months or even years while consuming large amounts of investment. So you may ask yourself, is there an alternative approach to implement Ethernet-APL that allows for lower NRE and shorter time to market? I guess you won't be surprised if I say, yes, there is a solution to this. CommOdule APL brings all you need directly to your field device. You receive a pre-certified communication daughterboard that implements an APL-compliant Ethernet. Its onboard power regulation and intrinsic safety design makes it suitable even for EX zones 1 and 0. Ready-to-use Ethernet communication is already implemented on the board, so you just need to create your device application software. Don't worry, there's no need to go through a long and costly software development project. With the provided tooling, you can configure your application and even reuse designs you may already have available for HART or Modbus. Let's give it a closer look. What we will find is CommOdule APL. It is a stamp-sized, highly integrated module with edge contacts. With its blank reverse side, it is suitable for automatic assembly on the device's baseboard. There is a potted version for use in hazardous areas. For less critical environments, there is an open frame type. That may also be used if the whole instrument is to be potted for protection. The module, implemented according to APL Power Class A, sources 2 voltages to the application part of the device. This application part can be linked to the module via a variety of serial interfaces. This is also where an existing HART or Modbus design can be connected. Using CommOdule APL gives you many advantages. Instead of creating a full custom design, you simply use a proven standard module for your development. All relevant verifications, certifications, and conformity tests have already been performed on the module. This facilitates the corresponding tests for your complete device. The clear separation of application and communication functions simplifies the integration process. Because the communication part is already there in hardware and software, you can concentrate on the application part. In many cases, it is as simple as configuring a mapping table that translates the data of an already existing HART or Modbus device design to Ethernet-APL. And finally, this approach is future-proof. With Softing as your supplier, it is on us to add further features and protocols. We also take care of the module's hardware design when new regulatory requirements or procurement issues arise. Altogether, this saves you a lot of time and money, not only for a short time to market, but also over the entire life cycle of your product. You may want to get a little more insight into the internal structure of the module. Coming from the left, you can see the connection to the APL network that provides communication data as well as electrical power for the field device through a protective circuit. As a power class A device, CommModule APL draws a constant current of 50 milliamps from the network. From this, it sources the module itself and provides power to the application portion of your device. An APL-compliant T1L Ethernet PHY provides the connectivity between the network and the onboard microcontroller. Here runs all protocol software and the mapping of the application data to APL. The actual device hardware connects to the module through a serial interface and may also use further configurable I/O. Finally, the programming interface here allows for downloading configuration information and software parts. Now, how can you proceed for your own device? Let's assume you have an existing HART field device that communicates over a HART medium attachment unit. It also gets its power from this connection. In this case, you would just remove the HART medium attachment unit and simply connect the digital HART signal to the CommModule serial interface. On that occasion, you may also want to increase the communication speed of your HART connection to a higher data rate for more performance. The power can now be sourced directly from the module. The following shows how an evaluation or development setup looks like. Here we see the module already assembled in an evaluation kit that provides the connectors for APL, for the device interface, and for a programming adapter. The device interface is connected via a small adapter to a HART device's application part here. For a fully operational setup, you should have a corresponding PLC or DCS controller that is connected to an APL field switch. This switch converts the typical 100 megabit Ethernet to 10 megabit APL. Here you can see the power supply connections for the controller and for the switch. Finally, the field switch connects and supplies the device with this single pair APL cable. With all this in place, you can start your evaluation and development. To give a short impression of how CommModule APL handles the data exchange between the Ethernet-APL side and your device application, I'd like to show you the module's software architecture. The network interface is where the PLC or DCS controller connects through the Ethernet infrastructure. Depending on the protocol to be used, the Ethernet traffic is handled by a Profinet, an Ethernet-IP, or a HART-IP stack. That connects to the corresponding application profile, or in other words, to the corresponding application data model. Additional Ethernet communication, like a web server or OPC UA, can be handled in parallel on the same network interface. The central component of the software is the mapping task that exchanges information of the application profile via HART or Modbus commands. For that purpose, additional master protocol stacks for these protocols are present in the module. Finally, these HART or Modbus commands are forwarded to the field devices application over the serial interface. The whole process can be configured using simple COM scripts that are part of the user-definable configuration table that can simply be downloaded over the programming interface. Like we heard already, Commodule-APL is typically configured, not programmed. For this purpose, Softing provides CommScriptor, a scripting tool that helps you tailoring the data model of your application according to the selected application profile. You can define the number and types of functions to be used, as well as the details of the application parameters. Also, device or vendor-specific extensions of the application profile are possible. Here we have an example of a parameter definition with parameter names, data types, and default values. Finally, the mapping between the individual application parameters and corresponding serial commands takes place. This is where existing HART or Modbus devices can be reused easily. This shows a HART command description with command name and number, a request definition, in this case none, and a response definition with various entries. This brings me to a short summary. Commodule-APL is a ready-to-use and pre-certified hardware. It has undergone thorough EMC and other environmental testing. With its ATEX certification and its physical layer and protocol conformance approval, it dramatically reduces effort, risk, and time for your APL field device development. The module comes with pre-installed protocol software. It offers a configurable application data model and command mapping. This avoids time-consuming software development tasks, thus speeding up your product development. Finally, being a standard product, Commodule-APL will be maintained by Softing. So updating your device with new features will be easy. This makes integrating Ethernet-APL a very easy task. In contrast to development from scratch, effort and development time are significantly reduced. Thus, you can very quickly participate in this rapidly developing market. If you require more information for your next field device development project, or if you have questions regarding Commodule-APL, the evaluation kit, or other useful equipment, please contact Softing. My colleagues and I look forward to speaking with you. Thank you.
Okay, we're scrambling here. We've got Michael Brychta from ADI is having a little bit of a trouble joining, so I'm going to ask Heather to chime in here and provide us some answers to some of the questions that are specific to him. I think we've got about 6 or 7 questions that are going that we need to address before we move on to the next section. I want to thank Christian and Martin for those great presentations and also for pre-answering some of the questions. I'm going to ask you to just repeat your answers here so that our live audience can hear what we what you said in the chat session that we were having. Okay, so the first question that I'm looking at here is it's for Michael. Oh, and it looks, no, he has not joined. Okay, it's for Michael. It says, is there a recommended circuit with values for the IS protection components required with the ADI-N 1100 or the ADI-N 1110? Did we get an answer to that question, Heather, or is Michael on? If not, we can address it later.
I didn't get an answer to that one in particular.
Okay.
We may have to come back to that one.
Okay, we'll follow up with that. Okay. Question 27. In ADI's evaluation board for ADI-N 1110, they have a 470 microhertz common mode choke. Oh boy, is this choke required, and how does one provide intrinsic safety for a common mode choke? I've heard one supplier of common mode chokes say that only L-stray of the choke applies to the intrinsic safety calculations. Is that true? We may not be able to answer this from Michael, but maybe some of the safety people here can answer that.
I can add what Michael left us before we lost connection with him. He said, good question. The common mode cannot be clamped. It needs to have a small enough magnetic core and fulfill the IS requirements based on max energy held by the core, not by inductance or clamping.
Okay. Any other comments on that? Okay. So the next question, this is also for ADI. Do you have drivers for the SPI interface to provide low-level network APIs?
I believe he said yes, they're on their website.
He said yes, and they are on the website.
Yeah, so check out our portal. If you scroll down, if you're watching on our website, there's a icon for ADI there. Click that button and it'll get you to the contact information for them. Okay.
Question 29. I think I know the answer to this one. Is a HART-IP stack included with the 1110 eval kit or with the 1100 eval kit? And I'm guessing the answer is probably that stacks are not included. But do we know? I'm going to guess that the stacks are not included. Okay. Let's go on to question 30. This one actually is for Martin. Okay. So the question is, how can SafeHART not be a black channel protocol? This would require the field switch and the power switch to be part of the white channel. How would SafeHART white channel affect the infrastructure, such as field switches?
Okay, thank you for the question, because you caught me with a mistake somehow. Because of course, SafeHART is not white channel protocol, as you mentioned, which would include to consider all the physics in between and so on and so on. What I wanted to point out is that, in contrary to like ProfiSafe or ZipSafety or all the standard safe field buses, who are working as kind of a container transferred as data payload by the underlying field bus. This is not the case for SafeHART, because SafeHART is more or less an extension of just standard HART protocols. So SafeHART protocol will just be a HART-IP protocol, or a HART protocol with some additional features, some CRC and sequence numbers, and some required mechanisms, but the data inside will be recognized as just, I think they will be able to be read by any HART-IP or HART device as well. These non-safe devices will not be able to compose such a SafeHART protocol or SafeHART telegram. So might call it a gray channel protocol or something like this.
I like Gray Channel. Okay, good. Okay, thank you. Okay, the next question is also for Dr. Lange. And I think it's actually a two-part question. First question is, does emBex do certification? And the next question is, does emBex develop Ethernet-APL products with SIL in mind?
Okay, so starting with the first question, no, we at emBex, we don't do certifications for safety. For this, we always work together with certification bodies like the German TÜVs, for example. And actually, up to today, this question has come very rarely because, well, it's a pity that still this TÜV stamp is much more worth than the emBex stamp.
Okay.
And the second question, whether we develop Ethernet-APL with SIL in mind. As I said, until today, the Safe IP, the HART, Safe HART standard is still not finally released. So, of course, there is no implementation of Safe HART devices yet. And we are working with some projects already on Ethernet-APL devices, just standard. And we at emBex, our business model is to develop devices on behalf of our customers. And I'm very sure that in the future, we will develop also Safe HART devices with Ethernet-APL.
Okay, thank you. So the next question is for Christian, and I'm going to consolidate a couple of questions that come in that are sort of similar. And the basic question is, I'd like to ask you to elaborate a little bit more on your comments about how your COM module APL does HART mapping, and more also, do you have a HART-IP stack, or how do the two concepts kind of relate to one another? If you could elaborate on that a little bit, I'd appreciate it.
Yeah, thank you for this question. As you may have seen from the presentation, I put these communication stacks as a layer in our software architecture, which can be several. So the basic commonality is, of course, the hardware platform that we use for that. So we can do all of this on the same kind of hardware, which our goal is to have a pre-certified design for our customers that make it very easy to reach their certification with all the required bodies themselves. To be pretty clear, and it doesn't make sense to hide anything here. Of course, we have a roadmap behind all that. And at the time being, we have not yet implemented the HART-IP part. Maybe this leads me also to another aspect. So the idea of the module itself was, of course, to be an instrument or a vehicle for our customers to be very fast to adapt to Ethernet-APL solutions by just relieving them from many of the especially of the hardware tasks. So we actually started now with the Profinet implementation, in which case it makes very much sense to do this mapping, to just bring a existing HART device, just by mapping it to the respective parameters of a PA profile device for Profinet, not needing to code all this, but do it in a mapping manner. So maybe for HART-IP, it's not the perfect approach. That's something we can admit, but I'm thinking of nevertheless doing something like that, like a more or less a stop interface for that, so that we just can pass through the HART commands on the same architecture. Nevertheless, the approach that I showed in the presentation was, like I said, intended for the very, very quick adapters to bring something to market. That doesn't mean that the hardware cannot also be used in a different way. And the second way of using it is that, of course, we are able to open up a software layer inside the module where you can add additional functionality. And this could be a more customized way of adapting to a HART-IP implementation in this module as well. which also would allow, for instance, to bring things closer to the single model. So you can have also some sort of application software inside the module, which is not the standard approach for the quick adaptation. So we just look on a device that is already there, and we rip off the medium attachment unit and just use the digital HART to go in, more like a gateway or a bridge to Ethernet-APL. But like I said, this can be opened up on the module if that's helpful in that case. Of course, making the dedication of our customers a bit more larger to do more work on that. Of course, they need to do the software then on it. And yeah, finally, this also opens up to maybe even make the external device superfluous somehow, the secondary processor that does HART communication, but just use IOs directly on the module side. So that's also possible. So we have already requests for this product that make use of it and add some additional hardware aside of it to map that directly into the software. So maybe it's a long answer now, but in short, the module concept is one thing, and the potential of the hardware, of course, is much larger. So we can open up to our customers. So we are very interested in also receiving requests from the HART-IP community for that, just to discuss the requirements our customers have, to see how we can ideally match our existing and planned offerings with their concrete demands to find best tailoring to the development pathway in that.
All right, great. So I've got 3 more for you, Christian.
Yeah, you're welcome to.
One more. Then I'm going to close with one for Dr. Lange. So so I'm going to try and ask all 3 of these kind of at the same time. So first question is, can a sensor directly be directly connected to COM module, or a baseboard with a couple of sensors be directly connected to COM module? I don't know if you showed that interface. The second was, does COM module support the security features specified in HART-IP 2.0, so the PSK and the user password model? And then the third question is, what about functional safety and the COM module? Is it a functionally safe device? So.
Okay, so it was three things. So I remember the multiple or the discrete sensors connected to the module. So as long as this is a digital interface or a simple analog interface, the module has everything on general purpose I/O that can connect to such a thing, which leads back to the second approach that I mentioned in my answer before. That would mean to put some customer software directly on the module, which is possible. Okay. Second was, help me once again.
Security.
Yeah, security is a big topic. I think that's true for all automation protocols we are looking at, at least for future generations. So that's a very, very important thing. And we have made precautions already on the hardware selection. So we have support for especially this AES support and things like that, to do that in software. So we are currently looking into that to implement this on this module as well. And the last thing was functional safety. Yeah, as long as we can look at the basic communication as a black channel, that's open as part of the application. So I think this is what Dr. Lange already mentioned, needs to maybe to have a bit more consideration to do that. So typically we do not do a safety developments on our side. So that would mean a more intense cooperation with our clients and customers to get that expertise in their final product. But from what I know from the past, we have a lot of customers using our black channel kind of stack offerings, protocol offerings that we have that can easily be used in safety designs as well.
Right. Last question for you, Dr. Lange. So the question is, what is maturity level 5 for functional safety development? And what does that mean? And is it mandatory to have a functional safety engineering for development? And what if not? I think the question is just basically, should instruments be safe?
Yes, no, I think it's more specific. First of all, maturity level 5 means that our functional safety management and our safety development process has been assessed and certified by TÜV Rheinland for the last 15 years or something like this. And TÜV Rheinland has, for their these assessments and certifications of development processes or safety processes, has an internal rating. And the highest level in this rating is 5, and emBex was the first company worldwide to gain this maturity level 5.
Well, congratulations.
Thank you. Whether it is mandatory to have, the question was, is it mandatory to have a functional safety engineer for the development? It is not necessary that everybody is trained as safety engineer or safety expert who is working in a functional safety development project. But there should be someone who is trained and someone who is qualified to do development. And this is something which is actually required by the standard. So the standard says you have to prove that people who have a certain role in the safety development are qualified for doing it. So there should be someone, and this can be some senior who is training and coaching those who don't have this experience. But someone should be involved in the development, at least someone who really is qualified for doing safety.
Okay. Thank you. I appreciate your answers to these questions, and I appreciate the presentations. Again, they were fantastic. So you guys can turn off your videos now, and we can move on. So we're coming up next. We've got a couple of things going on. First of all, we're going to have 3 more presentations from our suppliers. We're going to start out with Relcom, then we're going to move into smart embedded systems, and we're going to close out with Utthunga. In total, if I'm doing my math right, we've got about 18 plus 13. We've got about 31 minutes of content left amongst those 3 presentations. Please put your questions into the chat box again so that we can answer the questions at the end of those sessions. Then we will wrap up with kind of a brief overview of the microsite and some of the some closing stuff that Heather has prepared for us. So we're into the home stretch here. Thank you for sticking with us. It's been a long day, and here comes the last series of videos.
Relcom has learned a lot developing products for Ethernet-APL. The first project we started was a remote I/O product that would take multiple analog HART or discrete I/O inputs and multiplex them essentially to APL. And the first problem that we encountered was as part of development, and that was that we needed to be able to communicate with this device and test that the APL communications were working. And we didn't have anything to convert from the APL to Ethernet. And that led to the development of 2 other products, the A111 and A112, that are Ethernet-APL adapters. They allow you to connect to the Ethernet-APL device and then convert that connection over to standard Ethernet, so you can hook up the device to a network, or the A112 converts over to USB, so you could connect to a PC directly. And with those, you can then use standard Ethernet-based equipment to test, interface to configure your Ethernet-APL device. And they also provide power to the Ethernet-APL device you're working with. Ultimately, we anticipate this product being used by end users as well, because they will need to do some pre-configuration of their Ethernet-APL devices before they install them in the field. They'll need to assign them a tag or give them their pre-shared key for security, that sort of thing. While testing our Ethernet-APL products, we were using Foundation Fieldbus Type A cable, and we found we couldn't get the 1 kilometer distance over that cable that Ethernet-APL is capable of. We tried several different cable manufacturers and found that the distance we could get with that cable was somewhere around 400 or 500 meters, and varied with the cable. So we came up with the idea of developing a cable tester. The idea is to tell the user how long the cable that the tester is connected to is, and do an evaluation of it to determine whether or not it can carry APL signals and power. If it can, how long of a cable of that quality can be used for APL. So that's another project we're working on. Relcom continues to develop Ethernet-APL based products. We are going to work towards products that will help developers get their products out, as well as products that will help end users implement Ethernet-APL in their plants as easily as possible. To do that, we plan to partner with other companies that enables products to be brought to the customers that need them faster and on a larger scale.
Smart Embedded Systems APL demo. Smart Embedded Systems has been involved in the HART technology for more than 10 years. We have been shipping our HART-IP gateway products for more than 2 years and have been developing HART-IP 2.0 product as the specifications are evolving. We are prototyping, testing HART-IP security functions as the standards are being developed. We are fundamentally a technology company. We want to help speed up time to market for our customers by providing a building block approach to design. We are a long-time design partner for Texas Instruments. This design has been based on their APL5 solution. So what does our APL design offer? It allows companies making 4 to 20 milliampere HART devices to very easily migrate to APL. Our design can query your 4 to 20 HART device and relay the response to the APL side. This will allow you to quickly evaluate the design. So you can evaluate the design as a gateway and then migrate the design as an integrated APL solution. The question then is, how do we get fast 20 plus updates you need per second on the APL interface? In this case, You just have to speed up the serial port data rate where the modem is typically connected and connect to our serial interface. And using this faster serial port, now we can get fast updates of 20 plus updates per second. The design is also low power and complies with intrinsic safety aspects of the design. The low power consumptions is carefully optimized where you have 100 to 135 milliwatts of power available for the sensor side of the design. So what are the other major features? One can also do a standalone transmitter actuator design by using the ADC inputs, digital outputs, SPI interface, and I2C interface available on the I/O header of the evaluation board. By using this, you can connect your sensor module or your own current HART module, connect them using one of these interfaces, and be able to gather data from them. The device also has got onboard flash storage where one can store FDI and DD information. The device logs can also be stored in the flash. Our design complies with the current FCG HART-IP server test plan. We will keep track of test plan updates, security requirement changes, and provide you with a secure firmware update. As a designer, you just have to focus only on designing sensors and leave the rest of the aspects of the design to us. System architecture. As you can see in the block diagram, this is a very standard system design architecture. The power is derived from the APL loop. Since hard devices are not expected to do PODL negotiation, it is not included. The DC regulator is an isolated DC to DC buck regulator. The conversion efficiency is kept as high as possible to maximize the available power for the rest of the design. The MCU handle all HART-related control functions on the HART protocol. The APL device is Texas Instruments APL DP83TD510. The MCU is ST Micro's STM32F417 with MII or MII interface to connect to the APL5 device. The design brings out all the IOs from the MCU. We have SPI, we have I2C, we have ADC, and we have UART. We have also provided a HART 420 mA port so that you can easily get the APL setup up and running very easily and start testing your transmitter. You can have this setup up and running in less than 5 minutes. Here are the key components in the design. The microprocessor is ST Micro's STM32 family, F417 part. The APL5 is from Texas Instruments, DP83TD510. The DC to DC converter is LM46002. And the modem on the hard port is SES's patented soft modem technology, which supports the FSK and the PSK standards. So let's look at the physical board with all the I/O connections shown in this picture. So here are all the connections we have. The green connector on the right side is the APL connector. It's a standard 3-pin APL connector with chassis ground and then the APL plus and APL minus pins. And then the blue connector on the left side of the board is a HART port, and HART is, as you know, is polarity sensitive with a plus and minus. There are debug headers for connecting the debug port to STM32, as well as programming and changing MSP430 firmware on the FSK modem side. The I/O expansion headers support ADC, SPI, I2C, UART, digital input and output. That's also shown in the back. So using this setup, you can actually wire and set up your test in a few minutes. You can have it up and running using standard off-the-shelf HART-IP client software. In addition to the I/O connections, we also have LED indicators showing the progress and activity on the board. There's a power indicator, and then we have a link/activity indicator. The link activity indicator will stay green initially, and once the HART-APL link is established at 1 volt peak-to-peak signal level, it'll turn orange, and the activity is shown by the blinking orange LED. So in a real final production product, if you want to conserve power and use it for your other devices, you may have to forego some of the LEDs because they do draw at least 20-30 milliwatts each. Here's our APL demo setup. The APL devices are low power, so we would need a bench power supply to provide the power. Since client application is running in a PC with Ethernet, we will also need APL to Ethernet, a converter or bridge. You can do this with APL EVMs available from TI or analog devices, or you can also get an APL to Ethernet switch, which is available from some vendors. To make the evaluation even easier, SES will provide an APL to Ethernet switch in January of 2023. You can see the APL connection is going from our evaluation board to TI. TI's APL EVM board, and the Ethernet connection from the TI's EVM board is going to your local network. We also hooked up a HART transmitter to our HART port. You can see the ABB transmitter connected to those the blue connector with the 2 HART pins coming out. Our APL in this demo is working as a HART-IP gateway, so that it'll relay responses back and forth from the HART port to the APL port and through APL to the Ethernet port. The APL to Ethernet is strictly doing a function of a physical wire, just converting signals. There is no protocol, no translation happening other than the signal level translation that's happening. Yeah, here is the HART demo using FieldComm Group's HART-IP client software. So we will enter the IP address of our device, and then we will connect to it. And once it's connected, you'll see the list of devices it's connected to. You have the HART gateway, and then you have a device. We simply query the HART device, As you can see, the APL is responding extremely fast, probably more than 50 updates a second. And now we'll query the HART device connected on the other side. And then we'll repeat the queries. As you can see, this being a FSK device, it's getting 1 to 2 updates every second. Now we'll stop that, go back to the gateway, which is working as a APL device. We will query it with command 9 and repeat the query. You can see it's also very, very fast. And each dot, as you see in the graphics, is one primary variable update. And as you can see here, the APL is providing you more than 20, 30 updates a second. My estimate is it's about 40 to 50 here. So this is in essence is what a APL device can provide for you. Extremely fast updates compared to a standard 4 to 20 HART device. Here is a recording of the demo running on the physical bench so that you can see the LED that's blinking, indicating activity. As I had indicated earlier, our HART-IP stack is fully compliant to FieldComm group's test plans. And here is a snapshot of all the tests that's been compliant and passed. Some of these tests are pretty complicated and time sensitive in terms of command response time frame. And we have ran through the test suite. And as the test plans change, security functions get added, and other changes happen, we will keep up with the compliance requirements. So as a device vendor, you need to focus only on the sensor aspects of the design, and SES will provide support for the remaining items. So as I mentioned earlier, to enable the APL development ecosystems, SES will have an APL to Ethernet switch available in Q1 of 2023 as part of our developer platform. This will be in a standard DIN enclosure, providing 3 APL ports, 1 Ethernet port, a built-in DHCP server, as well as to provide APL power. We will provide SPAA only, no negotiation, just the 540 milliwatts you need. And we will also be able to provide some APL diagnostic data on the loop conditions. This product will make development easy, as well as if you're doing a trade shows or demos, the setup will be very easy to do. It can also be a great tool for bench configuration of the device prior to deployment. And we expect this will be available in January of 2023. So how can SES help you? We can significantly shorten your learning curve in moving from HART to HART-IP APL. We will handle all evolution and specification changes and keep you up to date. We'll deal with FCG test specifications, test requirements, TLS features, to name just a few. You can use our reference design as it is, or you can customize it by form factor and firmware. Or you can take our design and we can help you make your own custom design. Leverage our experience in hardware design for the APL as well as firmware development for HART-IP in your design. You can stay focused on the sensor aspects of the design. We will convert to HART-IP and APL. And this will provide you with very fast updates in terms of sensor PVs and so on, with minimal change to your existing design. SES can also support you with FDI and DAD support as you are completing your project. As I mentioned earlier, SES has been involved in the HART technology for a very long time. We have several other offerings, including our high-speed HART modem solution, FSK HART modem solution, and HART 7.x compliant HART stack. We also have been shipping our 4H 16-channel HART-IP gateway. We also have an edge gateway to cloud that supports multiple protocols for data gathering from sensors and PLCs. We support HART, Modbus, SCADA, OPC UA on the edge gateway. SES has a complete set of design services. Please check our website for more information. Here's my contact information, Pran Haran, and I also have our CEO's contact information. Feel free to reach to us with any questions about the APL design or any other aspects related to product development. We'll be very happy to assist you with those inquiries. Thank you for listening. I appreciate your time.
Hello everyone, I'm Jegajith, Director of Embedded Engineering at Utthunga. Today we are going to talk about one of our Ethernet-APL sensor reference design. So we are going to cover various aspects today. One is what is the architecture of the systems and what is the use case of the systems and what is the timeline or when it is available for our customers and as well as FCG members. So let's go in detail. So Ethernet-APL, so this is the specification and as well as the APL standard. I'm sure everyone aware about that, but still I would like to give a quick introduction about that. So Ethernet-APL is one of the first Ethernet standard which is introduced into the process automation side, which is intrinsically safe. And being Utthunga is one of the product engineering company, we will also offer end-to-end product engineering on Ethernet-APL based design. So we can split that offering into various stages. It could be your existing legacy device converting into Ethernet-APL standards, or the complete new design on Ethernet-APL based design, or the architecture of Ethernet-APL framework. It's including from field devices, how many power switch you need, or how exactly we are going to connect with the standard Ethernet, the communication standard. So we will go a little bit detail about our sensor design. So this is Utthunga reference design which we have designed for Ethernet-APL, which is compatible for power over data line. And this is again going to communicate with another Ethernet-APL switch or any other adapter which can be connected from Ethernet-APL to standard Ethernet, which is running a HART-IP or any other communication module. So the sensor features which if you go little more details, there is a microcontroller which is capable of clocking up to 400 megahertz based on the use cases. So this can put FreeRTOS or any other RTOS applications based on the use cases. And the entire system is designed in a low power architecture. So there is a various shutdown features. Even though we have a multiple sensors, there is an IO interface, so we can shut down this to save the power. And this is compatible for IEEE 802.3CG standard, which is nothing but SP specifications. And coming with an accelerometer, which is having up to plus or minus 8G dynamically selectable range and 16-bit data output on that, and high shock stability on that. So and this is temperature compatibility up to minus 42 plus 125 degree in terms of the sensor architecture, and the object temperature sensor, which is capable of measuring the temperature from minus 70 to plus 380 degree. So that's the specification of this device, and measurement resolution up to 0.02 degree Celsius. And this is designed as per the intrinsic safety compatibility. So this can be deployed in zone 0 as well. So let's go how exactly the shape of the device and how we can do fit into. So as you can see in this figure, there is a typical gas sensor. So we are designed a circular shape. So we are just comparing with €1. So this size is so close to an euro size. It's a 30 diameter, which include the Ethernet-APL 5 and a microcontroller and the power circuit with a 2-pin connector. So the idea is something like that with any typical gas sensor or typical actuator. So definitely there is an area where all the connectors and everything is sitting inside. So we would like to do kind of a retro engineering where we can put this as an adapter with your existing compatible HART or any other interfaces and convert into Ethernet-APL standards. So the necessary, the firmware which can convert this data to Ethernet-APL, that can be programmed, or we can do an architecture based on the device specific things. And again, this is a reference design, so this can be customized when this is evaluated from the different sensors or actuators, different form factor, we can customize it. So when you're talking about the firmware architecture, so obviously we have done kind of a modular architecture. It has a hardware, as we discussed, various components. As a reference design, we are using some sensors, so it could be an I/O also in future. And so there is a hardware abstraction layer. So typically it is divided into two aspects to have a simplicity, an Ethernet driver and sensor driver. So Ethernet driver is typically the I/O interfaces and all the driver related to the PHY perspective, and on top of it HART-IP is running. So HART-IP is, again, this is talking to the TCP/IP stack, and on top of it we are running the sensor applications. And again, sensor, we have sensor drivers which is acquiring all the data from the sensors, and the sensor middleware is packetizing all the sensor data and clubbing together with the HART-IP information and sending to over Ethernet-APL. So that's a typical architecture. As you can see, this is completely a modular architecture, so we can unplug any kind of applications or any kind of Ethernet protocol in this device in future. So this is system interfaces. So how exactly this is validated? So there is an Ethernet-APL host which is having a standard Ethernet, and other side we have a Ethernet-APL connection which we have tested with a twisted pair cable. As you know, 10^21L can go up to 1000 meter. So we have tested this with the power over data line capability, and the sensor module is capable of getting the power from the data line itself. And if you see the block diagram, there is a separate block for the power supply which is supplying the power to the different components in that, including the microprocessor and the sensor device. And the microprocessor is capable of controlling the power. Basically, you can shut down these sensors or any of the I/O features. If you want to use it, we can use I/O features. And we have a built-in eScorpio ROM to store any of the data or any of the settings which is specifically on the sensor configurations or any other settings of the device. So this is a typical testing compatibility to ensure that this is compatible with the standard Ethernet-APL. We have taken one existing evaluation board from Unlock devices which is connected to our the Ethernet-APL reference design. From there we have tested with an standard TCP/IP stack with a test application on the PC side, so which we evaluate the various speeds, how exactly this is connecting, and on top of it we ported the HART-IP. So coming to the design roadmap, this is started somewhere in October, the complete design, and it is completed as a full-fledged stage, whatever you can see in this slide. We completed by November, and now we are in a stage of porting the HART-IP and the testing phase, and the hardware engineers are working on the pre-complaints and validation on the intrinsic safety side, and by January this is available for our customer for evaluations. So anything in details about this particular hardware, if you are interested, please feel free to contact FieldComm group or Utthunga.com. Thank you.
Okay, we're definitely into the home stretch now. I think it's midnight in India, so we lost Jax. I don't see him anywhere. We've got a couple of questions from the audience that I want to go through, and we'll quickly move on to the end of this. It looks like it's finally gotten light out on the West Coast. Cyrus, your room is light all of a sudden. Pran, same with you. Good to see that. All right, so first question I'm going to throw out at Pran. So, it looks like as part of your development kit, you have a HART-IP stack, or at least you have the components of a HART-IP stack that, when combined with somebody else's existing HART product, can form a HART-IP over APL device. Can you just kind of elaborate on that a little bit? Do I understand you correctly?
Yeah, the demo we showed. So essentially, we hooked up a 420 HART on the HART board, and our eval board works like a gateway, transmitting from one to the other.
Mm-hmm.
So this is just to show, and as well as evaluate quickly. A customer can look at the product very quickly and see how this is going to do. And we can also provide an interface where we can actually represent customer's device on the APL side without making any code changes. They can download like a configuration file, and we simply pretend we are the customer's device.
Yeah.
So the only thing left open at that point is, since you're talking on the FSK on one side, you are going to get slow responses, not fast responses.
On that side, yeah, of course.
And
Okay.
just like you also heard from Softing and others, to speed it up, you have to connect it through serial port or some other mechanism, so you can get faster responses.
So it's
this way you can engineer your product quickly and say, yep, it's going to work, and then move on to a custom design or some other stacked module or whatever way you can approach the design.
So it's basically like the HART-IP adapter that we talked about earlier in HART-IP to Ethernet-APL adapter that we talked about earlier.
Yeah, FieldComm group originally sent out a proposal. Yes.
Yeah. Okay, sounds good. Sounds good. That makes sense. And I'm assuming that this is licensable and something that people can have access to, and that developers can have access to, and if they work through you.
Exactly. Yes. And I'm also assuming the customers already have a lot of their 4-20 HART commands and others, and we will help them port them over, or they can do some of the work themselves. We can assist them. We can work with the different models.
Mm-hmm. Cyrus, I'm going to move on to you. I was very intrigued by your cable story, and I wanted you to kind of just tell us more about this cable tester product. Is this something that you could see a developer using at all, or is it primarily targeted at end users? And and I know you had a couple of other things that you were discussing. If you could just give us a brief overview of where they stand and in commercial availability and what you're looking for.
Yeah, the cable tester I see as an actual end user application.
Mm-hmm.
I'm not seeing a way a developer would have much use for that. The other products, and that one's under development. We're kind of in the early stages of that, prototyping some things. The other products that we've been working on, we have two what we call Ethernet-APL adapters, and they're basically creating an interface between a PC or a laptop and an Ethernet-APL device. And that interface is either standard Ethernet RJ45, so you can hook up an Ethernet-APL to a standard Ethernet network, or a USB cable. And the difference there is because the USB cable, we kind of see that more as an end user wanting to do something in the field, or it could also support on the benchtop, going out and checking or configuring a device kind of in a more portable manner.
Okay. Mm-hmm.
And the Ethernet version is for more for developers. People just want something on their benchtop. Both of these products provide power as well as the interface to the device. So it just makes it easy for a developer or somebody who's using APL products to connect from a local PC to an Ethernet APL device.
Alrighty, thank you. Okay, that's it for questions. I want to thank both of you guys once again for joining us. You did a lot in terms of contributing content for this. It's great. Obviously, we'll be in touch, but I think that your roles and your purposes here have been fulfilled, and you can go back to doing your day jobs now. We're about to wrap up in a few minutes here. I think Heather is going to walk through a little bit of content on the microsite and some of the other stuff that we have, and then we'll be able to see if there's any questions come in at the last minute. If not, we'll call it a day. So please, let's go.
All right. Thank you, Paul, for the introduction. Most of you will have been watching this stream on our website. I sent out a link to everyone who registered so they can come to our portal here for HART-IP. Let's see, do we have my screen? Here we go. So here, this is familiar to you watching right now. As you open this and scroll down, underneath the live video, I captured this when Wally was talking. We have a bit more information, some references. Here's the agenda, everyone can see. Additional HART-IP resources, some previous videos that we did for other webinars, also Ethernet-APL resources. And then finally, the developer tools are described here in brief. And there's a link to where you can place an order for any of those. So that just gives you a little overview of that section, this middle part of the page that you're on today. And if you look at the bottom right corner, once we get down there, there we go. So if you've been asking questions, you'll see that little bubble in the bottom corner of the website. If you missed it, not a problem. You can send us support tickets after the show is over, and I'll send the questions off to the appropriate person and get in contact with any of our experts who joined us here today. Also, each of these logos represents a page for our presenters who shared with us today. If you open one of those, you'll see contact information about each of them, maybe some of the videos you saw earlier today, how to contact each one of our presenters, either a website or an email address is available to you. And then additional materials from their website they provide to us, which is relevant to what they were speaking about today. There you go. That's, for instance, one of the attachments there. And you can come back to our portal. So that's a very brief overview of this particular portion of our website. And like always, if you need specifications, if you have questions, please feel free to reach out via our support portal. We'll get them answered as soon as we can. And I think that is all for me at the moment. So, Paul, do you want to come on and we can wrap up everything for today?
A second here. Why don't we put all the FieldComm group staff on that have been involved in this workshop? It's been a lot of effort. We're very happy to have presented it, and hopefully this is all worked out and you found it very informative. We answered a lot of questions along the way. Those questions are clearly in here. Maybe we can try to put together a Q&A document afterwards. We'll see. We can publish all of that. The webinar itself is going to be available on YouTube. I don't see that we have had any other questions come in, but I think that we're in pretty good shape at this point in time. And thank you all for joining us again. Kudos to the FieldComm group staff and our partners that participated. And let's call it a day. Thank you. I think we're done. Bye.
Thanks, everyone.